जबाब देती जिव्हा सह्याद्रीचा सिंह गर्जतो शिवशंभू राजा
दरी दरीतून नाद गुंजला महाराष्ट्र माझा
जय महाराष्ट्र माझा जय महाराष्ट्र माझा काळ्या छातीवरी कोरली अभिमानाची लेणी
ओलादी मनगटे खेळती खेळ जीव घेणी
दारिद्र्याच्या उन्हात शिजला
विठ्ठलाच्या घामाने भिजला
देश गौरवा
हॅलो हॅलो माईक चेक चेक 1 2 3 4 5 हॅलो 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 येत नाही यायला पाहिजे
बॅक साईडला
हॅलो हॅलो बोल माईक चेक हॅलो हॅलो होतंय का आकाश
जय जय
Hello, hello, hello. Mic testing. Hello. Latency yourself. Good morning, ladies and gentlemen. I, Akash Khere, would like to welcome you all to the inauguration ceremony of the 31st Raman Memorial Conference on behalf of the Department of Physics. Today, we come together to celebrate knowledge, innovation, and collaboration. We have an enriching lineup of events ahead, and we are privileged to be in presence of the distinguished guests who have graced this occasion with their presence. To commence this event, I would like to invite our esteemed dignitaries to take their seats on the dais. Our chief guest, Professor P.S. Anil Kumar. Our Pro Vice Chancellor, Professor Parag Kalkar. Our guest of honor, Professor Pramod Patil. And on behalf of Head of Department, we have Professor Arun Banpurkar sir. And finally, our Chairman, Ms. Anupama Kadam. Ladies and gentlemen, let's welcome them with a big round of applause. Okay. So, I would like now to request the audience to stand up for the Vidyapit Geet and Maharashtra Geet. I request the Maharashtra Gate.
महाराष्ट्र माझा गरजा महाराष्ट्र माझा जय जय महाराष्ट्र माझा गरजा महाराष्ट्र माझा भीतीनं आम्हा तुझी मुळी कडकडणाऱ्या नभा अस्मानाच्या सुलतानीला जबाब देती जिभा सह्याद्रीचा सिंह गर्जतो शिवशंभू राजा
दरी दरीतून नाद गुंजला महाराष्ट्र माझा.
जय महाराष्ट्र माझा जय महाराष्ट्र माझा काळ्या छातीवरी कोरली अभिमानाची लेणी
ओलादी मनगटे खेळती खेळ जीव घेणी.
दारिद्र्याच्या उन्हात शिजला
विठ्ठलाच्या घामाने भिजला
देश गौरवासाठी झिजला दिल्लीचेही रक्त लागले तो महाराष्ट्र माझा जय जय महाराष्ट्र माझा गरजा महाराष्ट्र माझा जय जय महाराष्ट्र माझा
I request the chairperson, Ms. Anupama Kadam, to enlighten the audience about Raman Memorial Conference. Please.
Good morning, everyone. Respected dignitaries on the dais, Honorable President to today's inaugural session, Professor Parag Kalkar sir, Pro Vice Chancellor of Savitribai Phule Pune University, esteemed guest of honor Dr. Pramod Patil sir, Dean, Faculty of Science and Technology, Savitribai Phule Pune University, Honorable Chief Guest Professor P.S. Anil Kumar sir from IIC Bangalore, respected Head of Department Professor Banpurkar sir, distinct dignitaries, esteemed faculty members, dear student, and all our value attendees and participants. Good morning and warm greeting. On behalf of organizing committee, it is with a great honor and privilege I, Ms. Anupama Kadam, welcome you all to this prestigious occasion. Today mark a significant milestone as we have gathered for the 31st Raman Memorial Conference, a platform dedicated to knowledge sharing, collaboration, and innovation. At the very outset, I extend my heartfelt gratitude to our chief guest, Professor P.S. Anil Kumar sir, whose presence today adds immense value to our program. Sir, your achievements and contributions are a great source of inspiration to all of us. We are also privileged to have our guest of honor, Dr. Pramod Patil sir, with us today, whose support and insight will undoubtedly enrich our discussion. A special thanks to our President, Pro Vice Chancellor, Professor Parag Kalkar sir, for their leadership and unwavering support in making this event possible. I would also like to express my sincere appreciation to our Head of Department of Physics, Banpurkar sir, for their continuous encouragement and valuable guidance in organizing this event. Their dedication to academic excellence and research has been instrumental in shaping our initiatives. Raman Memorial Conference was started in 1993 by the research student of the Department of Physics under the aegis of Indian Physics Association. Ever since event started off 30 years ago, it has continuously grown in all aspects, where it to be number of participants, the event budget, interaction with industry, or enthusiasm of the student. All have seen grown in quality and quantity. I am happy to inform all you that this is a consecutive 31st year we have gathered here with a new hopes, new idea, and some new faces. RMC is a platform specially available for a research student of the Department of Physics and Research Institute in and around Pune, but the horizon is never limited. In these 2 days, students get opportunity to interact with the eminent scientists and academic personality during the seminar. The conference helps young researchers to boost their confidence level to participate in national and international conferences. Since the conference is wholly organized by the research student, it helps them to learn administrative and management skill, which is essential for their development. RMC is a two-day conference full of various events. There are invited talk by prominent scientists from the various field, thesis presentation, oral presentation, poster presentation, and cultural program. The open discussion after the poster or oral presentation is a key to self-assessment and self-understanding for the student. We are happy to announce that this year we have about 7 invited talk, 5 thesis presentation, 34 oral presentation, and about 85 poster presentations. To encourage and recognize the outstanding contribution of our participants, we are pleased to announce awards across the different presentation categories. We will be awarding 3 prizes for a thesis presentation. Additionally, 3 prizes will be presented for oral presentation, 3 prizes for a poster presentation in the research student categories. With this, we also give 2 prizes for which is recognized in the BIDE. This is called BIDE prizes, 2 for the Damle prizes. Furthermore, to inspire and motivate our young scholars, we have also introduced 3 prizes for a poster presentation, specifically for the graduate and postgraduate student. We hope these awards will encourage enthusiastic participants and foster a spirit of excellence in research and innovation. With this brief introduction of RMC, once again I extend my warmest welcome to all of you. Let's make this event a grand success together. Thank you very much.
Light symbolizes knowledge, wisdom, and the removal of darkness. To mark the auspicious beginning of our event, we shall now proceed with the lamp lighting ceremony. I request our esteemed dignitaries to kindly step forward and light the ceremonial lamp.
शंकर प्रभृति देव सदा वंदिता क्षमा पातु सरस्वती भगवती निःशेष जाड्यापहा।
To honor the presence of our distinguished guests, we now move on to the felicitation ceremony. May I request the Professor Arun Banpurkar to kindly felicitate our guests. Firstly, the chief guest, Professor P.S. Anil Kumar. Pro Vice Chancellor Professor Parag Kalkar. Guest of Honor Professor Pramod Patil. I now request Chairperson to kindly felicitate the Professor Arun Banpurkar. Sir. Research and innovation are at the heart of academia. As we celebrate scholarly contributions, it is our privilege to unveil the abstract book, a compilation of valuable research insights. I invite Chairperson to do the honors of releasing the abstract book. I invite esteemed guests.
I would now like to call upon Professor Banpurkar to give the opening remarks.
There is another program scheduled at sharp 9:45. So I take permission of the chair to, because the program will continue. It's a good opportunity for all of us to network with all the expert and stalwarts from the physics. The dignitaries on the dais, Honorable CPS Anil Kumar ji from IISc Bangalore, my colleague in university, Dr. Pramod Patil sir, Dr. Arun Banpurkar sir, Chairperson Anupama Kadam madam. I'm very happy that this is the 31st edition of conference, and I'm just going through that 2025 is the International Year of Quantum Science and Technology. So I think it's an achievement that we have started thinking about it 31 years before to conduct such kind of student-driven conference. And very happy to know that this all conference is led by the students, basically, because at the end of the day, the people skill matters. So what you learn during the process is very important. And just now, Banpurkar sir was sharing with me that there is going to be a paper presentation, then 7 invited talks and thesis presentation, and more than 85 posters have been presented. It's a very good thing that we always think that whatever we learn, whatever we do, or whatever we understand about the subject is the ultimate thing. But I think the interaction is more important, because once we interact with the people from the same area, we need to we can understand much better. We can get some more insight about the subject. I think this conference will definitely bring more insight, more deep dive into the subject matter. I should not tell you that quantum computing is so important, and the research and the innovation which is going on in this field is very, very important for all of us. And Savitribai Phule Pune University is a legacy, basically the Department of Physics, long history of creating the best human beings in this subject, and which are recognized all over the country. And the future of this lies in the student who are pursuing their PhD program or who are focusing their research or master's program from this prestigious department. Research is a very important thing. The reason is a lot of innovative things are required to handle this country of 142 plus crore people. And this research will definitely bring some changes, practical changes. The kind of posters the student have presented, I was observing in the morning, that a lot of things are required to be done. Still, many more are required. We always work. Research is not like a Google map where you Google something and then you reach to the destination at the end of the day. I think it's a travel through unknown territories, trying to finding out and fix. So somewhere this kind of networking is more important, where we realize that somewhere we are missing something and something needed to be added, something needed to be eliminated, because sometimes we have a dream and we just drive our dream very hard without understanding that somewhere we need to realign ourselves with the latest things which are happening. And I think this expert talk will definitely bring that kind of more clarity, more purification in your thought process, in your research process. Definitely it will bring more changes in your thinking. So I wish this conference all the best. Keep talking with the people, not only in the session, but beyond the session also. Try to understand that how they look at various aspects of this theme, and try to see that your thought process is more purified at the end of the day. I'm thankful to Department of Physics and all of you. And I would like to take your permission to leave this August gathering. The reason is there are another program is scheduled far away, but I'm going to join now our online mode. So thank you very much to making me a part of this journey. Thank you and all the best.
Thank you so much, sir, for giving us your valuable time and motivating the entire audience with your speech. I would now like to call upon Professor Arun Banpurkar to give his opening remarks.
I am a HOD, but I am not HOD. Actually, Professor Dhole is HOD. Professor Dhole has cooked all the, let us say, for the conference, and he has made all the arrangements and everything. But at the end, he has to move to his family wedding function. That's the reason I actually step in at a just like last moment. And this is kind of, he has cooked everything, and I am here to serve you. Okay, yeah. Okay, so this is okay. Because of a Professor Kadkar, he has to move. Okay, respected sir, respected Patil sir, respected our chief guest, Professor Anil Kumar, and actually my senior faculty member, my actually colleague, dear student, and participants. I would like to mention a special point about the 31st actually Raman conference. Okay. This Raman conference is actually this year it's actually thematic. Every year the student bring one different theme. This year the conference theme is quantum information and technology. Okay, always we actually sit together and look at, okay, what is the international scenario at that year, and depending upon the international scenario, the student and faculty member actually decide, okay, so this year this should be the theme, and based upon that theme the student arrange lectures, a student find out the speaker and everything to match the theme. That is one important point. There is also another aspect of this Raman conference. This is the 31st event of the Raman conference. It is firstly started in 1994, and because at the same year I joined, even Professor P.S. Anil Kumar is also our alumnus, and he was also here looking right from a first Raman conference. Okay, so this Raman conference was first, let's say, initiated by Professor Ogle to provide a platform to a student, because at that time conference means only student can be just like a take part or just like present a poster. But here this is a different way of the conference. This whole total conference is arranged by a student, right from funding, right from managing a poster, right from managing a presentation and everything, even gathering funds and everything. So over the 30 years, it is fully matured, and now they are even sometimes even if you wanted to conduct a conference, they are our, let us say, for example, gurus. Actually, we are at a backstage now, okay, and they are so much expert in dealing this kind of different things. And this, they are also MSc student, they are also PhD students, and they set up everything based upon their, and they also come to us, okay, so what kind of, let us say, talk has to be arranged and everything, and depending upon their discussion, we arrange the talks and everything. But it is fully managed by a student, for the student, and this main important point is that they get a benefit that just like presenting some, let us say, paper or some work at this conference, they are very much, let us say, equipped to present their work in any conference at international level. That is actually, I'm sure that they are getting this, let us say, platform or benefit, that whenever they, because most of the students say that even I am presenting a, let us say, paper in a Raman conference, he is busy, or his confidence into present in any conference. That is important point. Okay, yeah, and this is continuously, it is actually a success story. Okay, and regarding funding and everything, we have now enough fund. They are also having, let us say, collaborators, or even fund is supporter, right, from different banks. Even physics department endowment fund is also supporting so there is enough fund to support. And I wish that this is very, let us say, noble activity. It should continue, and I wish that it should continue for infinite time. Okay, thank you very much for this.
Thank you so much, sir. I would now like to, it is my honor to introduce our guest of honor, Dr. Pramod Patil. Dr. Pramod Patil is a distinguished academician and a researcher with over 23 years of experience in academia, research and industry. An alumnus of the College of Engineering, Pune. Currently, he serves as the professor and dean at D.Y. Patil Institute of Technology in Pimpri, Pune. And he is also the Dean, Faculty of Science and Technology at Savitribai Phule, Pune University. Dr. Patil has held key leadership positions including Principal, Vice Principal, Head of Department and Associate Dean. Under his leadership, the institute was ranked in the NIRF's top 200 engineering colleges in India, and multiple programs received NBA accreditation. He has played a significant role in setting up online examination infrastructure and implementing New Education Policy 2020 at Savitribai Phule, Pune University. With 8 patents and over 90 research publications, he has received awards for his work and authored 2 books. As an active member of professional bodies like CSI, ACM, and ISTE, he has delivered keynote addresses and reviewed papers for prestigious journals including ACM, Springer, and Elsevier. His expertise spans business intelligence, data mining, big data analytics, and machine learning. Dr. Patil continues to contribute significantly to education, research, and industry collaborations, shaping the future of computer engineering. I request our guest of honor, Dr. Pramod Patil, to say a few words.
Yeah, thanks. Very good morning. Very good morning. Very good. Dignitaries on the dais, our chief guest, Professor P.S. Anil Kumar sir from ISC Bangalore, Head of the Department, Professor Dr. Dhole sir, dignitaries on the dais, Dr. Banpurkar sir, the chairperson of this conference, Dr. Anupama ma'am, Professor Datta sir, all the senior professors sitting here in this hall, and my dear students and participants. First of all, I'm very thankful to the organizer for giving me an opportunity to interact with all the participants during this prestigious conference that is on quantum science and technology. Dear friends, you know, this is the era of multidisciplinary, interdisciplinary, and transdisciplinary. And I think the topic that is chosen for this conference is really emerging and very useful in our day-to-day lives. At the same time, let me tell you that we are implementing this new National Education Policy 2020 at Savitribai Phule Pune University, and there also we are trying to inculcate or adding the courses related to emerging fields for upskilling the students and seeing that how the students can perform better at the global level. So the ultimate aim of that implementation is very simple: how we can produce the globally competent professionals with wings of knowledge and power of innovation. And I think this type of initiatives will definitely help us to enhance the knowledge, upgrade the knowledge, and coming together and sharing the ideas and discussing on those ideas is very, very, very essential. Knowledge is power, and empowerment through knowledge, I think, which can be done through this particular platform. Dear participants, you know, this conference is a great tribute to Sir Dr. C.V. Raman. And this is really, I wonders that you are doing it since 31 years. And when we were discussing, Dr. P.S. Anil Kumar sir is a alma mater of this department, and he was sharing his memories of this department, and this is really very heart touching. So still, it was very simple thing, but he was discussing, sir, somebody came to the head's office and asking some basic questions, whether this is wall bricks or a wood. But these are the memories, and I think 31 years legacy is really a great, and I heard that this conference is organized by the students, and really a great achievement. I think I read the name, that is Swati. Who is Swati? I think she is secretary of this organizing committee, and taking these initiatives and discussing about the research. Everybody is talking about research. Everybody is talking rather quality research, and coming together and presenting the research is a bit difficult, challenging, but having such type of platforms, that is becoming so easy for all of us. We are coming together and sharing the knowledge on a specific topic. So let me also share some few things about this quantum science and technology. Dole sir has given very good name in Marathi, that is Punjakiya Vidyan ani Tantradnyan. So it is really interesting, and it touches to our heart, and then we start thinking about that we should also come forward and do something out of it. We have to also see that how we can contribute to this great initiatives, and see that how it can be done. Dear friends, I'm not expert in quantum computing, but let me uh, take you through some basic understanding why quantum computing is so important, and what are the open challenges in quantum computing, and how the science and technology come together and contribute in quantum. So that is very essential. So let me tell you a few things about it. It is tremendous honor to stand before you at the Raman Memorial Conference, a gathering that brings together and bright minds to pay the tribute to legacy of Dr. Sir C.V. Raman, and to explore the frontier of science that contributes to shape the world. This conference not only commemorates the invaluable contribution of one of the greatest physicists of the 20th century, but also serves a platform to discuss innovations and breakthroughs that have taken us beyond the horizon of classical physics. And this is the Department of Physics, okay? And Dr. Raman has contributed a lot in physics, and we still remember the lights and the matters, how it works, and now it is going further, and we are talking about the quantum. Today I would like to speak about the field, but much Sir Raman's work challenges our understanding of universe and open new doors of future technological revolutions, that is quantum science and technology. So it is not just the physics, now it is going to see that how the technological revolution is going to happen in the quantum computing. Many times we discuss about like quantum computing is related to only uh, 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 the technological part, but it's not like that. The origin, the foundation is from the science, the origin is from the physics. Okay, so we need to understand the basics of it, and then definitely you can see that how it can be useful for the society through many ways. The legacy of Sir C.V. Raman's and quantum science, we need to understand these things also and see that how the Sir C.V. Raman's contributed in that. So Sir C.V. Raman's groundbreaking discovery of Raman's effect, we never forget about it. Revolutionized our understanding of lights and interaction with matters. His work exemplified the power of knowledge in many ways. His contribution set the stage of exploration of microscopic world, a realm where quantum mechanics resume supreme. So these are the basics about this time, from where it started. If it is a legacy of 31 years, then we need to understand like from where it gets started. So while Sir Raman focused on classical physics and optical phenomenon, and his work laid a foundation that contribute influence modern physics. Now we are talking about the modern physics, and we need to see that what are the emerging areas in modern physics and how we can contribute in that also. So quantum mechanics, which governs the behavior of particles at the smallest scales, has evolved from the early studies of light and matters into an era of intense research that is transforming industries, economies, and our fundamental understanding of universe. So this quantum science and technology is part of the modern physics. So let me take you through the quantum science, a leap into unknown. Quantum science is founded on concept of deny our intuitions, ideas like superposition, where particles can exist in multiple states at once, and entanglement, where particles remain connected even where separated by vast distances. And I think Dr. Kadkar sir was telling research is not like a Google map. So we have to see that some unknown territories and see how we can go and achieve the goals. So these principles have opened up new avenues for technological development. I'm from engineering, so I know the technology, and I think physicists and engineers, they can come together and they can contribute for technological development, with quantum technologies becoming a powerful tool in the field ranging from computing, communications to sensing and encryptions. So I think this computing, communication, sensing and encryption, these words are very popular in this era where we are talking about artificial intelligence, data science, data mining, data analytics, and business intelligence. As we gather today to honor the Raman's contribution to science, we also stand at patience for a new scientific era, one that could reshape the world as we know it, just as his discovery reshaped our understanding of light. So let me take you through the quantum computing, the future of information processing. So lots of informations processing is happening around, and we have to see that how we can come up with the emerging algorithms, emerging techniques, tools to process the large amount of data. The most widely discussed area of quantum technology is quantum computing, which promises to revolutionize information processing. Unlike classical computer, which store data as bits, that is zeros and ones, quantum computers use qubits, and qubit is a part of the computing science and technology that is totally based on the superposition. Thanks to superposition, where people have contributed a lot. These qubits can exist in multiple states simultaneously due to superposition, and additionally qubits can become entangled meaning that the state of one qubit can depend on the state of another, no matter how far apart they are. So this is very important. This is the basic things that we have to understand during this particular conference, and see that how these things can uh, revolutionize, and the things are happening accordingly. So this radical shift in computing power enables quantum computer to solve problems that would take classical computers millennia to process. Fields such as cryptography, artificial intelligence, drug discovery, and optimization problems stand to benefit enormously from these advancements. So today I'm feeling so proud to be a part of this particular conference, where people, they are going to talk about the quantum science and technology together. So these are the part. This is not just a part of engineering, sir. Unfortunately, I can say that here in Maharashtra, engineering and science colleges, they are working in isolation. So it should not happen. They should come together and they should collaborate with each other. They should connect each other and see that how simultaneously they can work. Many times we heard about the material science. Lots of things are happening in material science. Lot of good R&D institutions, organizations, they are coming forward and they are contributing in material science as well, like CMATE and all. And we should collaborate with them and see that how it can be done so easily. So, however, these are the significant technical challenges ahead. Building scalable computing computers, maintaining qubit coherence, and developing quantum error correction protocols remain open questions. So, my dear students, these are the some of the challenges that we have to understand and see that how we can develop a small laboratories, how we can develop a small ideas, how it can be presented before, how we can get the solutions out of it. That is very much essential nowadays. Yet we are sensing extraordinary progress with quantum process now operating at unprecedented levels of performance. The path is being paved for a new era of quantum algorithm that will solve the problems we previously thought were unsolvable. So basics never get changed, but the things which are moving ahead, so we have to be with it and see that how we can solve the unsolved problems with these technology. At the same time, let me take you through quantum communication. That is also very important. The dawn of secure networks, another era of immense promise. Quantum communication, which seeks to use the principles of quantum mechanics to create communication systems that are inherently secured. So this is the contribution from the physics, that they can also contribute in how communication can inherently secured. Quantum key distribution uses quantum entanglement to create encryption keys that cannot be inserted or altered without detections. Any attempt to envelop on a quantum communication systems would disrupt the quantum state, altering both parties to the intrusions. So intrusion detection system is not part of the communication networks, but it is now part of the era of computing quantum science and technology. And the third, that is quantum sensing, that is revolutionizing precise measurement. So that is also needed somewhere in the medicine field or healthcare field or drug discovery. So where we can contribute and see that how it can be useful. So these are the some of the challenges that we have to take up through this particular platform, and see that how we can come together and we can work in a team and develop a new good solution, emerging solutions, or innovative solutions. At the outset, as we celebrate the legacy of Sir C.V. Raman, let us remember that his words was not just the discovery but an invitation to ask deeper questions, to explore the unknown, and to push the boundaries of what is possible. So possible thinking is very, very essential, and I think that possible thinking, critical thinking, problem solving, these type of platforms are definitely are going to help for all the participants, all the researcher, and all the teacher and student community. So today, quantum science and technology present us with an opportunity to contribute this legacy of inquiry and discovery. So the future of quantum science holds the boundless potential. By continuing to collaborate, share knowledge, tackle the challenges ahead, we can ensure that quantum revolution becomes a force for good, transforming industries advancing human knowledge, and ultimately creating a better world. I think this message I would like to give here from this particular platform to all the researchers. I'm now going to tell you about like how to present the paper, how to develop the paper, and what are the guidelines, what is IPR, and what is there are different funding agencies available here to promote your research or to support your research. Yes, of course, we all are researchers and we should pursue our knowledge and pursue our research in a systematic way. And I think here you will get all those research directions for giving the boost to your a small research idea, and definitely in future you can convert it into a very good innovative ideas which can leads to the startups. And I think our country's mission is that only how we can motivate the uh, students and faculty to do more and more innovations and start their own startups. At the same time, as we know, there are some few countries like China, US, and India. They have their quantum mission, and I think this type of conference is definitely going to also ensure their contribution in that particular missions. So there is a legacy of our university to taking such type of initiatives towards the national development or towards the nation betterment. So I think Department of Physics, Professor Dole sir and his team is doing a lot of things with the help of the students. Students are very enthusiastic, I'm seeing here, and they are taking a lot of initiative towards research and development. We were talking about NIRF also, that is National India Ranking Framework. I think research has got some importance in that, and I think ISC Bangalore is doing a great, some IIT is also doing a great, and at the same time, Savitribai Phule Pune University also contributing a lot in research and development. We are doing a lot of things in research and development, and by doing such things, we are also recognized, and we got third rank in NIRF, that is National India Ranking Framework for our university. So thank you once again for giving me an opportunity to interact with such a wonderful researcher over here, and given me an opportunity to share my views about quantum science and technology. Thank you very much. Yeah.
Thank you so much, sir, for enlightening the audience. I would now like to introduce our chief guest, uh, Professor P.S. Anil Kumar. He is a renowned physicist whose groundbreaking research has significantly advanced our understanding of condensed matter physics. Professor Anil Kumar earned his PhD in physics from University of Pune in 1998. His postdoctoral journey took him across the world, beginning at the University of Twente in the Netherlands as a Dutch Technology Foundation postdoctoral fellow. He then moved to the Max Planck Institute of Microstructural Physics in Germany, where he was awarded prestigious fellowships such as the Max Planck Postdoctoral Fellowship and the Alexander von Humboldt Research Fellowship. In 2004, he joined the Indian Institute of Science (IISc), where he has been at the forefront of research in spintronics, magnetic nanostructures, and magnetotransport phenomena. His recent work on topological insulators and ultra-thin ferromagnets continues to push boundaries for modern physics. I would now like to call him on stage to
Thank you. First of all, let me thank the organizing team, the students of the department, for inviting me to this prestigious conference. And I thank all the faculty members of the department for inviting me. It's a lot of memory when I stand here. So I came to the department in 1990 and left the department in 1998. And I would say that, when I'm standing here, the department contributed a lot for me to stand here. I'm very happy to hear that, Professor Anjali Shirsagar, Professor Rajiv Pathak, who were teaching us at that time, is teaching the MSc students even now. So it's very, so you are at the safe hands, I can tell you. So the department has evolved. I mean, if my memory is correct, we started this with the Raman Memorial Mini Conference. It was RMMC. And after 2 or 3 years, it became RMC, which is Raman Memorial Conference. And this gave a very good platform as far as I am concerned in my career, right? So your presentation skills get improved during this conference, and that gives you confidence to go and present elsewhere. And that time, you know, we had around 40 plus faculty members here, and they will come to your presentation and poster and grill you like anything. So once you are surviving that grilling, you can survive anywhere in the world. So students, at that time, you know, this department never slept. So it was 24/7 working department. I hope that this tradition continues here. And I hear that large number of publications are coming every year from this department. So that truly speaks about the caliber that this department has. So many times the students have a confusion whether they are studying in MSc or PhD. Is there any future? Is everything that is done, I mean, whether anything is left to be done in physics or in research. So that's a confusion many times students have. See, sometimes I give this example. I mean, it's not well documented, but it is told that in 1899, the American patent officer has made a statement, it seems, that he, turn of the century, he looked around, electricity is there, water is there, motor car is there. So he said that all what is needed for the mankind has been invented in 1899, yeah? If you look at today, such a foolish statement, right? Similarly, if somebody makes a statement today that all what is needed for the mankind has been invented, it won't take even 10 years to identify that such a foolish statement it is. See, when I studied in this department, I never thought that a mobile phone will be in my pocket here, right? And if I remember, our computer lab didn't have a computer with a hard disk. So we were coming with this 5.5-inch floppy. You go to the computer lab, insert the floppy, boot the system, and then, you know, do the Fortran programming in our computer lab in the first year. And when I started my PhD, I got my first computer with a hard drive, and that had 20 MB hard disk. It was a huge, you're working with 512 kilobyte floppy to 20 megabyte. It was a giant leap for us. And if you look at today, a 2 terabyte computer is a common affair. But if you look at last 5 years or so, the hard disk capacity is not improving because it has reached its saturation called superparamagnetic limit in the memory storage. So now people are thinking about, how to go vertically up. So the space which you occupy in your computer hard disk, 1 bit space, now people are thinking about how we can vertically integrate. Imagine that at the place of 1 bit, if you can vertically integrate 1000 bits, you will have a 2000 terabyte computer soon. So, but it takes time. It won't happen overnight. In 1956, when the first transistor was invented, you must have seen this photograph of the germanium transistor, like a big transistor. So that is the job of the physicist, to invent things. Then engineers will convert that into technology, and you have now billions of transistors in your mobile phone. So this is how the science is progressing. So what is important at this point of time is for students is to learn the problem solving skills. So I'm very sure that you get a lot of assignments for your MSc, and you start solving those problems, and that is the first step. And then you have your tutorials where things are solved on the board again. And I think it is still continuing during our time it was there. And then once you start doing research, you again start solving problems of a different kind. The first 2 years of MSc, you're solving problems where you know that there is a solution existing. When you start doing your PhD, you start solving problems where you don't know whether a solution exists. Forget about the solution, right? Whether the solution exists, you don't know. But during this period of your PhD time, you start learning the problem solving skills. That is what is going to take you to higher heights. For example, today, I mean, if I look at my students, maybe around 32 students have completed their PhD under my guidance, and my all initial batch of students were uniformly moving towards academics, faculty members in IITs, etc. But of late, I'm seeing that a sizable number of students are also opting for industry. So 50% of the students go to academics and 50% go to industry. So it doesn't matter which area you work on. It's not an important aspect. How you work in that area and how you shape up your problem solving skills is the most important aspect. What does industry want? Or what does anybody want? Person who can solve the problem, right? So that problem solving skills is something that you should nurture during your PhD. And the first step is your MSc, where you start solving problems which have a solution which is existing or somebody else has solved some time back or whatever it is. Once you start doing PhD, you start solving problems where sometimes solutions are not existing and you are searching for solutions. So that problem solving skill is something that we should inculcate in us so that then you become very useful. So there's no question of whether there is any future or not. I mean, the technology is fast evolving. If you talk about the computers, why did it go from 20 megabyte to 2 terabyte? The reason is that the computer hard drives got introduced something called a read head, which is a spintronic read head, which is a giant magnetoresistive based read head in 1998. So that immediately changed the areal density. That means the bits are stored in your computer in zeros and ones, it's all magnets. If you take a magnet with a north pole and a south pole, when I keep the north pole towards you, I call it as a 0 state. When the north pole is towards me, it's a 1 state. So you can have, the zeros and ones. So that means when I say 2 terabytes of hard disk, that means 2 into 8 into 10 power 12 such magnets inside your computer. So now once you have a magnet like this, now the cap is towards you, you can say it's a 0 state, and cap is towards me, it's a 1 state. But inside a computer, there's no cap in a magnet, to check. So electronically you have to detect. So the magnetic stray field that is coming out of it was detected using this magnetic field sensor. It's a giant magnetoresistive sensor. So this was first discovered. I mean, people were working for several decades, and finally it became successful in 1986-87. Albert Fert and Peter Grunberg. So they were the pioneers in demonstrating GMR. And in 1998, it came to our hard disk. And in 2007, they got the Nobel Prize in Physics. So this is how it goes. So in that sense, there's a lot of things to be done. And don't think that, everything has been done. I mean, see, imagine that, you have a 2 TB mobile phone, right, with you. What all things you can store? How many movies you can store? See, though we are doing research for, these aspects, finally, 80% of our research is going for entertainment. Right. So that's how it is. So the mankind needs much more things. So a country with 142 crores people, solution cannot come just like that. It has to come through technology. The technological interventions are needed in the country for the mankind to prosper. And also yesterday I was discussing, see, the new fabs are coming into the country. So from 2028 onwards, India will start producing their own chips. It may not be of an Intel chip of, very high density. So 60 to 80% of the market can be captured by the fabs that is coming in India. So that technology is sufficient, but we should be ready. There will be a lot of job opportunities that is coming for students, not only in academics, even in industry as well. It is on the rise. And for the years to come, this will even rise further. So we should be prepared to grab that opportunity. So in that sense, work very hard. Keep the department 24/7 active. Anyway, I'm going to talk about, a scientific talk later. So with this, let me wish all of you all the best. And I'm also hoping a very good, fruitful discussion for the next 2 days to come. Thesis presentations, oral presentations, poster presentations. I have given in all this format here in this hall. So tomorrow you will be standing here and doing the same thing. Yeah, thank you. Thank you all for inviting me.
Thank you so much, sir, for your inspiring talk. I now request our respected Professor Banpurkar to felicitate the branch manager of Bank of Maharashtra, Uday Shankar Thakur, for his valuable contribution. Thank you so much. And with that, we now conclude the inauguration ceremony for the Raman Memorial Conference. We will take a short break, after which we begin with the talks. Uh, we will gather here after 15 minutes for the talks. At 10:30, the talks will start, so kindly be present by that time. Breakfast is served outside, so you can enjoy the refreshments and be back by 10:30.
Hello. Hello. Hello.
Hello. Hello.
Okay, I welcome you all to this session. Uh, this session, this is the keynote by Professor P.S. Anil Kumar. Uh, P.S. Anil Kumar is our distinguished alumni. He did MSc and PhD from this department. That's the most important thing. He's now a professor at Indian Institute of Science, Bangalore. And he is a convener and he is actually Dean of Administration. So he actually explained the role of this Dean and Administration and Finance position. So he is different kind of, let us say, situation as compared to our, let us say, university situation. Okay. So he has postdoctorate, did a postdoctorate at University of Twente, then he moved to the Max Planck Institute. He's a Humboldt Fellow, and I think 2004, no? 2004, he's a faculty at ISC Bangalore, and he's a person which work by hand on magnetic nanoparticle and then move to the magnetic heterostructure and everything. He is in a keynote speaker. He has mentioned about magnetism. So I welcome you and I hand over the microphone to you for your magnetism studies. Okay, thank you.
Yeah. Thank you, Professor Arun, for this nice introduction. Yeah, once again, thank you for inviting me here. Am I audible at the back? Yes. Okay, good. So today, looking at the theme of the conference, I thought that I'll speak about quantum materials and heterostructures. This is some work which I am pursuing for the last 12 years. So these are the people who worked in this area. For example, Abhishek Banerjee and Kujalada, they did their PhD in my group in the area of topological insulators. Kujalada finished his PhD and moved to Cambridge University. Abhishek is now a postdoc at Harvard University. And Gagan and Abhinav just completed the thesis, in the sense the thesis reports have come, now they have to defend the thesis with this, they will complete. And Dr. Ganeshan is my collaborator. So I work on different areas of magnetism, and as I told you, last 12 years in the area of quantum materials and technology. Now, we hear about quantum a lot. In India started National Quantum Mission, etc. So I thought I will give a brief introduction first about what is a quantum material. So we should understand what's a quantum material. Then I will give you some kind of a tutorial that about material, device fabrication, etc., and the physics we are extracting out of it. So if you really look at the quantum materials, exhibit novel electronic behavior such as superconductivity. I will qualify this with one more word, unconventional superconductivity. Then topological insulating behavior, unusual magnetic properties, not usual magnetic properties, unusual magnetic properties. Ferromagnetism, not. So unusual magnetic properties. The materials, when you are talking about topological insulators, graphene, vial semimetal, spin liquid, etc. Now if you go to Wikipedia, that's our first source of information usually. So if you look at the definition, it says quantum material is a broad term in condensed matter physics to put under the same umbrella materials that present strong electronic correlation and or some type of electronic order like superconducting, magnetic, etc., or material whose electronic properties are linked to non-generic quantum effect. Please watch this word, non-generic quantum effect. It's not quantum effect, it's non-generic quantum effect, such as topological insulators, etc. So I'll be talking about topological insulators a little bit today. So now let us examine the periodic table. If you look at the periodic table, does the elements of the periodic table belong to quantum materials or not? If you really look at, from hydrogen atom onwards, in quantum mechanics, we employ quantum mechanics to understand the hydrogen atom. So if it is materials that obey quantum mechanics, then from hydrogen atom onwards, every element in the periodic table should be a quantum material, but it's not. So it's not that every element in the periodic table is a quantum material. Then what does it, what qualifies? Now we look at copper, right? Copper has got this different kinds of orbitals, sp, df, everything we have learnt. So if you look at X-ray production and everything, if you look at it, quantum mechanics, without quantum mechanics, the properties of copper we will not understand. But if you wanted to talk about quantum material, so that they should display like, quantum oscillations, quantum Hall effect, and those kind of phenomena. So now if I take copper, the X-ray emission, etc., I need quantum mechanics to understand, but copper does not exhibit quantum oscillation. For example, to give an example, some materials, when you change the apply a magnetic field and measure the resistance, sometimes the resistance oscillates. So materials exhibit Hall effect, and certain materials exhibit quantum Hall effect. So these quantum materials are the materials that exhibit quantum oscillations, quantum confinement, quantum Hall effect, etc. So in that sense, copper is not possessing any such property. So copper is not a quantum material. On the other hand, if I take an element like bismuth in the periodic table, bismuth is a material with a high Z value, heavy material. So it has got some property called spin-orbit interaction. So that goes as Z to the power 4 generally. So because of this high spin-orbit interaction in bismuth, bismuth shows some exciting property. Like if you apply a magnetic field and measure the resistance, etc., it starts some kind of an oscillation. That oscillation is a manifestation of the quantum effect that we are talking about, the quantum oscillations. So in that respect, bismuth is an element from the periodic table that can be qualified as a quantum material. Similarly, if I take carbon. So carbon, again, any of this element in the periodic table, you need quantum mechanics to explain, but quantum material is not that. It's not that any element that obey quantum physics is quantum material. It's not like that. Now if I consider carbon, so carbon, if you consider carbon in different forms, carbon is diamond is made up of carbon. So diamond is not a quantum material. But if carbon in the form of graphite, and if the graphite, if you exfoliate to graphene layers, then this has got very peculiar band structure, and it shows these effects like quantum Hall effect, etc. So carbon in the form of graphite, and then when it is made into a graphene, it is a quantum material. Whereas the same carbon in the form of diamond is not a quantum material, right? See the difference. So now if you look at as a function of applied magnetic field, if you look at the resistance really oscillates. It's not a monotonic variation of resistance what you see. So these are the peculiar properties that qualify graphene a quantum material. Similarly, if you look at mercury, the importance of mercury, Kamerlingh Onnes as liquefied helium, and then showed that mercury is a superconductor below a certain temperature, which is a transition temperature. You see here around 4.2 Kelvin, it becomes a superconductor. But again, with the definition of quantum material, I qualified that superconductivity, conventional superconductivity, where you can explain things with the BCS theory, etc., is not a quantum material. So in that sense, mercury cannot be considered as a quantum material, whereas unconventional superconductors are quantum material. So in that sense, mercury, though it's a superconductor, as an element in the periodic table, is not a quantum material. Let us consider another element. See, I'm taking these elements, I have different properties. See, I started with the copper, a normal element that we look at it. Then I went to a heavy metal like bismuth, high Z, high spin orbit interaction. Then I moved to carbon again like diamond, not, graphene, yes. Now I move to mercury, superconductor, not. And now I come to another element, iron, cobalt, nickel are the three elements in the periodic table which shows room temperature ferromagnetism. So all magnetic materials are not quantum materials, but certain materials exhibit properties like spin ordering, frustration, quantum phase transitions, spin liquid behavior, etc. They are the quantum materials. So with a conventional, classical physics, not fully classical physics, but the ferromagnetism can be explained without going deep into quantum mechanics, right? So in that sense, iron is not a quantum material. Whereas if you make iron with a compound like, some arsenic based compound, etc., which shows unconventional superconductivity, yes, it is a quantum material.
So different elements in the periodic table in the form of a compound with some other material, with some other elements, some of them qualify as a quantum material, some of them are not. So I just wanted to tell you that quantum dots, generally when you speak about, it's not a quantum material. It exhibits quantum phenomena, but it doesn't show the properties that is expected from a quantum material. So in the modern context, today's context, when you talk about quantum material, is the materials that shows these kind of peculiar property. Now let us examine a little bit more in detail. So let me give one example as a tutorial, which is a topological insulator. So what's a topological? So we know that some solids are insulating like diamond, whereas some other elements, solids like graphene or graphite are metallic, though it is made up of carbon. And now this concept of insulators we are now revisiting through a lot of experiments and theoretical things, and we can qualify these insulators into two different categories again. If you look at the conventional ordinary insulator like diamond, we all studied electrons fully occupy energy bands. The next available electronic state is far away in energy. This energy gap is what renders diamond and silicon, insulating or semiconductor, whatever it is. Now what is this second group, which is a topological insulator, where the energy gap is getting modified due to something called a spin orbit interaction. Because of that, you see, when you talk about topological insulators, it is made up of heavy materials like antimony, bismuth, selenium, tellurium, etc. So this topological insulator has some very interesting property. It's a new kind of a semiconductor that looks like an ordinary semiconductor in the bulk. See, for example, if I just want to draw an analogy, so don't take this as very serious analogy, but it's an analogy. I take a wooden block which is insulating. Now I cover that with a copper foil. Copper is conducting. So this entire block is such a way that the bulk is insulating whereas surface is conducting. But imagine that now that's two different materials. Now topological insulators are a class of material where within the same material the bulk of the material is insulating or semiconducting, whereas the surface is conducting through surface states. So this is a topological insulator. Now see why I am interested in topological insulator is, it has got a very interesting property that the bulk is insulating whereas the surface or the side surface are conducting. So if you look at this 2D surface, it is conducting and the penetration depth is few nanometers. That means from the surface to few nanometers, it should be like a metallic behavior, whereas if you go deep inside, it is like an insulator. Now not only this, it has got a very peculiar band structure. This is the bulk bands, and then there is a surface bands, surface states. And if you look at the surface state, you see I have put an up arrow here. This talks about the spin polarization. So that means electrons in this band is spin polarized in one direction, whereas the electrons in the other band is spin polarized in the opposite direction. What does it mean? That means if an electron is moving in this direction, this electron will continue to move in that direction without scattering. If it has to back scatter, because of the band structure, it has to change its spin direction. So if an electron moving in this direction will continue to move in that direction without back scattering, if at all it has to back scatter, it has to change its spin direction. How can you change the spin direction? You need a magnetic impurity, because somebody has to absorb the spin angular momentum. So in the absence of a magnetic impurity, the surface state of a topological insulator will be a perfect conductor, because it cannot have back scattering. Similarly, an electron in the downspin direction moving in this direction cannot go back in the opposite direction because it has to flip its thing. So that is the importance of this topological insulator. See, it's an exotic property. But unfortunately, if you make this compound, so the first predicted compound was bismuth selenide, you see that the Fermi level, this is angle resolved photoemission spectroscopy, the Fermi level is into the bulk band. What does it mean? Initially I said that, look, the surface should be conducting, bulk should be insulating, because of this self-doping, the bulk is also conducting. So you cannot distinguish between bulk and surface because everything is conducting. So you have to make compounds where you have to bring the Fermi level into the band gap. That means the Fermi level should be lying somewhere here, so that if the Fermi level gets here, it becomes conducting because it's heavy N doping. If the Fermi level comes here, it's heavy P doping. So in that sense, you have to make a compound where the Fermi level is in the band gap, bulk band gap. So this is the first proposed compound, which is bismuth selenide. It's a layered structure. It's a van der Waals force connected multiple layers. So it's called a quintuple layer, and with the 1 nanometer thickness. So you can do the exfoliation like what you do on graphene. And then what we did was, so the first compounds which you made, bismuth selenide, is a self N-doped material. But if you look at the literature, you see bismuth selenide, Bi2Ac3, is a self N-doped material, whereas antimony telluride, Sb2Te3, which is a self P-doped material. Now if you take a solution of these two, Bi2Ac3 and Sb2Te3, then you expect that the solid solution should compensate for the self-doping, and it should be like a topological insulator, and precisely that's what we are observing. So we have made single crystals of bismuth antimony tellurium selenide. So the composition is BiSb Te 1.25 selenium 1.75, and this is a single crystal grown by Bridgman, modified Bridgman technique. Each of this crystal takes around 15 days to grow. And after 15 days of growth, after all the characterization, sometime you find that this is not the proper composition. We started with, we wanted Te1Ac2, but finally the composition that we optimized is Te 1.25, Ac 1.75. Probably the student has grown nearly 15 different crystals finally to arrive at this. Each crystal takes 15 days itself to growth, and then maybe another 1 month for all the characterization. After 1.5 months, you realize this crystal is not useful. Like that, you make crystals after crystals after crystals, and finally he got this thing where when you look at the angle resolved photoemission, you see that the Fermi level is in the bulk band gap. So this is the X-ray diffraction, 003, 006 is all 0L planes. So X-ray says that it's a single crystal. We also do Lavie diffraction to find out. And MSc students must be doing X-ray diffraction here. Please understand, this X-ray diffraction is going to take you for your lifetime, that technique. So then what we do, we make devices. We take this crystal, we exfoliate them, and then make devices, and we do electron beam lithography and then make devices. So what we do, we make a field effect transistor like configuration where you have silicon dioxide substrate on which you exfoliate a BSTS, which is bismuth antimony tellurium selenide layer, and on top of that you exfoliate another layer of hexagonal boron nitride, HBN, and on top of that you give electrical contact with the gold. So there is a source, drain, and gate. So you can have a top gate, you can have a back gate. So this is a field effect transistor that you do. And then what do you do? I mean, how do you make it? It's like this. You take a glass and a PDM stamp, and then you exfoliate HBN on top of that with a scotch tape, and then you take silicon dioxide substrate where again with the scotch tape you put BSTS, and then under a microscope you bring them together and then look from the top and then align it and then drop it and then heat it, release the structure so that you have this kind of a structure. So this is done, everything is done in a glove box where there is no oxygen or moisture, and then there is a microscope, and then this transfer stage, everything homemade transfer stage. So we don't make, buy things, we just make things, and with this we make those devices. Once you make those devices, you see different. See, one device is not sufficient for any experimental data. You need multiple devices and show the repeatability and reproducibility. But each time when you make a device, it has got a different shape because you are doing exfoliation. So but You know the exact distance between the probes so that you can extract the property. I'm not interested in resistance, I'm interested in resistivity. That's a material property. So in that sense, shape doesn't matter. So once you have these devices, we do wiring and then put it into a cryostat, and you can cool down. See, in our case, we can cool down to 20 millikelvin. So it's a dilution fridge or normal liquid helium cryostat. And then comes the next technique. Again, this is one technique that is going to take you for your lifelong experiments, which is 4-probe resistivity measurement, which you do in MSc lab, right? So when you do MSc experiments, you think that, oh, this is to write a report. No, please understand that this is for your lifelong bread and butter, 4-probe resistivity. So we do by either DC 4-probe resistivity, like you apply electrical current and look at the voltage drop in between, or we do AC electrical resistivity where we apply an AC current and then using a lock-in amplifier you pick up the signal. So that's what I just wanted to tell you, any experiment we do in our MSc, if you are going to be a serious researcher in future, I can tell you this, all these experiments are designed such a way that this is going to be useful for your lifelong research. So now let us take one such device and look at the resistance versus applied, the temperature. You see that the resistance at a high temperature is here, and as I decrease the temperature, resistance goes up, right? We all studied for a semiconductor. If you decrease the temperature, resistance goes up, right? And if you start from here, if I start increasing the temperature, you see that the resistance keep on increasing. So this is like a metal, right? So imagine I told you in the beginning, the bulk is insulating, surface is conducting. So what happens at high temperatures? The bulk is dominating, so the resistance keep on increasing. And at some point of time, the conductivity of the surface starts dominating. Then the bulk resistance will go up like that, diverge. Whereas at this point of time, the surface conduction starts dominating, so the resistance coming down. So this gives you the first indication that it is a bulk insulating, surface conducting material. But this is not the proof, because any material can have a metal insulator transition. So people will say, oh, this is a metal insulator transition, it is not bulk insulating, surface conducting. So then what we do, we apply gate. So when you start applying a gate voltage and you see that from +4 voltage, and you come and it reaches a peak and then starts coming down. So what's happening here, by applying a gate voltage, you are moving your Fermi level up and down. So once, if you are in the heavy N-doped region or a heavy P-doped region, and if you start applying the voltage, it comes up, and it gets into the band gap, and when it's in the band gap, the density of states is minimum. When the density of states is minimum, the resistivity is maximum, so it reaches a maximum. Then again, if you start increasing the voltage, then what happens? It goes away from the center. Again, the density of states starts increasing, and so it's almost like a transition you are seeing. So how do we know that? So you take another device, you apply the gate voltage. You apply for a constant gate voltage, you vary the applied magnetic field. Again, Hall effect measurement is what we do in the lab here, right? So that distinguishes between P-type and N-type conductors. You see here, at a certain set of voltage, it is a N-type conductor, and for certain type of voltage, it's a P-type conductor. So this also tells you, if I give you a little bit more dramatic data, you see that as a function of gate voltage, it goes to a maximum and comes down. And this is the kind of region which is an N-type region. You can calculate the carrier concentration as well as the mobility. And again, in the P-type region, you have the carrier concentration and mobility. So what is happening here? You have a Fermi level in the bulk band gap. The bulk is here, and you are moving this Fermi level up and down. When the Fermi level reaches this point, which is called the Dirac point in a topological insulator, the density of states is minimum, and the conductivity is minimum, and the resistivity is maximum. So now, from the temperature dependence of resistance, gate voltage dependence, and the Hall effect measurements, I can now say that this is a topological insulator. Of course, we had the acid test, which is angle resolved photoemission. So now we have a material which is a real topological insulator, which is bulk insulating and the surface conducting. Now with this we do a lot of different experiments. So we now know the trick that you can make this material N-type of P-type by doing the gating. So then we started asking ourselves the question, can we make a p-n junction? So we have the silicon dioxide substrate, we have the topological insulator, we have hexagonal boron nitride and the gold contact. Now by applying the appropriate voltage, you can make regions N-type or P-type. So this will tell me that we have been successful in doing this. This is all published work. You take this configuration and you apply a voltage here. In this particular region, you make this is N-type, this is P-type, this is P-type. So you can make a single material by applying the gate voltage PNP, PPP, NNN, NPN, the way you want. So if you do a silicon wafer, you have to do doping, right? And once a silicon wafer is N-doped, it is N-doped for its lifetime. Similarly, if it is P-doped, it is P-doped for the lifetime. Now, here it's a material, depending upon the voltage you apply, you can make it P-type or N-type. So this is a beautiful demonstration. We are further developing this. So then the aim of this lecture to show you some more exotic results which we are getting in the recent past. So we also grow single crystals of superconductor, right? So now I have a topological insulator. Now I'm going to grow a superconductor. So which is niobium selenide. Again we do by chemical vapor transport. We wanted to make NBSE2, and finally what we get is NBSE 2.06 plus minus 09. With the EPMA you can find out the composition with accuracy of second decimal. So many a times we start with something, end with slightly different composition, but we can find out. So this is the superconductor NBSE2. So again it is a 2D superconductor in the sense that you can exfoliate. It's a 2D structure. You can exfoliate and you can make devices. Look at this very thin device of few atomic layers of NBSE2. And then if you look at the superconductivity, it is having a superconducting transition around 7 Kelvin. And we also get some very interesting properties with this material alone. Now my job is, with this recent advances in quantum technology, all of us are looking for topological superconductivity. So what is topological superconductivity? Preserve its topological properties, at the same time make it a superconductor. So this is very important. So it was predicted in 2008 that if you convert this topological insulator to a superconductor, then it can have very exciting properties. See, day before yesterday there was a Nature paper. You must have all read about the Microsoft Nature paper on quantum computing. So topological quantum computing. So there they have taken a semiconductor and made it superconducting with the proximity. So here what we are trying to do, we are trying to make superconductivity in a topological insulator. So that is our line of thinking. And this prediction in 2008 says that a topological superconductor can host Majorana zero modes at the ends, which can undergo, okay, we don't have to worry about this thing. This is needed for fault tolerant quantum computing. So the holy grail is to get Majorana, and the prediction in 2008 says that first recipe is to get topological superconductivity. So that's why for the last several years we are working in this area. So if you want to look at topological superconductivity, there are different ways you can get it. One is proximity effect. That means you take one material and bring another material close to each other, having two different properties, and you can induce the property of one material to the other material. So the idea is, I take a topological insulator and I bring a superconductor, and the superconductor will induce superconductivity into the topological insulator. Similarly, if you take platinum is a non-ferromagnetic material, right? The magnetic moment is extremely low. But if I bring platinum in contact with cobalt, the platinum gets magnetized. The few layers of platinum is, with sufficient magnetization it comes. So if I take cobalt as a single layer, the magnetization should be 1400 EMU per cc, but if I put few layers of platinum on top of it, the total magnetic moment goes to 2500 EMU per cc, because the remaining 1100 cc is coming from, EMU is coming from platinum. So similarly, today world, standalone material, see, we had elements and then we started making compounds, and now the interfaces. So one layer have a property, another layer has a property, the interface has a totally different property. If you know, lanthanum aluminum oxide and strontium titanate, two insulating materials, when you bring them in contact, the interface becomes superconducting. So two insulator. So that means there's a lot of physics that is there at the interface. So this proximity effects with the superconductor, or you can do doping, chemical doping. Or what you can do, recently we published a paper on pressure induced superconductivity. You can apply pressure and make it superconducting. But my preferred choice is proximity effect, because pressure can sometimes change the lattice constant and it can break certain symmetry. So doping also may introduce defects and dislocation. So my preferred choice is proximity induced coupling, because that does not suffer from the shortcomings and may provide much better control. So with this, we made our first observation of topological superconductivity using this bismuth antimony tellurium selenide in combination with the niobium selenide, and we showed superconductivity some time back. But what we wanted was something called a P-wave superconductivity. The superconductivity itself, we can have S-wave superconductivity, P-wave superconductivity, D-wave superconductivity, depending upon its wave function. So the prediction of 2008 says that if you induce superconductivity in a topological insulator, you must get P-wave superconductivity. But this experiment did not give us P-wave superconductivity, but it gave us induced superconductivity. Then we started searching for alternates to get P-wave superconductivity. So there we moved to another topological insulator, which is called a dual topological insulator, which is BITE. And in combination with the niobium selenide, we make this compound, this thing. So this is the image. So this is NBSE2 layer, and this is BITE layer. And then we started looking at superconductivity in this kind of a structure, induced structure at the junction. So we do something called differential conductance measurement as a function of applied bias current in this experiment is done at 100 millikelvin. This started showing, imagine that this is not the first experimental result. We were trying with the different samples and hundreds of, combinations were tried, and I'm only presenting the final outcome. So it's an effort of 2 PhD students for nearly 5 years. The next few slides, I'm showing you 2 PhD students' effort for 5 years. So the first experiments will not give you anything. If you're very happy, lucky, you will get something, right? But you'll have to get the result. You have to work hard. So you got this thing. So that gave us, once we started getting this data, we were very, very thrilled, because it has got a very characteristic V-shaped curve like this. Usually this kind of a V-shaped curve is coming for a non-S-wave superconductor. So we thought that, okay, there are first indications that we have P-wave here. And then we have some kinks, etc., etc. So then what we do, we start analyzing. So we have a very beautiful model, which was 2D Blonter-Tingham-Clapwhite model, BTK model it is called. And that was for a one-dimensional conductor, isotropic. And then it was expanded further in 1996 to give a 2D conduction thing. So we have beautiful equations and everything. So theory has been developed. So then we did some simulations and look at how the P-wave superconductivity varies, and we started getting the one which we are getting. So the modeling is also coming fine. Then we started analyzing the data with this understanding with the 2D model. So first we tried with a single band. Okay, there's a problem. Yeah, doesn't matter. So we tried to fit with a single band, and we see when we try to fit with a single band, look at the fitting. Fitting is no way matching the experimental data. Then we looked with the P wave. Again, data is better but not matching well. So then we moved with, okay, I think there is some projection issues. Okay, we looked at with the multi-band BTK fitting, where we tried to fit with the 2 S bands, and the data fitting is not great. Then we tried to fit with 1 P and S wave. Then you see the red data is exactly matching the experimental data, including a small kink here, right? So now this shows that we are able to induce P wave superconductivity for the first time in a topological insulator like this. And if you really look at the data, so this is the black curve is the experimental data, and the red curve is the fitted data. Now we decouple this into P and S component. You see that it is a combination of an S wave. It's a dual gap superconductivity, where one component is a P wave superconductivity, which is sought after for last 20 plus years, and an S wave superconductivity. So this gives us a lot of confidence now with this particular work. And then once you get this, then it's becoming, you know, routine work that you vary the magnetic field, you vary the temperature, and extract all the parameters out of it. So these samples, once they get into a dilution refrigerator, it takes approximately 2 months to come out. So it's 2 months of experiment for one sample inside. And if you put, you know, 10 samples inside, few samples will blow in the machine itself. So if you make 10 different samples and put it inside, maybe 3 samples will give the data at the end of the day. And each of this data takes 2 months to come out. You have to vary the magnetic field in different axes, temperature in different axes. Since you are working at millikelvin temperature, stabilization is an important aspect. See how much patience a PhD student needs to get this kind of experiments. So then what we look at, we look at 100 millikelvin, the experimental data, then as a function of applied magnetic field, you see that we can look at the evolution of the superconducting gap as a function of magnetic field. You see that, you know, this is just coming up to this field and then abruptly vanishing. If it was a conventional BCS superconductor, this gap would have gone very nicely like a BCS theory data. This is not. So that's why this is known as unconventional superconductivity, P wave, and lot of experiment, because there are not many candidates for P wave superconductivity. Now we got a gold mine to explore further. And also we look at as a function of temperature, and you see how the superconducting gap varies. So none of them are matching the conventional BCS theory. So this unconventional superconductivity, that's what I qualified in the beginning. Quantum materials show unconventional superconductivity. This is an example of an unconventional superconductivity. Now also we apply the magnetic field in different directions, because, you know, if it is anisotropic, if it is isotropic like S wave superconductor, then in whichever direction you apply the magnetic field, properties should be same, whereas for an unconventional P wave, it has direction dependence as well. So it's a rich field now. Now I look at another compound, which is again BIT is a dual topological insulator, BISC is also a dual topological insulator. So we have discovered this BISC as a weak topological insulator in 2017, it's our first work. Then we made again exactly the same kind of a stack, BISC, which is a dual topological insulator, MBSC is a superconductor, and I will skip these things. And again here also, if you look at the differential conductance as a function of applied bias current, you see that, you know, a dual gap feature here. So again we analyze the dual gap feature. So this is the raw data, and we did the S plus P kind of a fitting. You see how well it is fitting, right? And then you can decompose it. This is a P wave component, this is an S wave component. So now as a function of temperature, this vanishes. Now this gives us a lot of confidence. For each device like BIT, NBSE2 combination, we have multiple devices that shows us P wave superconductivity. Now there is another compound which is BISC, not BIT, that is also showing the P wave superconductivity. Now this is a established fact that we can get P wave superconductivity by proximity in a topological insulator, and we are all excited with this particular result. Now again we do all temperature dependence, field dependence, etc. I mean, I just wanted to convey you the overall picture. You know, you see that once you get some result, then you are wedded to that. You know, then you do all sort of measurements. Students get immediately, you know, charged much more. I mean, it's like a 24 hours measurement. You know, so students are staying in the lab. One person will go to the hostel, the other person is in the lab. So they take turns because the machine is running 24/7. 2 months with one experiment. In between, if there is a problem, then that sample has to be discarded, new sample. So after 1.5 months, if the experiment failed, means entire 2 months data goes out and new sample has to come in. So this is the kind of patience is needed. So then we started looking at, you know, why we are getting this kind of very interesting property. So we started looking at scanning, tunneling, microscopy and spectroscopy. So this department has a history. The first scanning, tunneling microscope, atomic force microscope in the country was home built in this department. First in the country, right? In 1980s, late 1980s, this was built in Switzerland and they got the Nobel Prize. And in India, within few years, this machine was made here in this department. So, but now we can buy, you know, sophisticated equipments. So we take this BIT, then we do, this is the atomic image of a BIT surface. We do the exfoliation in situ. Inside the STM machine, we do exfoliation. We can cool down to, you know, 10 Kelvin. All these experiments which I am showing you is at 10 Kelvin, scanning, tunneling, microscopy and spectroscopy experiments. You see this is the surface atomic image of this crystal. And you know, this crystal is a very interesting crystal. If you start exfoliating, this has got different steps it can get exfoliated. If it gets exfoliated with a step height of 0.4 nanometer, this has got a bismuth bilayer. If it gets exfoliated with 1 nanometer, it has got only Bi2AC3 layer. If it gets exfoliated with 1.5 nanometer, that step contains one bismuth bilayer and a Bi2AC3 layer, Bi2T3 layer. 2 nanometer, 2 Bi2T3 layer. 1.5 nanometer, again this thing, and 2.4 nanometer. So I can find out from the step height whether this step contains bismuth bilayer or not. Now what we do, I mean, we can see all kind of steps which is possible in situ. Then what we do scanning, tunneling, spectroscopy. When you do scanning, tunneling, spectroscopy, you see that you see kind of a shape here. So this is the topological insulating property. So at the terrace, if you look at the scanning, tunneling, spectroscopy, you get a Dirac node. Whereas, you know, when you look at it, there are multiple steps inside. When you come very close to the step, you see the nature of the spectra changes. That means near the step, the electronic property or the electronic structure of this material is different than what is there in the, see, it is almost like these steps. This is a terrace and a step, a terrace and a step, terrace and a step. We will have different heights of the step depending upon how it is getting exfoliated. That's only difference. Now what we try to do the scanning, tunneling, spectroscopy exactly on top of a step. And then you see that you start getting an additional conductance if it is at the step. Now if I move away from the step, that additional conduction is vanishing. If I move to another point, again that is vanishing. So the next point, again it's vanishing. So this tells me that when I am on the step edge, I have an additional conductance. Whereas if I move away from the step edge, when I am at a step edge, there is an additional conductance. But if I am away from the step, there is no conductance. That additional conductance is not there. This is very interesting property. So then what we looked at it, we moved along the step. So we moved along the step from A to B, and you see that when you move along the step, that feature is there everywhere on the step. So wherever, I mean, if you are moving along the step like this, that feature is there. If I am doing it here, that feature is not there. If I am doing it there, that feature is not there. Whereas exactly when I am on top of the step, this feature is there, and this feature is there in the entire length of the step. Very interesting. Now what we look at it, we had a fortune, you know, when you do experiments, if you are very serious, you will be very lucky. You will get, you know, good results. So that intention should be there to do the good experiments, results will come. That intention is more important. I generally say if I do an experiment, no results are coming, again try once more, no results are coming, again try once more. Finally you are fed up, oh my result is not coming. You think, okay, let me do once more. That's not coming, okay, it's time to wind up and go. No, let me try once more. And 99% cases, that once more will give you your result. So don't give up. So we were very fortunate when you do exfoliation, we got within one exfoliation itself 3 different types of steps. So this step is a 1.4 nanometer step. 1.4 nanometer step has a bismuth bilayer. When you do this step, it is a 0.4 nanometer, I mean this is a 1 nanometer step, does not have a bismuth bilayer. But if I do this, this is a 0.4 nanometer step which has a bismuth bilayer. So now I have 3 steps here, out of which 2 steps have bismuth bilayer and 1 step is not having bismuth bilayer. The step which is not having bismuth bilayer is this step. Now if I do a conductance mapping, you know, in scanning tunneling spectroscopy you can do a 2-dimensional conductance mapping, you see that the conductance is very high along this line. What is this line? This line is a step that contains bismuth bilayer. Whereas this step is the step that does not contain bismuth bilayer. Look at an additional result here. That means wherever I do this scanning, whenever I have a bismuth bilayer, I have enhanced conductance. So this is coming from the 1-dimensional. So I've got 1-dimensional conductance channel now. Now for me it's becoming more exciting. Look, 1-dimensional conduction channel, and if I can induce topological superconductivity, this should be the host for the Majoranas. This is the next step we are trying. So look at here, and these steps, you know, in a different sample, it is running into microns. So long distance, but the trick is you need to have a one bismuth bilayer there, and this structure gives you that. So then we thought, okay, what about BISC? Because BIT is getting this thing. What about BISC? Again, we went to do in situ exfoliation, BISC crystal, and you know, if you look at all the properties, you know, interatomic separation, everything you can do, I mean, X-ray, and this gives identical result. You know, one is the so if you take a STM image, take the FFT, it's a reciprocal image, so that's what you get from the other one. So similarly here also, when we try to do the exfoliation, we started getting 3 types of steps again. So 1 nanometer step, 1.4 nanometer step, and 0.4 nanometer step. So 0.4 and 1.4 gives you bismuth bilayer. 1 nanometer, no bismuth bilayer. And again, we can do at the terrace, you get Dirac cone. At the terrace, you get Dirac cone. So topological crystalline insulating behavior. And the step, you get enhanced conductance. And this is the edge stage, which is a weak topological insulator. So now it's called a dual topological insulator because it has got a topological crystalline insulator phase and a weak topological insulating phase. So it's a dual topological, that's why it's called a DTI, dual topological insulator. And again, when you go to the step edge, you start getting this feature. And if you move away from the step edge, this is a 0.4 nanometer step, you get this feature. Now if you move away from the if you move away from the structure, that vanishes. If you go to the other side of the step, it vanishes. This is what I was telling. If I go there, that feature is not there. If I come here, this feature is not there. If I come here, if it is a bismuth bilayer containing step, it has a feature. If it does not have a bismuth bilayer, no feature. It's a very exciting thing that is coming out. So this is the feature. Now we looked at the 3 junctions, and you see that whenever there is a bismuth bilayer, this has got this additional feature. So now this is an exciting time for us because it's a very interesting results that we are getting. So we did the conductance mapping, look, half a micron length. So it's a long channel. So wherever this step goes, now we are trying to track these steps. So with this, let me just conclude. So what I was trying to tell you, that it's a very exciting period for all of us working in the area of condensed matter physics, material science, physics, etc. So the quantum materials, see, India has started 4 verticals in National Quantum Mission. Quantum computing is one vertical, quantum communication is another vertical, quantum sensing is one vertical, and quantum materials is a vertical. So which I was talking about today is about quantum materials. So I was trying to give you some idea of what is a quantum material. So everything that is small is not quantum. So quantum material should have its own peculiar properties. These kind of exciting new physics that is coming out of it, and we were very successful to get P-wave superconductivity in a topological insulator, and we are now getting clues why we are getting that P-wave superconductivity, and we are actively pursuing this area. With this, let me thank all of you for your attention. This is my research group in physics department. So it's very nice. In the one of the spring we took this picture, and some students were asking me whether there's a possibility to do projects at IISc. Answer is yes, if it is a slightly long-term project, because any of these experiments takes time. So because it's not that easy. Crystal growth, as I told you, takes 15 days. I mean, unless you have 6 months to 1 year, you will not get a proper crystal. I mean, if you're so lucky in the first crystal, it works. But the Murphy's law always says that, you know, the last crystal will give you the right property, or you stop with the last crystal, whatever it is. Yeah. Thank you.
Okay, thank you. It's wonderful talk. I was about to ask what kind of crystal growth technique is used.
There are 2 types here. One is the Bridgman. For the topological insulator, we use Bridgman. For the niobium selenide, we did chemical vapor transport with iodine medium.
Okay,
See, we do single crystals, thin films, we do PLD. So many of these topological insulators, we have done PLD as well. So we do MBE, we do PLD, we do sputtering, we do single crystal growth. So the good thing about the students in the lab is they do everything. So it's not that one person does crystal growth, the other person does the. These students, they have grown their crystal, they have done the exfoliation, they have done the e-beam lithography, they have done even the wiring. And these 2 students even done the wiring for the dilution fridge when it came. They do the measurements, they do the analysis. So they write their own MATLAB codes to analyze the data. So it's an end-to-end.
Okay, thank you very much. Okay, please.
Yes.
Bulk is say insulator and the surface is conductor, then that defines the topological insulator?
Not always. So you need linear dispersion. So all this qualifying, see the word topology coming from mathematics.
Yeah, that's what I
have just borrowed. I mean, it's nothing more than that. Yeah, it's because there's a band inversion that's happening because of the high spin orbit interaction and that linear dispersion. All these things together will define the topological character.
So the surface geometry matters or not?
No, not important, because sometimes there are topological insulators, only the edge is having topological property. So if you take a weak topological insulator, it has got double Diracons at the edges. So it depends. Yeah.
Achha, so it's not mathematical.
It's not that mathematical thing. Yes.
Achha. So, but that will reflect in K space, right?
Yes. So that means, you know, the general example, people talk about the donut to the cup, that kind of an analogy, you know, that can be same, but a sphere is different. So that way. Yes, question.
As per your schematic, the bismuth layer is always sandwiched between the multiple layers.
Yeah, actually the structure itself is getting stabilized. Bi to Ac3, bismuth bilayer, Bi to Ac3. That is the structure for this thing. And yeah, when you grow also, it comes into that kind of a structure.
Do you expect that same behavior?
See, yeah, it is ideally speaking, yes, it should be the same behavior, but many times crystal, I mean the thin film growth needs much more optimization to control the composition. Yes. See, imagine it's like doping. Yeah, because once you have a proper single crystal, then anytime you exfoliate, you get the same data. Whereas the film growth needs little bit more. See, with the PLD, we have shown something called the new phase, which is granular topological insulator. See, we believe that MB is needed to get a good topological insulating property. We have a paper which published some time back where we have granular topological insulator. Still, it shows all the topological insulating property. It's granular. Yes.
Any question from student?
Very nice talk, sir. So I wanted to just ask, does there any specific heat capacity measurement for this?
Specific?
Heat capacity.
Let me tell you, it is very tough to do it here. The thing is that it is a few nanometers of a superconductor with a few nanometers of a topological insulator, and the junction is a few micron. You cannot isolate the property, and everything is sitting on a substrate. So if I measure a heat capacity here, I will be measuring the heat capacity of the substrate rather than these films. So what we are trying to do now is, see, we cannot go below 10 Kelvin in our scanning tunneling spectroscopy. So we are trying to see whether we can do a collaboration where this can be measured at millikelvin in a scanning tunneling spectroscopy, and then see whether we can get the superconducting property. That's one thing. Second thing, I mean, again, you have to fabricate this and put it in a vacuum suitcase because you can't expose it, and then transfer to a machine where they have millikelvin, dock it to that and do it. Second thing which we are now we are in discussion is to find out whether we can do micro ARPAS. So near the junction, angle resolved photoemission spectroscopy. That will be further proof for these experiments.
Another thing is that you know from somewhere when you say the electron has to come and then someone should be there to.
Yeah. As a cartoon, yes.
Yeah. So, but that was something. You also some band gap and other kind of thing. So I was just thinking about the Pauli parabionism, but that is in case of metals. So that is something.
No, this is totally different. This is totally I'm talking about electrical conduction.
Any questions from the student?
Yeah.
Topological insulator, maybe not a textbook.
I mean, see, this is what I tell students, sometimes a speaker will say, oh, fantastic question.
Yeah.
There's nothing like a fantastic question, a good question or a bad question. A question is a question where you didn't understand something, I want to know what it is, that's a question. There is nothing like a fantastic question, good question, bad question. Every question is a question. Sometimes people hesitate to ask question thinking, oh, others will think I didn't know about it. No, it's not like that. Nobody knows everything. So whatever doubt you have, you should ask. Be it in the class, be it in a lecture, without any inhibition, hesitation. Don't even think what others will think about you, no. So students should ask the questions. Yes, madam.
Other than topological insulators, are there other materials that can be explored in the same direction?
Oh yeah, see, a whole plethora of materials. This is an exciting period for us. See, I do a lot of work on this pyrochloriridates, wild semimetals, right? So wild semimetals, topological insulators. I mean, the platter is full. We are unable to take everything.
So I was recently reading about alter magnetism.
Alter magnetism is a new one
is
coming up.
Is it also going to be contributing in the same way?
It should be contributing. I'll tell you why. Everything should be contributing. The reason is, if you look at the Nobel lecture of Louis Neal, when he was giving, so he got his Nobel Prize for magnetism, etc. So that time, antiferromagnetism. So he said that, look, there is a material which is an antiferromagnet, though it won't be useful for anything. He said, no, it won't be useful. But today, the antiferromagnetic spintronics is the most hot topic, and people are sought after because this material is sought after because there is no stray field. It can have all, since sublattice magnetism is there, it can have all its magnetic property. There is no stray field. This is going to be one of the most useful material in the magnetism community, the antiferromagnetism, which was thought as a useless material. I mean, it's not his fault. I mean, what I'm telling is that he said at that time it was not useful. Similarly, today you think that something is not useful. I will not believe. You don't know when it is going to become useful.
So last question.
Yeah.
Do you have the facility of measuring anomalous Hall effect?
Let me tell you, anomalous Hall effect, we should not get scared, because yesterday I was talking to some students. If you have a Hall effect measurement setup, you have anomalous Hall effect measurement setup. It's exactly same. Hall effect, you apply a magnetic field, pass current through a line, measure the voltage perpendicular to both, you get the Hall effect. In 1879, when Hall effect was discovered, they found that when you apply a magnetic field, Hall voltage keeps increasing. 2 years later, they measured it in nickel and found that no, even at zero field there is a Hall effect. So then that time people didn't understand how to explain. That's why it's called anomalous Hall effect. If that was discovered first, that could have been the Hall effect, and the other Hall effect could have been anomalous. Yeah? So anomalous Hall effect is something, what you need is a magnetic field, you need a current source, you need a voltmeter. And if the Hall voltage is too low, then you need higher magnetic field, thinner samples, because Hall effect goes with the thickness of the sample, right? If you, one recipe to get higher Hall signal is make the sample thinner, higher current without heating the sample, because you can keep on increasing the current, then I squared R, joule heating will come in. So it should not alter. So the current, you can keep increasing the current until the joule heating becomes dominant, keep increasing the magnetic field, keep decreasing the thickness, and the Hall effect will be prominent. And if you have that setup, anomalous Hall effect is only a terminology.
Thank you so much.
Yes, thank you.
Yes, Anil Kumar, and he has shown the path that sometimes from this bench, and you can showed it to just like topological insulator, which is not a textbook, let us say. Okay, thank you very much, Dr. Anil Kumar.
Thank you, sir, for that insightful and engaging keynote address. Your perspectives certainly broadened our understanding and sparked meaningful discussions. We truly appreciate you sharing your knowledge with us today. And as a token of gratitude, I request our session chair, Professor Banpurkar, to present you with a memento. Thank you, sir, for your valuable time and your contributions.
I'm from the physics department of IISc. IISc physics department is started by Sir C.V. Raman. And he is the first Indian director of physics from science.
I would now request Mrs. Swati Rahane to felicitate the session chair. Now, as we move forward with our sessions, I would like to invite Professor N.B. Chaure on stage to introduce our next speaker. Please join me in welcoming him.
So it's a PDF. No, no. Okay, no need to. Which one do you want? I have PDF. डायरेक्ट नाही करायचं मायक्रोसॉफ्टला वापरायचं. It will move like this.
Okay, so good morning to everyone. Today I'm quite happy and privileged to introduce today's invited speaker, Professor Virej Datta. He did his PhD from IIT Delhi in 1978 under the guidance of Professor K.L. Chopra, who is one of the pioneers of thin film solar cell. Professor Datta joined the Center for Energy Studies IIT Delhi as a faculty in 1980 and became a professor in 2002. He established the photovoltaic laboratory in the Center for Energy Studies IIT Delhi. He has published over 200 research articles in highly reputed specialized journals and guided numerous research theses on photovoltaics. His research interest in the areas of thin film photovoltaics, thin film science and technology, solar photovoltaics, semiconductor nanoparticles and embedded systems. He has established microcomputer controlled experiments in thin film laboratory, Department of Physics, IIT Delhi. He has extensively worked on thin film technology, as I said, in CZTS, CIGS, then CDT, dye-sensitized solar cells, organic solar cells, photovoltaic instrumentations, and building integrated photovoltaics. His current research interest in the areas of nanocrystalline material for photoelectrochemical solar cells and organic solar cells and photovoltaic instrumentations. So please join with me in welcoming today's esteemed speaker, Professor Virej Datta. Sir, over to you, please.
Thank you. On in? Okay. Thank you, Dr. Chaure. It's indeed my pleasure. I should mention that I had this opportunity to be here in this conference 2015, and thanks to Professor Chaure, I'm revisiting the university, and obviously coming after Professor Kumar's lecture, it probably is a transition to a different domain, but I hope people will accept what I'm going to talk about because as you are aware, energy is an important topic, and I try to give you a flavor of what is happening. One thing I should mention is that I probably would not do justice to the entire area of energy because it's a vast area by itself, too many dimensions to it. So to that extent, I would probably, as I will mention, restrict myself to a limited area. Those of you, if you have seen the reference on the IIT Kanpur publication, they probably have given you better coverage in the sense of covering different forms of energy. And my talk would be restricted to what I'll say the electrical energy. And for a good reason, because as you would see that electrical energy is one of the contributing factors for the environmental degradation that we are seeing, and that's why the energy transition is being motivated for. Given the fact that we are talking about quantum science and has been elaborated by the previous lecture, I have tried to dig in some information on how quantum science would be giving you equally important and different energy system. And the part C is actually the slides I've taken from Professor Kumrala to give you a flavor of solar photovoltaics in India, but given the time frame, if I may not cover, or I'll run through if the time permits. First thing I thought I'll talk about transition, because all of you are physics student, and you are aware of so many transitions that we are talking about. Something was referred to. And one of the things which is from your textbook, which all of you have studied, is the transition of water changing from solids, liquid to gaseous phase. And what from energy point of view is any transition, and that probably can be an axiom of sort, that any transition that you are incurring would involve energy. And in this case, you can of course go in increasing and decreasing temperature, and you would probably be able to create whichever state that you desire it to be, involving the energy. And of course, what you also would recognize is the fact that we also have, for energy systems, requirement for steam as the working fluid. So all the thermal engines that you talk about, would you create energy out of it, electrical energy out of it, because you can drive the system to turbine using the steam, and I've given you some numbers, but one of the things which you are recognizing is the fact that higher the temperature, higher is the, which one is? Higher is the temperature, higher is the, higher is the temperature, higher is the efficiency from your thermodynamics knowledge, and that's why we are talking about ultra supercritical technologies, pushing the temperature to almost 700 degrees or so. Associated with all these phenomena, since the primary fluid that is driving these turbines or creating the spin through boiler is probably coal or gas for that matter, and what you find that you would have essentially a lot of carbon dioxide coming out of the fuel that is being burnt, combusted, and I have left it for you to try and estimate how much of the carbon dioxide will be emitted if you want to create a gigawatt of electricity generation, just to appreciate that the context that we're talking about energy transition requires this kind of understanding. The same is true for gasoline, for travel. There again, you can estimate how much carbon dioxide is being emitted, and other things of course, but carbon dioxide is more. I've also tried for you to think about, and you might be aware, what happens if you want to melt ice in a microwave. Then the other transition that you people must have learned about is the switching losses. Here we are talking about switch, electronic, microelectronic, or whatever way you want to go from on state to off state. But in most of the cases, be it a current transition or voltage transition, since the transition is not instantaneous, you would have a positive power V into I being dissipated, and that's what constitutes a loss. And if you go by, and I think some of the slides have an indicated number, for even a digital computer with a nanowatt of generation because of switching, if you multiply it, enormous amount probably can be consumed in the switching process. And obviously, all of you are aware of the heating, etc., that happens because of the large number of switches that are present in a microprocessor or any device built in a computer. That's why I've left it for you to try and understand what zero voltage or zero current switching is, whereby you can probably reduce these losses and make more efficient. So ultimately, we also are looking to efficiency of devices when you're trying to use electricity for whatever purpose you want to. The other context of this switching is when you talk about photovoltaic, for example, which is a DC generator, you want to create an AC out of it. The simplest way is to take a DC, chop it in a square wave through, again, a chopper circuit, and get a square wave, filter it. But obviously, from your Fourier analysis, you know it probably will give you efficiency of close to 60%. Associated losses or tail losses in the inverter will also come into picture. So you would essentially not be able to convert the DC very successfully. And that's why I have left it to figure out what can be done. And these are the technologies which are being used in all the PV inverters. So also we use devices like silicon carbide again, because that allows you to have very efficient switching at higher voltages and all the associated advantage. So that's another transition we have to understand. This I have added more, not as a transition in the sense of phase or otherwise. This I thought can be introduced because we are talking about a hydrogen economy. The whole energy system could lead to, again, could is the word because a lot of uncertainties are there, a lot of questions are there, but there is a trend for you to try and create what is known as green hydrogen, and all of you must have read about a lot of reports in the newspaper about in India's national hydrogen mission. Again, with the energy transaction in concept, we will understand why hydrogen becomes equally important for the transition in making for energy systems. I thought I'll also refer to another transition which is more complex because this is talking about social systems or countries. So there is political, economic, but I'm not really interested in those aspects, but just to indicate to the fact that one of the things which again requires transition for different countries, because ultimate aim for most of the countries, most of the people is to have high income because of the living standard, quality of life, all those factors will indicate, and we probably are approaching it, but there are a lot of issues, and that's what is going to impacted by the energy availability, and that's what the context I'm talking about. And here, one of the ways in which the UN reports talk about is HDI, and what I think you might have known about it, that the numbers are pretty low, 134 out of 193 countries, which indicates that the fact of the matter is that there are places, if you have heard Raghuram Rajan's statement, that you would have places in the country which are as good as what is the amenities available as the first world, but this number tells you that there are places where the things are not as good as they ought to be, and that's one of the effort which all countries are trying to make, is to improve the HDI for the people of the countries in particular, and obviously globally. Why it is context of energy is important, some of you might be aware that there is a correlation which has been studied, that energy consumption and human development index is having a very strong correlation. India, the average consumption is probably half of what is the world's average consumption with a high HDI. So one of the things which we want to probably try and create a make energy transition, that the energy consumption, energy availability is available for the people to go from this number to somewhere here. Obviously, one has to worry about these countries because we would see that higher energy consumption has associated issues, and we'll talk about that later. So as I said, that what we have seen is that there are energy transitions in the aspects that I thought would be correlated with the fact that each transition requires energy, and obviously as the complexity of the system goes, energy requirement is going to change. And as I've already said, that we would be looking at electrical energy in particular, coming from my expertise or research in photovoltaics. Obviously my understanding of electrical energy is slightly better, but without trying to say that there are not other energy transitions that are required to be done. So to that extent, I would just suggest that this is why I'm trying to talk about energy systems, particularly in context of electricity. Now, one of the things which I thought we could go back to our basic understanding of thermodynamics for energy system is this thing which was suggested by King Herbert. However, whatever he predicted was not true, or not coming out to be true. But the fact of the matter is there is something which we have to try and understand is the thermodynamic efficiency of producing energy. So today we probably have consumed most of the oil and coal or fossil fuel which are available close to the surface. You may have to try and develop technologies to create these resources. We won't persist with using these resources, but the energy cost, because of thermodynamics involved, may not be required, may not be justified. However, I should also mention that given the fact that the energy companies, particularly fossil companies, are so well entrenched economically, probably they will always create systems requirement to keep doing it, whatever be the ecological consequences. So those are the kind of dangers that we need to be aware of, but obviously the economic cloud may not be able to change the thermodynamics of the things. So what is important to remember, as I was trying to say, that there would be obviously efforts to try and persist with the existing technologies, but we probably have to keep this factor in mind that at one point you would be able to see that you cannot really draw the the energy required for. This is a textbook picture. All of you must have seen it. All I wanted to point out is that apart from the fact that whatever energy efficiency was for the generator, you also have to worry about the fact that there's T&D losses from the point of generation to point of consumption, which could be hundreds of or kilometers or thousands of kilometers for that matter. So each component have to be improved, and that's one of the contention that energy system technologies are trying to create, that the transmission of power over large distances are done with minimal loss of energy. And obviously one of the things which you might be aware that it may be interesting for you to create your generator close to the load, the distributed generation as we call it, so that you really avoid those losses. So the Surya Graha and attempts of that type probably would allow you to create that you consume your power and also sell it. So that's why the concept of prosumer is coming in, where you're producing the energy, also consuming it, but the cost of the system is being offset by the government support. Now this is just to say that there would be a lot of energy systems, and accordingly your requirement you will be using in a different form, and you can convert it, as you know, directly to solar cell by photovoltaic generator, the chemical energy directly to electricity by fuel cell, and other energy systems would always be what we call the indirect generation, and that would obviously, because of the thermodynamics, the Carnot efficiency limitation would set what kind of efficiency numbers would be there. In photovoltaics, the limitation is what we call for a two-level system, the Shockley-Queisser limit, but obviously people have looked into a way of obviating that limit by giving it tandem devices. The gallium arsenide 3 tandem, 4 tandem, they are talking about 50%. Again, there also the thermodynamic limitation, probably you would not be able to get it kind of assumed Carnot engine of 90% or so because of the temperature difference, but there are a lot of thermodynamic limitations. So typical limit could be in the 70%. Most of the devices we limit in photovoltaics, particularly for silicon device, for example, would be close to 30%. But as I said, in all these cases, alongside the fact that it is conversion efficiency, we will also talk about externalities in terms of thermopollution and the greenhouse gases. Now, energy transitions have been taking place, so this is just a cartoon to show that initially we probably were using more of wood, coal, then as other energy resources became available, the transition has been taking place, and now we have a mix of all these technology. But the future might be more complex, and that's where I think a lot of quantum technologies will play a role, as I'll try to give you in some slide. But the current energy system probably would have lots of different energy sources which have different characteristics, different generation characteristics. Ultimately, you won't have electricity, but once you convert in electricity, rest of the paraphernalia will be same, but the energy mix may be more complex, and that would require the system designing to take into consideration these things. So that's another thing which we need to keep in mind. Now this is again a cartoon to show, just to indicate how the primary source of energy can be created in different forms, and you have electricity as a thing. This is from a BE publication, not my design. You have conventional, non-conventional, renewable, non-renewable, and we probably would like to focus in these energies, and the energy transition per se would have to incorporate these systems in more and more. This I thought was very interesting to read in one of the things, that if you have a reserve, the numbers quoted were few years, and I thought if it was that small, the publication is about 5 to 10 years old, probably we would have a crisis situation. But as it happens, these numbers can be here and there. Each time some number is generated, you have, for example, a recent report that USA has shell gas for 200 years. Obviously, extracting it, thermodynamic efficiency is not so very important because they think they would be able to extract all that is available. But again, there are considerations one has to keep in mind, the availability. Here in this cartoon, what we are trying to see is that the energy system requirements now are adding features like carbon storage, hydrogen generation. These are the sectors which we are all aware of. And one of the sectors which was most kind of difficult to meet the decarbonization was transport sector. But obviously, the improvements in the battery technologies has resulted in this also being part of the carbonization or decarbonization scheme of our energy system. This I thought would be useful to try and see how the energy density is going to play a role, because the amount of diesel you require for the same amount of energy, you probably will require much more of the other fuel. So that again is a consideration that you have to keep in mind, the kind of fuel that you use. And here hydrogen, as I said, is part of the consideration for deep decarbonization, and creating hydrogen liquid or compressed form itself requires energy. So there is an embodied energy in, so that has to be taken care of and subtracted from what is available in the hydrogen form. Right, so this kind of gives a kind of flavor of what we look at energy system, their requirement. But then I thought I would look into this paper by Smalley. All of you may be aware of Smalley's work, Smalley Institute in Houston. And here he talked about a future global energy prosperity, a terawatt challenge in 2005. So I've tried to and give it a context at what he thought the prescience part and what changes have happened with the improved technology or understanding which has taken place since. One of the things convenient for us and for the energy transition, we believe energy is the number one issues. Obviously, one can debate on it, but for us, for today's discussion, energy and environment are the key issues, and that's why we are looking at the ways to do energy transition. And this is the kind of number he gave, about 900 million barrels of oil. What you see is the consumption of energy in Quad is numbers given here. I have left it for you to try and correlate what a barrel of energy or million tons of coal or any other number, exajoule and Quad. So that is for you to convert what these numbers mean. But what it is telling you is that important thing is that you need to find what he called a new oil, and that's what we think the renewable energy is going to play the role, so that we are able to maintain all the requirements, all the growth in requirement as well through these routes. What is important to recognize is that there is externalities involved in terms of the carbon dioxide and associated temperature rise. All of you have talked about 1.5 degrees and 2 degrees. I'll be giving you some graphs to show that. So that is where the utilization of larger amount of fossil fuel and its correlation with the temperature rise is what is leading to energy transition. This I thought I'll just show you for the fact that there's a lot of interaction with the solar energy, the way it comes from outside into the atmosphere to the earth, and how you can understand, and there are a lot of probably studies going on to understand how the energy changes within the atmosphere is affecting the surface temperature. So coming back to Smalley's, and I've just quoted from his paper, one of the things which at that time he was recognizing, and as I said, we think the peak is imminent, but somewhere the companies will always find out new sources, new fields, and create that peak is shifted. So that is something which you have to worry about. But what is important is that as HDI showed and its correlation with the energy users, that there are people in the country, including our country, that we have lack of excess of energy. So energy excess is also important for trying to improve the HDI for that matter. Now, as numbers show that you're talking about 14.5 terawatt, which again still a large portion of coming from oil and gas. We at that point of time is 0.5%. So Professor Chaure and I probably belong to that generation where we never thought PV would be what it would be, and it happened because of various reasons. So 0.5%, and now we are almost projecting to 50%, which is a huge, huge transition, and which has come in because of the contributions of scientists working in this area. So ultimately, why I'm saying this number, cents per kilowatt or penny plus kilowatt, was never the number that we looked at. Dollar per watt was what was looked at for PV. But now the numbers have really come down, and that's why there are all these possibilities that the improvement in the technologies is allowing you to create what is current technology. Economic numbers are here and there, but say 3 trillion per year, probably we would have similar thing coming into being because of the renewable energy technology, growth in renewable technology, and not the other technologies. Conservation efficiency is another thing which is of importance, and I just thought, I just saw a diffusion pump in the window outside. Most of you who have done vacuum system would know Edwards. So I just thought, just for information, that if you look at a fab, obviously India is getting into semiconductor manufacturing in a big way. Here the numbers can be about 1,000 megawatt per hour, and its quality of power has to be extremely good, perfect sine wave, no harmonics, perfect frequency, perfect voltage. So it's not going to be it's not going to be the power that we get with all its dirty electrical characteristics, but it can be as high as that one. What Edwards has shown, and that's what I just quoting, that if you change the pump, you are going to save that much energy per year, and numbers wise it can show millions. So that's what is the conservation and efficiency efforts are telling you, that each part of the system, if you improve, there would be economic implication, and obviously we keep talking about the CO2 emission. So associated with any economic, we also have to put into context the emission characteristics or saving because of these numbers. This was interesting for me to read, that Smalley at that time was talking about hydrogen not being of any of use. So I thought I would put it in the context, in the current state of technology, hydrogens, and as I said, different forms of hydrogen, you can create for all these applications. For creating synthetic fuel, ammonia is also one of the important part of the storage, for example. And you also see the hydrogen application in various fields. Toyota Myrna was run in Delhi recently. You also must have heard about the RDSO developing a hydrogen engine, one of the largest in the world. And again, the railway trials will be happening. ABB is already running. There are a lot of countries are hydrogen trained. So what I'm trying to say is that what was thought in 2005 is not coming, coming out to untrue because of the developments, and hydrogen could become so very important as we talk about. Sequestration, again, I don't think I'll be talking about much, but again, if you stay with carbon technologies, you also have to make sure that all that carbon that is coming out is stored somewhere. This again is a thing which all solar scientists will probably tell you, that why to worry about fusion the ITER program and Chinese producing a sun thousands or more brightness, you have a sun giving you all that power that you need. But obviously, from scientific perspective, it just cannot be denied that people have to look for. The only problem, obviously, is whether it will be used for energy generation or any other use. That is a question which probably we cannot address as energy scientists, but believe in the fact that yes, the energy available from sun could be more than adequate for what we are doing. Now, this is a diagram that he has shown, that you can create the solar systems and meet the energy demand of the world. In fact, there was a kind of idea that you can create a kind of global energy system using photovoltaic and other renewable sources, so that if the places that does not have sun in the night, for example, that energy can be transported from the sunny side, and you have all possibility. And I think there was a mention about that kind of a grid conceptualization we'll be talking about. But what I thought was this probably illustrates this better. Obviously, this GEPC that I have quoted in this diagram is from almost a decade, so this number might have changed. But the fact of the matter is that we can identify that there are renewable resources without the externalities associated with other generators, which can meet the requirement which is represented here several times over. So the energy transition has to seriously look into these, and it's looking into these technologies more and more. How much time does it do I have enough? I will run out of time, but anyway, I'll probably stop at this. Yeah? 10 minutes? Okay, I think I'll probably just cover one part. I would not be able to do the quantum. Anyway, let's live with this. Now, this is a curve which we are very happy to show. If you remember, 2010 was the first energy mission was announced. India started making its presence, and now there is sufficient growth and requirement and the push from government to try and meet. I like to draw your attention to this book by Wolfgang Pals. In fact, Pals and Scheer were the people who drove the German program, and if you can see, Germany has been constantly, in fact, the Eigen went, they have been able to create a program, and I think only after China took over manufacturing. In fact, 2005, the Barcelona EU conference, I and others really saw the presence of Chinese company for entire supply chain of the silicon photovoltaics. So Germany was the pioneer in promoting the solar technologies, and China obviously took advantage of Martin Green's training, and a lot of people got into it, and now they are top 10 companies are Chinese. In fact, in 2005, Webull was the only Indian company we saw in Barcelona. Obviously, now we have other companies which are making inroads. So importance of these companies is there in promoting the PV technology, but it is required. One of the things which always we talk about is the fact that earlier there was a factor of 4 or 5 between the coal electricity prices and solar electricity prices, and somewhere we started, depending on the location of VCs, we started to have the grid parity, and now probably the inversion is happening. The coal prices are going up, and the photovoltaic prices, or RES, I would probably should be better put it, is going down. This is something which, again, you may be familiar with, the fact that you have the embodied energy in the solar cell in trying to make and manufacturing. The numbers are again varied. The modern solar cells will give you about a year and a half. If you talk to First Solar, the cat telluride probably is 3 months or 6 months. So important is that much energy has to be recovered first, and then rest of the 30 years or so, the energy is essentially free because input energy is free. So that's one of the selling point. Obviously, those who have loaned this for PV would probably dispute this straight line. There are LID, PID, LETID, a lot of factors which reduce the loss, but fact of the matter is that there is energy generation, and energy system will provide you almost free electricity. This is another interesting thought. I thought I'll take it from what Smalley was talking about, microwave energy. So a lot of times, this is Philip Glaser who first proposed it, and people obviously didn't take it up strongly, but who knows, this technology of trying to generate up in space, create microwave, because obviously if you put it up space, you're not affected by atmosphere, you're not affected by dust. You know AQI in the northern part of the country, you lose a large amount of power because of the dust. The report from NICE said almost 50% power can be lost because of dust, and you have to use water to clean it. So again, there is a correlation that, so this could make sense, but again, the technology is still not there. I don't think there's a Japanese company who talked about it, but we have not seen anything happening. The other thing he talked about was the local energy storage. All of us probably used an inverter. Now with the power quality being such, we don't use it. We also have pump storage. At that time, as I said, that battery technology was not of as much importance, but today the lithium-ion battery is what is ruling the roost, and we have grid-level electricity storage. And in fact, I've quoted this number from location in Rajnathgaon in Chhattisgarh, where they're trying to store almost 120 megawatt of electricity in battery. So again, as the technology improves, becomes available, you do have the possibility of storing, which in Smalley's context was not available. Here, the pump storage is again, all the companies who run dam probably are enthusiastic about it because they have the basic understanding of how to operate the water-based system. And here is a 1440 megawatt of storage in Neemuch. So again, there are a lot of reports you'll be able to see in the literature where PSP is going to be one of the important technologies for storage. So one of the things which we have to keep in mind is what he called unreliable and episodic energy, because there are a lot of fluctuations, intermittency, which will happen because the cloud may come, the wind may stop working. And I thought this was a very instructive report where the German electric system in 2005, 15 solar eclipse lost 17 gigawatt of power, but because they were prepared for such an event, they could restore the power, so the consumer were not affected. But there is a term they call Dunkelflaute, where you would have the loss of energy because of wind generator. And this has been raised as one of the concerns, that as more and more penetration of solar and wind energy takes place, you would have more event of Dunkelflaute, and in one of the reports it said that it probably will cause so much loss of energy, and the consumers will not be able. So this again was an example that if you are able to understand the requirements, you probably will be able to create systems. And that's, since I will not be able to go into those slides probably given the time constraint, one of the things where quantum computing could play a role is anticipating this kind of a changes given the large modeling that we have for the atmospheric and solar wind conditions, and try to create energy systems, the robustness in the energy system, so that they can withstand this kind of thing. So that is one of the contexts I thought I would mention. Probably I will not be able to go. I think in quick time, I just say about energy transition. One of the things which we know is that the whole effort in the terrestrial application of energy systems started in '73 with the first oil crisis. We had IPCC come into being because that's the report you all know about, because that's where they're raising the flag about the temperature rise, etc. We know about Kyoto Protocol, Paris Agreement. That's what is dictating today's energy transition. Rest I have taken from a paper on modeling, so those who are doing energy system modeling might like to read about that. I think this again is what is known as Kuznets curve, where they have correlated with the essentially HDI, and we probably are somewhere here. We have to reach on the other side so that the environmental impact of our energy transition does not affect the environment. In fact, one of the things which always is a bit of contention, whether you talk about energy emission as a country or per capita, and that's been one of the things which always gets into. What we are looking at is making a transition to energy system which will reduce greenhouse gases by 43%, so that you are in the range of 1.5 degrees. So again, there is a correlation which has been studied, that CO2 emission, which again comes from the energy, and India is somewhere here. So again, we need to worry about the fact that we need to reduce emission, but also increase the HDI. Energy triangle is again one way of describing. I don't think I need to get into that, but ultimate energy system should be such that this balance is maintained, so that you have the aspect of energy sustainability, economic growth, energy access and security is keep in mind. I think my stop would be better, right? One last I thought I would be able to show, come on. Yeah, this is a paper which I thought was very interesting in the point of view where they've analyzed carbon capture or AC versus the all wind, water, solar. And this paper essentially says that probably we should not promote CCs, SDAC versus very contentious as I am concerned. We need to really look into it, because the people who burn carbon, because coal is the main source of electricity, almost 60%, probably would not agree with this kind of information. But I just thought it would be interesting to show. Thank you.
Okay, thank you very much, sir, for giving a very nice, scenario about the energy. The requirement of energy, and further, basically the consumption of energy and the carbon dioxide evolution as well, emission of the carbon dioxide. So that needs to be considered, because energy demand is increasing. That is all we know. So this information is also very, very important for us, to move forward. So now, this particular session is open for the discussion. So I would like audience, to please do raise some questions.
Hello, sir. Thanks for great insight. My question, it may not be a question related to the data that you have presented, but just out of maybe projection that we are looking for. We have already installation of 100 gigawatt in India by solar photovoltaics, and aggressive plans for say 500 gigawatts by 2030 and so on.
Yeah.
Given the intermittent nature of solar PV, there is inherent need of energy storage. And what kind of grid scale energy storage do you look forward to?
As I said, I think I probably can go back to, what Eminari report is saying, that you have to put everything in place, right? So what I talked about was battery energy storage, which is grid level energy storage, which obviously is finding a solution. Pump storage is another solution. So as you can see, it's not one unique solution. What you're probably trying to say, so we cannot recommend one solution. Pump storage, water availability is important. So you need to have either river, a pond, and a hill to lift it up. So you have to identify, and that's one of the things where, if you see the paper for quantum computing point of view for energy, that's what they are trying and analyze, how to optimize through quantum rules, the siting of the PV, wind, storage, all put together. So what I'm trying to say is that these energy systems are now more complex. we need to find solution for diurnal variation, seasonal variation, all, and as I said, solar eclipse can be another extreme example of losing power. All the solutions have been found through some way of energy modeling and optimization, and the suggestion which I did not cover was quantum computing could be one way in which you can really look into the whole perspective of what complexity energy systems are going to face. So all the tools that are available for technological point of view would now have to be analyzed through the quantum means if you have those tools and create. So this is what is the roadmap for India. So the numbers are there, availability of technology is there, the economics have to be looked into, the energetics have to be looked into, and found a complete comprehensive solution to meet all the requirements that we talked about. So I mean, I would not say that you should use battery storage, but in some cases battery storage is more expensive for pump storage. So the solution would be found maybe pump storage. So I mean, what it's probably is what we are trying to envisage hydrogen, the energy system in which pump storage will be there, flywheel may be there. You can talk about E2G, for example, sorry, G2V, V2G. So you can have all your electric cars store energy when the energy is available, and when the requirement is there, car gives it back. So vehicle to grid. So there are a lot of complexities which today's energy system has formulated, conceptually there, but commercial viability would have to be looked into, and that's where I'm just pointing out the complexity of energy generation and solutions to meet the requirement of the whole global. I mean, India of course is part of the system, but globally, how can we solve the problem? And if you look at what, I mean, I didn't show, there were one conference in India Energy Week in Delhi, and there was 25 knots in Goa. There they showed all kind of numbers where India has contributed to the energy systems in different ways, and particularly renewable energy. And now we have a role, leadership role to play, because we can be example for other countries who need energy. So energy poverty in those countries can be removed by the methodologies which India is saying. There's another conference, Electro-Rama in Noida, which again has a whole lot of activity. So point I'm making is that there are concerns what we are raising, that how to solve the problem. We now have for individual tools. We need to create more and more systems, demonstration to convince people, and obviously the companies will follow it.
Thank you, sir.
Hello, sir. Here. In one of the last slides, some bold letter words caught my attention. How would you send microwave energy up to satellites?
No.
I might have read it wrong.
This is, as I said, Philip Glaser had proposed, and earlier people thought it's a wacky idea, but as Professor Kumar was pointing out, a lot of times ideas are projected at one point that do not make sense, but tomorrow they make sense. The point was that if you put my solar panels up in sky, above the atmosphere, I get almost 24/7 throughout the year sun. All the satellites are obviously using those kind of. And now I create microwave and project it in this part of the country. So the transportation is, so that's why they call it energy to energy. So convert those energy of megawatt, beam it down, and utilize it back to electrical energy and use it. So it's a concept which has been proposed, and I understood some Japanese company wanted to try with the idea, but I have not seen any demonstration. But the advantage that I was trying to point out is, up in this sky, energy is available throughout. It's working at a perfect condition. On Earth, in Indian condition, up north, Rajasthan, the sun may be very high, but so is dust, so is atmospheric dust, a lot of scattering. So in fact, we did some experiment when we compared data for tracking, the 2-axis tracking in Jodhpur gave us lesser result than Delhi, and of course we did a Leh. Leh was 50% more. So the point is that we can generate, say, 50% more energy, even if you lose some in the exchange to microwave. Probably it will make some sense. But today it has not made sense. Till the technology improves to create this kind of transition, maybe somebody will put a satellite up there. So it's creating microwave up there and rebeaming it down. That's a process that we talk about. So energy to energy, that's what Smalley called it.
Okay, so any more question? Okay, anyway, if you have further more questions, you can discuss with sir during the lunch time as well, and even the dinner as well. I mean during the dinner time as well. So he will be around us with us today for whole day. So please, join with me. Let's thanks Professor Viraj Datta for giving such, good and very nice talk, today's talk. So thank you very much, sir. Thank you.
As a small token of our gratitude, we would like to present sir with a memento. Thank you, sir, for being with us today. I request Mr. Akash to facilitate the session chair. I hope everyone enjoyed the talks by our esteemed guests. Moving further, we have a series of oral presentations and thesis presentations. So some of the oral presentations will be held in the Bhide Hall and Raman Hall simultaneously. And due to time constraints, the thesis presentation will be held in the seminar hall. Members of the audience who are interested in attending the talks held in Bhide Hall or the thesis presentations, please head outside. And I request the volunteers to guide the audience. Participants whose oral presentations are scheduled to happen in the Raman Hall, please be present with your presentation. Come near the stage. Ms. Samina Mulani, Ms. Monica Javale, and Ms. Tanushri Sukul.
उस पर लगा दो ना कॉल हो गया ना
बोल के दिखाओ
हेलो नहीं आ रहा ना थोड़ा ऊपर करो हेलो
Hello. So, good afternoon to all. So now, welcome for this particular oral session. Okay. So there is instructions for oral presentee. You have to strict with your time.
Yes.
So 8 minutes is your presentation and 2 minutes for discussion from the audience. Okay. So now I request Dr. Samina Mulani to start her oral presentation for this particular conference.
Good afternoon everyone. Am I audible to all? So good afternoon all of you. I am Dr. Samina Mulani. Today I am presenting on the perovskite MnFeO3 nanoparticles for bifunctional application. So in my bifunctional application, photocatalytic dye remediation and desalination, these are the topics which I am going to focus. So these are the content of my presentation. So as we know that most of the water is present in the ocean form and a very less amount of water is in accessible format and which get polluted by the various sources of pollutant, and it has the hazardous effect on human health as well as overall ecosystem. So there are various methodologies has been proposed to degrade this dye molecule which are present in the wastewater, which include the physical, biological and chemical methods. So in my presentation I will be focusing on the photocatalytic dye degradation, which is one of the chemical method to degrade the dye pollutants. Another one is we can utilize the abundantly available water in ocean and so convert it into the purified drinking water by means of the process called desalination. It is nothing but in presence of sunlight we can desalinate the salt water into the pure drinkable format. So by keeping this in mind, we have synthesized the MnFeO3 nanoparticle for bifunctional photocatalytic dye remediation and desalination application. So we have synthesized the MnFeO3 nanoparticles by utilizing the simple co-precipitation route by using the sulfate precursor. So initially all the precursors are dissolved and mixed together to get the homogeneous solution, and then by adjusting the pH to 11, the material is synthesized by following the process of drying and annealing. Phase is analyzed by utilizing the X-ray diffraction pattern. So here it is clearly observed that it shows the uniform and it shows the crystalline nature with all the peaks are well matched with the reported literature. Then surface morphological features indicate that it has the nanoparticle like morphology with all the particles are uniformly distributed, and we have identified its average particle size is around 86 nanometer. Then EDS analysis confirmed the presence of Mn, Fe and O element without any other impurity, which indicate the pure phase formation of MnFeO3 nanoparticles. Again, XPS analysis was performed to analyze the oxidation state of the material present in the MnFeO3 nanoparticle. So Mn and Fe is present in 3+ oxidation state, whereas in case of oxygen it has two peaks, one correspond to the lattice oxygen and another one is correspond to the surface contamination. Then optical properties we have identified by utilizing the diffuse reflectance spectroscopy and identified the band gap of around 1.81 electron volt. So this material we have further utilized for the photocatalytic dye degradation. This is the actual setup which we have utilized to perform the photocatalytic dye degradation measurements. So initially we have performed the catalyst dose optimization, means the weight optimization for particular dye degradation. So here we have taken the crystal violet as our dye solution, and then by varying the dose of catalyst from 5 mg to 25 mg, we have carried out the photocatalytic dye degradation measurement, and here we observe that for 25 mg catalyst it shows the highest degradation efficiency. Then by using the Langmuir-Hinshelwood kinetics, we have checked the we have calculate the rate constant and correlation coefficient, and it shows it follows the pseudo first order kinetics. Then by using this 25 mg of MFO weight, we check the dye degradation activity for various dye, which include I have tabulated in this table.
So the material shows the highest degradation activity for crystal violet dye, and again the reaction kinetics follow pseudo first order kinetics. These are the actual images, means with increase in the reaction time, how the dye is degraded and how this violet color of dye is converted into the transparent water that we can see here. So after that, as the material shows highest degradation activity for crystal violet dye, we have checked the scavenger study to identify the which of the radicals are responsible for the photocatalytic dye degradation, and from which here we can observe that the O2 minus and H plus are the main radicals which are responsible for the dye degradation. Then we have utilized the same material repeatedly for the to check the cyclic stability, and material shows good stability up to 3 cycles of photocatalytic dye degradation. Then second part of my presentation is the same material is utilized for the desalination measurement. So this is the actual desalination measurement setup. So here the synthesized MnFeO3 nanoparticles are coated on the cellulose paper. Here cellulose paper is act as a membrane. So we have coated that powder onto the cellulose paper by utilizing the vacuum filtration technique, and the light is allowed to the material is exposed to the incident light, and we have measured the weight loss of the water which is present in this beaker, and from this initially we have checked the surface temperature on the surface of the MFO coated cellulose paper, and here we can see that with increase in the time the surface temperature increases, which indicate that the material is suitable for the desalination measurement. So this is the formula which we have used to calculate the evaporation rate, and this setup we have used to collect the water whichever is evaporate, that is called as a purified water after desalination measurements. So along with the DI water, we have checked the solar steam generation performance for various salt contaminated water ranging from 3.5 to 10 weight% NaCl solution, and here by calculating this mass loss, we have calculated the evaporation rate, and here we can observe that for DI water as well as that salt contaminated water, the material shows the evaporation rate which is around 2.5 kg per meter square hour, and here the collected water we have to check that whether the material photothermal material really desalinate the water. So for that we have checked the TDS of this collected water, and here we can observe that it shows the drastic decrement in the TDS before and after desalination. So the same material is utilized for the 5 number of cycle, and again it shows the consistent evaporation rate after 5 continuous cycles of desalination measurement. Then we perform the measurement in direct sunlight. So here we can see the change in the mass loss with respect to the intensity of sunlight. So here we can observe that irrespective of the sunlight intensity, we have observed the continuous mass loss, and for the 12 noon we have observed the highest mass loss, and from this we have calculated the evaporation rate. So this is the table of comparison. So we have compared our material with the literature in terms of evaporation rate and total time required for the evaporation. So in conclusion, the MnFeO3 nanoparticle are utilized for the dye degradation. It shows the highest degradation efficiency for CV dye, and it performed well for the ISSG measurement as well. It shows the good stability for 3 cycles of dye degradation and 5 cycles of desalination measurement. So this material can be used we can see these are the industrial and social aspects. So this is the useful material in the places where there is a crisis of clean water, or we can use it as in coastal region as well. So finally, I would like to acknowledge my thesis supervisor, Professor Rupesh Devan from IIT Indore, for his constant support and for giving me for providing the experimental facility, and to RMC committee for giving me chance to present my work. Thank you.
So now session is open for the question. Any question from the student? Okay, so I have couple of questions.
Yes, sir.
So in this MnFeO3, does there any role of oxygen vacancy?
Yes, sir. Actually, if suppose basically the photocatalytic dye degradation is basically depends on the how much the adsorbed oxygen we are getting, that we can utilize to degrade the dye.
Are present or not here?
Yes, sir. That sir, no, sir. Oxygen vacancy is not there. That defect, that adsorb oxygen is there, so that we can confirm from XPS analysis.
Okay, you have selected one element that is manganese.
Yes, sir.
And you, after XPS, you said that it is a 3+.
So actually, it is present in both oxidation state, 3+ as well as 2+ oxidation state.
Okay, and you said some nanoparticle-like morphology. So I didn't understand what is the meaning of nanoparticle kind of morphology.
Means, sir.
Because by looking morphology, you are saying nanoparticle kind of morphology. So is this the type of morphology? I don't think so.
Yes, sir. It shows the nanoparticles. So like morphology should not be used there.
And for UV visible, you have figured out some band gap. No?
Yes, sir.
So you have used some optical reflectors method. No?
Yes, sir. DRS, diffuse
But,
reflectance
the
spectrum.
figure caption you have mentioned UV visible.
Yes, sir. UV visible diffuse reflectance spectroscopy.
You have used for
Yes,
that.
sir.
So what kind of band gap you have said? It's a direct or indirect?
Direct band gap.
And what about the cost effectiveness of this material?
Cost?
Cost effectiveness.
Yes, sir. Actually, that I have not calculated. Means, sir, that. Yes.
And pH 11 is very high. Why it's so high?
Sir, actually, I tried from pH 8 to 11. So I get that means pure XRD at pH 11.
Can you increase the pH more than 11?
That's very high because you are getting XRD at pH 11 doesn't mean so optimization.
Generally at 11 you can, it gets saturated.
It's
quite difficult,
saturation.
to increase the pH. That means we have added whatever the
Ammonium hydroxide I have added. Yes, sir. Yes, sir.
It's very high. And later on you have centered at 850. So you need to think on that.
Okay,
But anyway, very nice presentation.
Thank you, sir.
Next.
I would now like to call Miss Monica Javale.
Hello.
Is it?
What is that?
Okay, presenters, please note there will be a warning bell at the completion of 8 minutes and a final bell at the.
Yeah, sure. First of all, I like to thank the organizing committee to accept my abstract for the oral presentation. I am Monica Javade, PhD Research Scholar at Department of Physics, IIT Bombay, Supervisor Professor Avinash V. Mahajan. So it is like a homecoming for me. I completed my MSc from here in 2018. So today I am going to talk about NMR and a MUSA study of the S is equal to half 1D Heisenberg antiferromagnetic chain Cu McClBr. It's a metal organic framework kind of compound. So these are the outline of my talk: general introduction and a motivation, sample preparation, bulk magnetic susceptibility, proton NMR and a MUSA study, and finally I will summarize the results. So general introduction and motivation. So in IIT Bombay we work on the experimental search for a quantum spin liquid candidate. So quantum spin liquid candidate is a state of matter where the spins are fluctuated even at the lowest temperature without breaking any symmetry. So it has very great features. I will not explain, but these quantum effects are more prominently found in the low dimensional system like 1D, 2D, and which have, with the small spin we can get the exotic ground state. So let's take the 1D Heisenberg antiferromagnetic chain system with S is equal to half is the simplest example of a spin liquid. Its ground state is a microscopic singlet entangle all the spin in the chain. So its excitations are not like a standard spin wave which we found in the order system, but it's like a phenon, and we will found the continuum in the dispersion relation. So these are the These are the examples of the 1D system, like a uniform Heisenberg antiferromagnetic chain. We have alternating Heisenberg antiferromagnetic chain, and there is another Gauss-Muzumdar-Dehn, which is the exactly solvable model. And then the spin dimer and a Halden chain. Halden chain has a S is equal to 1, and it has a gap ground state. So the motivation of preparation this CuMCClBr is like that. This is the phase diagram of the S is equal to half J1 J2 Heisenberg antiferromagnetic chain with the frustration parameter J2 versus the randomness. So he has found 4 states like unfrustrated random singlet, frustrated random singlet, gapless TLL state, and a dimer state with a finite gap. So let's say this Cu, Amphi and Br2 is a order state around 4K. So we are introducing the Cl atom in a place of Br2, and we are randomizing its exchange pathway by introducing the J2 parameter. So we have prepared a polycrystalline sample and analyzed its structure through the XRT and did the Rietveld repayment. And we found a monoclinic crystal structure which is matched with the Br2 and also the Cl2 atom. This is the crystal structure, and in the crystal structure one can see clearly it is forming the zigzag Cu2 plus ion forming the zigzag chain along the precrystallographic axis. And these chains are well separated by the Amphi, which is a benzene kind of structure, and so one could imagine it as a 1D system. And then we did the magnetic susceptibility. This is the susceptibility versus temperature down to 0.4 K, and we fitted the high temperature region with the Curie-Weiss fit and extracted the theta CW and a mu effective. So we got the negative theta CW, which is which will tell us we have a predominant antiferromagnetic interaction in this system. And also in this figure one could see that there is a hump at 10K, and this is the clear signature of this one-dimensional chain system which we have found, where we have fitted with the Johnston model, and we got the average value of antiferromagnetic interaction which is around 18K. And just in the last slide I have explained that with the Br2 analog we have 4K bifurcation, and with mixing Cr2 we are making it to the non-order state. Many times the bulk susceptibility at low temperature is dominated by the extrinsic paramagnetic impurity and also some chain break effects. So that's why to know more about the intrinsic susceptibility of Cu2 plus ion in the sample, we did the 1H NMR, and with the temperature dependent spectra, we found the broad hump at the 67.7 megahertz. And with the temperature these broadenings are increasing, but we did not found any change in the central line, because maybe this proton and a Cu2 plus atom has a weak hyperfine interaction, but we have this broadening which is sufficient to prove the spin lattice relaxation in this compound. So we did the temperature dependent phase lattice relaxation rate at various frequency, mainly at the 67.7 megahertz. We did measurement down to 88 millikelvin. Down to 1.7 K it's performed at IIT Bombay, and below measurement we performed at University of Augsburg, Germany. And in the 1/T1 we showed the remarkable decrease in the in 1/T1 at temperature 2.5 K. This is maybe appearing due to the opening of a gap in this system. So this is the first time through the local proof technique NMR we found that there is a gap opening in this excitation spectrum, which can be due to some dimer singlet state in this compound. And we fitted this fast component of 1/T1 through the exponential function, and we got the 2 gap delta 1 by kBT, kb, and delta 2 by kb, which is around 7 Kelvin, and delta 1 is around 0.72. And also we did another local probe technique, which is complementary to the NMR. But these muon are like 100% muon has a 100% polarized spin. So we will get very good data through this muon. This measurement is carried out at ISIS Neutron Muon SOR, UK. And we did measurement on the bulk sample, like a powder sample. And muons are implanted on the sample, and through the backward and forward detector, one could calculate the muon asymmetry. So in this muons asymmetry data, if we found any oscillation with time delay, with the time, then it's we have some static moment, and our sample is in order state. But we do not found any oscillation in the asymmetry, which confirm that we don't have any kind of ordering down to 88 millikelvin. Also, we fit the data with the Gaussian Kuboto, because above 2K one could clearly observe the Gaussian kind of behavior in the system, and below 1.5K it's clearly the exponential. And from the Gaussian fit, we have the delta value, which is around 0.26 megahertz, and when we convert into field, it is 3 oerstrat. And this is the muon relaxation rate. So above 2K, it's almost constant. As we decrease the temperature, it is gradually increasing, and below 1K, it's again the constant. Such kind of feature is also we seen in many of the QSL compound. And also, sorry, I forgot to mention, this is the zero field MUSR measurement. In the next, we did the longitudinal field measurement also, and above 2K, it's 2.4K, the decoupling of the muon is already happening at 40 Gauss, where in the 88 millikelvin, the decoupling of the muon are completely gone above like a 320 Gauss. So it generally says that when this decoupling is in between 5 delta to 10 delta, that there we have in the static moment. But for these above 2.7, it's 10 times delta, and for the 88 millikelvin, we are almost 100 times delta. So we are in the dynamic moment. And when we plot the, we have plotted this LF MUSR spectra to this relation. From there we got the delta 1 and delta 2, and this muon relaxation rate we plotted with respect to the field. And as you can see, these spectra, these muon relaxation rates are following the red field motion and a diffusive motion, but it is not following the ballistic. Generally, for the 1D Heisenberg antiferromagnetic change, we don't have any randomness or any disorder in the system which followed the ballistic motion, but maybe because in our system we have introduced randomness by introducing the J2, and also we have might be the chain break in the system. So that's why we are getting this diffusive and red field motion. So finally, I will summarize like that. We have prepared these antiferromagnetic compound, and with the CL-BR mixing, it's expected to generate the randomness through this nearest neighbor interaction. And the presence of gap is also confirmed through these proton NMR. NMR by the measurement of free lattice relaxation rate. Also through the MUSR, we found that there is no any ordering present, and also this chain break and randomness is preventing the ballistic motion of the spinon. And we thought that these muon sites which are away from the chain are sensing the diffusive motion of phenon, and which are the at the end chain following the red field variation. And for our data, we reveal the presence of a grab ground state, and we suggest it's a dimer singlet state. So these are the collaborators and co-authors, my professor, Professor Avinashmi Mahajan, and our postdoctoral fellow, Dr. Saikat Nandi. We did this work together, and these are other authors. And finally, I like to thank all the funding agency, and thank you for your attention.
Now the session is open for 1 or 2 questions.
Actually, I have one question. In one slide you mentioned a few measurements you have taken in IIT Bombay and few measurements you have taken in Germany.
Yeah.
So and you compared both the results.
Yeah.
So is there any instrumental errors have you considered there?
Actually, this is the idea of the NMR. NMR has no any disorder which is intrinsic. We are dealing with the nuclear level, so most probably there is some scale factor, but in our case we did not find it, ma'am.
I like your enthusiasm, the way you presented.
Thank you.
It's very good. So in this NMR spectra, you are getting the broadness by decreasing the temperature.
Yes.
So what could be the reason? Can you explain?
Yeah, I forgot to mention this broadening is because of the dipolar coupling. So if we have this magnetic coupling, like if this hyperfine interaction is very good, then we have a shift in spectra also. But if like we have not, if there is not even a broadening, so there is no point in doing this because there is no interaction. But we have some broadening, so yeah, we have some hope that we will go ahead.
Have you considered the hyperfine effect on your material?
Yeah, we don't have much. If we have, then we can have a shift in the spectra, and that shift has a static.
You are talking about the chemical shift?
Not really. This actually spectra central line is shifting with this frequency.
But as far as NMR is concerned, the chemical shift is the major
Yeah,
on y-axis?
most of the time. But in our case, we yeah.
Okay, so your work is related to the antiferromagnetic.
Yes, sir.
Okay, so there is a Curie-Weiss law.
Yeah.
Okay, what is that law? You have mentioned C
So,
divided by T.
yeah.
Something else you have written there.
Yes. So we have.
Minus you have written.
Well, yeah, this is minus theta CW. So that's the representation which I have used. If this theta CW is negative, then we have predominant
For
and
antiferromagnetic, what is the theta? It's a positive or negative?
it's a negative. Like here, it's positive.
Okay. And what about the exchange integral you have considered during your calculation?
This one?
Yeah.
So actually, sir, we have fit it with some Johnston model. Johnston is some theoretician. He write the model for the purely 1D chain system. So is it like this? And this chain, from there we have the J and all those parameter we used. Actually J by K beta.
What's
It's,
we both are trying to ask.
oh, okay, it's negative or positive.
J is positive or
Sorry,
negative
I
for antiferromagnetic.
don't remember that exactly.
That's why it is negative, but you are mentioning the only absolute value.
I think so. I need to look at this. It might be this fitting has gone.
So you did all these FC and ZFC. There is always one opening. Huh?
Yeah, for this BR2,
For most of the times.
actually in our case we don't have bifurcation. If we had bifurcation, then it is clearly some spin glass kind of behavior in your system, and which can more verified with the SE susceptibility also. Thank you, sir.
Thank you so much for your wonderful presentation. Next we have OP26, Ms. Tanushree Sukul.
Good afternoon, everyone. I am Tanushree Sukul, PhD student working under the guidance of Professor Santosh K. Haram in Department of Chemistry, Savitribai Phule, Pune University. So today I'll be discussing about our recent work on electrocatalytic reduction of carbon dioxide by using bismuth and tin based bimetallic alloy catalyst. In addition to that, we are going to this research will will be more explaining about the mechanistic aspect as well as the performance evaluation. Now to start with electrocatalytic reduction of carbon dioxide is nothing but converting carbon dioxide into valuable fuels and chemicals. In as a result of doing this, what actually we get is whatever the greenhouse gas emission is taking place into the atmosphere, we can close the carbon loop, at the same time mitigate the emission of carbon dioxide, and hence ultimately we can it is having an application in the sustainable energy development. Now when we talk about electrocatalytic reduction of carbon dioxide, it always comes with some challenges, and those challenges are like this carbon dioxide is thermodynamically inert and highly stable molecule. So for its activation, more amount of energy is required. In addition to that, carbon dioxide conversion in this process, selectivity is a very important factor, means converting carbon dioxide into selectively desired product. But in that potential range where carbon dioxide reduction takes place, various other side reaction also occurs. At the same time, one of the biggest competition for hydrogen evolution reaction, CO2 reduction reaction is the hydrogen evolution reaction, which also occurs in that potential range where CO2 reduction reaction takes place. Therefore, achieving high selectivity is another challenge in CO2, in electrocatalytic reduction of carbon dioxide. In addition to that, getting or synthesizing or preparing highly efficient catalyst for converting CO2 is itself again a biggest challenge, means getting a catalyst which is highly efficient in terms of high activity, in terms of high selectivity, like that. So therefore, our work is an attempt to synthesize bismuth tin bimetallic alloy catalyst, which is ultimately going to overcome the challenges, means it's an attempt to overcome the challenges that I have just now mentioned. Now before going to the the scheme, how the catalyst has been prepared, before that why bismuth and tin has been chosen. Bismuth and tin, these are the two elements which are a very good candidate to convert selectively carbon dioxide into formate. Although various different kind of products are there, but selectively this bismuth and tin are good candidates for converting CO2 to formate, means selectivity is high for formate. In addition to that, several other advantages are also there, like these two elements are less toxic, environment friendly, and catalytically very active. But at the same time, why we have chosen bimetallic system? Because when we talk about the monometallic, of course these two elements individually, these are good for CO2 reduction, but at the same time, unfortunately, these elements need higher over potential to achieve that high current density and high Faradic efficiency for the desired product. Therefore, to overcome that, we have done alloying in this. So alloying is one of the strategy nowadays which is done by many researchers, that alloying basically it increases the activity by changing the binding energy of the key intermediates which play an important role in the formation of the final product. Now by changing the key intermediate binding energy, basically one can tune the electronic system or electronic structure of the active sites where actually the reaction is taking place. So to start with the synthesis process, bimetallic bismuth tin alloy catalyst has been synthesized by employing electrodeposition technique, where the gold rotating disc electrode has been used as a substrate to be used as a working electrode. In addition to that, platinum flag electrode has been used as a counter electrode, which was placed exactly 2 cm away from the working electrode to ensure or to facilitate better, means to optimize the thickness of the catalyst which is been deposited on the surface of the substrate, plus to tune the morphology whatever is obtained for the catalyst. In addition to that, for the synthesis, a constant current density of 30 milliamp per centimeter square has been employed for the same. At the same time, to study the basically the influence of the catalyst, that is been means to have the or to tune the morphological features, to tune the thickness of the catalyst which has been used here. In addition to that, different electrodeposition time period has also been employed. The electrodeposition time that has been used here is from 30 seconds followed by 60 seconds, then 90 seconds and up to 120 seconds. After this is by FESEM we have checked the morphological feature of the as prepared catalyst. Now as you can see here, the first 30-second deposition duration. Now if you can see from A to D, there is a morphological change which is being seen here from 30 second to 120 second. If you will see the 30-second duration, there some feature is there, but sparse nucleus same time surface coverage is not complete. In at 60-second duration, if you will see, of course some little defined structure has started to begin, but at the same time the surface of the deposition is again something uneven. If you will go for the 90-second deposition, some distinct floral morphology, as you can see, is appeared over there. Now as we increase the time to 120 second, the deposition it got worsened. At the same time it becomes broadened, means we can say it becomes denser, at the same time got aggregated, because of which one can, it's when we started checking the performance, electrochemical performance, that started coming out. On the basis of this, we can say that the one which we got at 90 second gave the best morphology which we checked for the electrochemical performance. This XRD powder for structural identification, we have done X-ray diffraction studies. From that, the peak, characteristic peak which is obtained here, that exactly matches with the characteristic peak of the individual bismuth and tin, which confirms the successful formation of the bismuth tin bimetallic catalyst. Apart from that, to check the formation of the alloy, we have done DSC. The endothermic peak at 138 degrees Celsius confirms the formation of the alloy, which is less than that of the melting temperature of the individual bismuth and tin elements. Apart from that, for electronic structure, we have done XPS. From XPS, there is a notable shift which is observed. Basically, bismuth has shown, as you can see, the negative shift, and tin has shown the positive shift, and because of this shift we can say that the alloy formation has taken place. This is the electrochemical performance we have checked with the help of like the linear sweep voltammogram has been obtained at various at different rotation rate, and from this we have this data we have plotted at this data we have fitted into the Levitch equation, and from that we have got the KL plot. From KL plot we have got number of electron 2, which signifies that for the conversion of carbon dioxide to formate, it follows 2 electron pathway. In addition to that, we have done TEFL analysis also. TEFL analysis basically has given us that which since in this we can see that the reaction mechanism that it follows. From the reaction mechanism, the TEFL slope has given us the fact that the TEFL slope for the catalyst, bimetallic catalyst, is lowest compared to the individual metal. At the same time, 1 electron reduction of carbon dioxide to carbon dioxide radical is nothing but the rate determining step in the mechanism of the CO2 reduction to carbon formate. ECSA has been calculated, on the basis of which the bimetallic catalyst has shown highest ECSA means electrochemical active surface area compared to the controlled elements. From the Nyquist plot, we have seen that more mechanistic insight in which 2 different charge transfer processes has been taken place. The charge transfer resistance for the bimetallic catalyst is less compared to the monometal, which again confirms that this is good for CO2 reduction to selectively convert it into the formate. Apart from that, how we can say that it is selectively converting into formate by analyzing the catholyte that we get during the long term electrolysis, and from that the peak which is obtained at 8.3 ppm in the NMR spectra confirms the formation of formate as one of the major product, having Faraday efficiency of 86% and partial current density of 18 milliamp per centimeter square, which is confirming that it is superior for the conversion of carbon dioxide to formate. This is the conclusion. Thank you.
Yes. Bismuth and tin, you suggested that bismuth is in 3+ and tin is in 2+,
Yes, sir.
right?
Yes, sir.
Why don't we expect it to be in metallic state if it is bimetallic system? So the charge state should be 0.
Sir, basically, we wanted to make it an alloy. So in alloy, of course, it is in different electronic state, but due to the shift, yes, as we can see, due to the transfer of electron from this tin to the bismuth, it is achieving the same. Yes, sure, sir. Yeah. Yeah. Okay. No, no, it's an alloy, sir. Because we have checked, we have like proved it by doing DSC. Yeah, sure. Yes. Yeah. Yeah. Yes, sir. Right. Yes, sir. Yes, sir. Conclusion is that the one which we have got at 90-second deposition, because it is giving, as you can see, that the morphology that we have obtained over there, no, it is a kind of floral morphology where we can say on the basis of EC. Okay. Yeah. No, okay.
One of the significant point for that.
Okay, 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 yeah, okay. I'll check into it. Sure, sir. Yeah, yeah. Yeah. Yeah, yeah, yeah. Yes, sure. Yes, sir.
In your matrix plot, I observed both Z prime and Z double prime almost got the same value.
No, it's not same value. We have just set the same scale over there. Same scale over there.
And the second, in this XPS, have you observed any LS splitting, this LS coupling splitting?
No, we haven't checked for that. We have just seen the shift in shift is there.
There might be splitting.
Yeah, yeah. We'll have to look into it. Okay, sir.
Thank you. I would now request OP19 Sharon Alex to come.
I'll start. Good afternoon, everyone. I'm Sharon Benyalex from Department of Chemistry, SPPU, presenting before you my work on deciphering strain and ligand effects in 2D platinum at MXene RGO aerosol for oxygen reduction reaction. This work, conducted under the guidance of Professor Santosh Haram, explores an innovative catalyst design which is aimed at enhancing sustainable electrocatalysis. To understand the significance of our work, let's first look at the current scenario. With the ever-growing population, the demand for energy has grown over the years, which is duly satisfied by the non-renewable resources such as fossil fuels, coal, natural gas, etc. This has led to various environmental issues such as the growing carbon dioxide emissions as shown in the statistics. Thus, there is a need to shift to good fuels, and one promising alternative are the fuel cells, where green hydrogen and air combine to generate electricity. However, the commercialization of fuel cell is still hindered owing to the cathodic oxygen reduction reaction, which is a slow and energy intensive process compared to its counter reaction, that is the anodic hydrogen oxidation reaction. Thus, we need to address this reaction specifically to enhance the fuel cell efficiency. Coming to the theoretical part, according to Noskov plot, platinum is a state-of-the-art catalyst for oxygen reduction reaction. However, it poses several challenges. That is, platinum is a rare and noble metal which is going to be very expensive. Its active sites are prone to poisoning and its performance degrades over a period of time. Therefore, in our work, we have developed a unique electrocatalyst with lowered platinum content and enhanced ORR performance by integrating advanced two-dimensional materials, that is MXene and RGO. MXene is a two-dimensional transition metal carbide known for its high surface area, excellent electrical conductivity and tunable surface chemistry. However, its layers tends to restack over a period of time. So what we did was we introduced another 2D material, that is RGO, which is again known for its structural stability and high surface area. This RGO acts as a spacer which prevents the restacking of MXene layers and creates a porous aerogel. So utilizing gamma radiolysis, we deposited the platinum nanoparticles onto this MXene RGO aerogel heterostructure. So this is the aerogel photograph of the platinum MXene RGO aerogel. It produces enhanced active sites and creates a porous aerogel with improved ion charge transport. The SEM images, as you can see from B to E, shows 3D cross-linked framework of numerous nanosheets with the larger nanosheet of RGO wrapping the smaller nanosheet of MXene. This unique conformation prevents the restacking of MXene that is crucial for its electrochemical stability. The TM images from F to G shows that the platinum nanoparticles have a rough spheroid-like morphology with a size of around 4.9 nanometer. And it's well dispersed within the MXene RGO matrix without much apparent aggregation. Motivated by these structural features, we set out to carry out its ORR performance of the platinum MXene RGO aerogel featuring different ratios of MXene RGO, that is 1:3, 1:1, 3:1. We have kept the platinum content to be constant within a range of 7 to 9 weight percentage so that we can compare it against the state-of-the-art catalyst 10 weight percentage platinum carbon. The CV curve that was recorded in 0.1 molar HClO4 displays essential features of hydrogen adsorption, desorption, formation and reduction of platinum oxide, which are all characteristic features of a clean platinum surface. Further, we recorded the LSV curves at various rotation rates and the 1600 RPM is shown here. It is observed that the platinum MXene RGO 3:1 composition shows the highest activity towards ORR with its high onset potential and half wave potential. Further, the Teffel slope constructed from these LSV curves shows that the platinum MXene RGO 3:1 catalyst shows the lowest Teffel slope, suggesting again the enhanced ORR activity, because smaller the Teffel slope, smaller is the increase of overpotential with current density. Further, to assess the electrochemical stability, we conducted the accelerated durability test for over 10,000 cycles. It was seen that the platinum MXene RGO 3:1 catalyst showed only a drop of the 18 millivolt compared to a 32 millivolt by platinum carbon under the similar testing conditions. This again renders the fact that platinum MXene RGO catalyst is showing superior performance for ORR. Now, to understand why it showed high performance, we set out to investigate its electronic properties using XPS and XAS measurements. First, we investigated the ligand effect. Ligand effect is the effect that is arising between the electronic interactions between a support and the platinum nanoparticle, which is going to alter the platinum's electronic structure by fine-tuning its D-band structure. From the XPS, we see that there is a negative shift in the platinum 4F peaks of the platinum MXene RGO aerogel compared to PT carbon. This negative shift is attributed to the more electron density that is present on platinum due to the electron transfer from the MXene RGO support to the platinum nanoparticle. Further, to validate this, we conducted the XAS measurements at the platinum L3 edge. It was here you can see the rising edge. This is known as a white line. It is due to the electronic transitions from the 2p 3/2 orbital to the 5d orbitals, vacant 5d orbitals of platinum. This intensity, as you can see here, is particularly lower for the platinum MXene RGO aerogels, particularly for the 3:1 composition. This again reverberates the fact that there is relatively more electron density at platinum in the platinum MXene RGO aerogels due to the electron transfer from MXene RGO to the platinum nanoparticle. Thus, the ligand effect arising from the electron transfer from MXene RGO to platinum nanoparticle is one cause of the enhanced ORR activity. Further, coming to the strain effect is something that is arising from the compressive forces that is exerted on the platinum lattice, which will reduce the PT-PT bond distance and by downshifting its D-band center. As you can see here, we qualitatively and quantitatively analyze the strain effect by conducting the EXAFS data at the platinum L3 edge. You can see a peak at 2.5 angstrom, which corresponds to the PT-PT bond. Here, the PT-PT bond is downshifted towards lower direction, R direction in our catalyst compared to PT carbon and PT foil, again reverberating the fact that there was a strain effect exerted on the platinum lattice due to the MXene RGO heterostructure. This was visually confirmed by the wavelet transformed analysis. The contour plot shows that the intensity maxima has shifted to lower R and K directions in platinum MXene RGO aerogel compared to PT carbon and PT foil. Thus, Again, we can conclude that the PT, MXG and RGO aerogel structures have shown enhanced ORR activity due to the ligand and strain effect exerted on the platinum lattice by the MXG and RGO heterostructure. Thus, in conclusion, we have developed a platinum MXG and RGO heterostructure aerogel structure with lowered platinum content which showed enhanced ORR activity due to the ligand and strain effects operating in the system. These are the references. Thank you. We can. So platinum is the one that is going to reduce oxygen. Its active sites are the ones who is going to reduce oxygen to water. So main problem of platinum is that when platinum is laid out such, it's a rare and noble metal, you cannot have a large amount of platinum like that. So its dispersion in these metrics will prevent agglomeration, Oswald brightening and dissolution. Probably when you're just using platinum as such, it tends to agglomerate and it tends to dissolve into the electrolyte, causing Oswald brightening and then retain. So that for its well dispersion we have used of the platinum. The MXG RGO is avoiding the agglomeration of the platinum nanoparticles and creating a well stabilized structure so that every platinum nanoparticle has its active sites. When it tends to reaggregate or agglomerate, its active sites are being reduced. Yeah. The platinum, I didn't get you. No. We have to, according to the DA concept, they have told ki you have to lower the platinum content and at the same time increase. Yeah, activity.
So which parameter is important, which morphology is important, or maybe is it like MXL is important, RGO is important, what is it?
Platinum itself is important. Its active site should be feasible. No, the platinum reduction, it's around 10 to 8%, which is more than enough. But when you are just using it, just say like in MXene, platinum will go somewhere or here, it will not adhere properly onto the sheets. Now what we did was, it's now properly adhered on those sheets such that each platinum nanoparticle's active sites are seen for the oxygen reduction to occur. Its ECSA was also high. It's a nanoparticle. PT0 was shown by the XPS measurements as well as the XS measurements. But PT2 plus was there, but its content was very much relatively lower.
So PT0 is yours in alpha?
Yeah, 4.9.
PT2 plus you are meaning iron.
PT2 plus was the iron. But as such, TM. Maxine was, Maxine we didn't synthesize. We had procured it from Sigma Aldrich. Further, the delamination and etching we had done it. Yes, sir.
Green hydrogen, what is
green hydrogen, blue hydrogen are terms I don't really. Green hydrogen is something that is like produced through electricity. Yeah, I don't know. Sorry, I'll read it.
What kind of X-ray source you will use?
Aluminum K alpha.
Aluminum K alpha. So if I change the source, then anything is going to change over there?
No, it depends on the binding energy of the core electrons, so it will not change.
So now the oral presentation session is over.
I would now like to invite the PhD students to felicitate our session chairs. First, Nikita, I request you to present a token of our appreciation to Professor Sayed. Next, I request Mansi to kindly felicitate Professor Kamble. And with that, we now conclude the oral presentations. Everyone can go outside and enjoy their lunch, and we will resume after 1 hour. So around 2:40? Around 2:40. Everyone is requested to carry their ID for the lunch outside.
Okay.
Good afternoon. Yeah, it's 2:35. Now this talk is very interesting. Its title of the talk is to enable ferromagnetic and antiferromagnetic states in the charge transfer materials. A case study of CR, COO3 or X, I don't know, but he will deliver his talk on I think some perovskite or double perovskite compound. Basically, I will introduce Ram Jani Chaudhary. Ram Jani Chaudhary, he is basically from Bihar, Sitamarhi, because we attended his marriage in Sitamarhi. Therefore, I know. And graduated MSc from Allahabad University. I don't know now the name is Prayagraj University or Allahabad University, but he is graduated from the Allahabad University, and then he came to Pune University for PhD, and he worked in mostly 3 institutes for the PhD. One is Pune University, is pivoted point here. Then another one is Nuclear Science Center. Now it is called as a Inter-University Accelerator Center, New Delhi. And third one is Professor Venkateshan's lab in University of Maryland, College Park. He worked in 3 different labs for thin film and some some ferromagnetic materials, I will say, some ferromagnetic materials. And he graduated in 2005. Yeah, he graduated in 2005 from the Department of Physics, Pune University. Same where he delivered his open defense, and he will give you the talk here, same position. He has a very good, he is our student of the Department of Physics student. He has very good physics understanding, basic physics understanding. He is a good teacher. Another one point is, he has a very deep insight on the Madhushala. Madhushala is poems written by Harivansh Rai Bachchan, and he has very deep insight on Madhushala. Probably he will give one Madhushala finally. Yeah, and he will tell the meaning also. Yeah. And we can arrange separate program also. And yeah. And I request Ram Jane to deliver his talk. Yeah.
Thank you, Guruji. Good afternoon, everyone, and namaskar. I am Ram Jane Chaudhary. गुरुओं जी की एक आदत होती है कि अपने स्टूडेंट्स को बढ़ा चढ़ा करके कुछ बोलते हैं, तो बिल्कुल भी विश्वास मत कीजिएगा. और टाइटल लगता इनको इंटरेस्टिंग लग रहा है, लेकिन आप टाइटल पे भी मत जाना. इंटरेस्टिंग तो सिर्फ इतना है कि मैं आज यहाँ पर हूँ और आज आप सब लोग हमारे सामने हैं. And it has given me an opportunity to communicate with all of you, meet our gurus and our friends after long gap. After 8-9 years or so, I am visiting again this department, and I am feeling a bit emotional, nostalgic. So many feelings are there, but thanks to the organizers for remembering me for this occasion, and I am really glad to be here. Now coming to the topic, as I said, that title may not be interesting, so I will not go on the title at present. What is interesting at present to talk about this UGC DAE Consortium for Scientific Research. There is an institute which is created by University Grant Commission to use the mega science facilities which are created by Department of Atomic Energy, right? So our institute is located at 4 different centers in our country, And you can see that Indore is the main center, then we have Mumbai, Kolkata and Kalpakkam. And at all these 4 centers, 4 cities, you will see that Department of Atomic Energy has created mega science facilities. Like in Indore we have synchrotron source, in Mumbai we have BARC, in Kolkata we have VECC, and in Kalpakkam we have IGCAR. So for the university researchers or college researchers or any researcher across the country of different institutions who may like to use these facilities, we are the contact person, number 1. Number 2, besides these mega science facilities, at all these different centers, we also have a wide range of in-house facilities, right from sample preparation to characterization techniques, be it for a structural characterization or for magnetic measurement or for transport measurement or for heat properties related measurements, you know, spectroscopic related measurements. Wide range of facilities are there. So if any one of you who is interested to use these facilities, please visit our webpage csr.res.in, and remember there is no cost involved at all at any stage regarding uses of these facilities. What we do, we also provide you the travel support to visit this place. We provide you accommodation and the local hospitality. So what you have to worry about is your research problem. You do not have to worry about anything else. You have to contact us, you have to write to us. Of course, it may take time for us to respond depending on the queue and the, you know, the prior commitments which have been given to different users across the country. So it may take some time, but certainly it works wonderfully in this type of arrangement. Once you are done with your measurement, please believe that the data is completely yours, idea is completely yours. We do not come into picture in even your paper in terms of authorship, etc. It is completely your paper. What we need in return is the acknowledgement of the consortium, nothing else. Okay? The authorship, etc. comes into picture when the scientific interactions, deliberations, analysis and all those things, contributions in the writing part, etc. come into picture, which is a normal course of action whenever we write any manuscript, right? Otherwise, please feel free to use these facilities. Okay. So this was about the in-house facilities, and as I said that in Indore we have synchrotron source. What is synchrotron source? So just I will take a minute to briefly talk about the importance of synchrotron source. Remember, when you have a static charge, what it creates is an electric field. Okay? Now you give it a motion. A moving charge will create magnetic field, right? So you have now a moving charge giving you electric field as well as magnetic field. Now what you do, you accelerate that charge. What it will do now? It will create electromagnetic radiation, right? Now if the same charge is accelerated at the speed which is close to that of the light in the relativistic norms, then it creates synchrotron beam. This synchrotron beam or the focused electromagnetic radiation contains a wide range of, you know, electromagnetic radiation spectrum. So using this wide range of wavelengths of the light that we are having, one can plan a wide range of measurements, and accordingly you will see that at synchrotron source, which is at RRCAT Indore, there are actually 2 synchrotron sources unique in the country, Indus 1 and Indus 2. So in Indus 1 you can see that there are like high resolution vacuum UV spectroscopy, angle integrated photo emission spectroscopy, angle resolved or soft X-ray reflectivity photophysics. So wide range of techniques are there, and the energy ranges are also given here. Similarly, in Indus 2 again we have a wide range of experimental stations where one can do wide range of experiments, be it X-ray diffraction, be it X-ray absorption spectroscopy, be it for, you know, photo emission spectroscopy. So you have to plan your experiment that what you want to do at these synchrotron beam lines. Okay? And again, you can use these beam lines even by directly visiting the web page of RRCAT, and you can directly apply for the individual beam line, or you can contact to us. Again, for using this beam line, it is completely free of cost. You do not have to worry about anything. Okay. So this was about Indus 1 and Indus 2, and the red ones that you can see, this is BL2 at Indus 1, angle integrated photoemission spectroscopy, and at Indus 2 we have soft X-ray absorption spectroscopy. These are the two beamlines which are created or designed and assembled and being run by our own institute directly. So a brief introduction about this angle integrated photoemission spectroscopy. That the wavelength that we are using here is in the range of say 10 electron volt to 210 electron volt. I will give you an example that why we need this type of experiment to be, which can be carried out only using synchrotron radiation. What is so great about this? I will just come to that explanation. So this is about AIPS beamline, and this is about soft X-ray absorption spectroscopy beamline. So please remember, when I talk of this angle integrated photoemission spectroscopy, it simply works on the Einstein's photoemission equation. What is that Einstein's photoemission equation? You shine the photon, the electrons are ejected, the photoelectrons are ejected. As simple as that, right? But remember, this incident photon has certain energy. The electron which is being emitted from the material may have certain binding energy, and when it overcomes that binding energy, it comes out with certain kinetic energy after overcoming the work function, right? So your equation is actually h nu equals kinetic energy plus binding energy plus work function. So what we measure is the kinetic energy. The work function of the spectrometer comes into picture, which is generally constant. So what we get in return is the binding energy of the ejected electrons from your material, right? These ejected photoelectrons can come from any of those levels whose binding energy is lower than the incident photon energy, right? So if you are probing the core level electrons, it gives you the information about the elements from which this electron is ejecting and its charge state, right? So since you are ejecting the electron from the occupied state, the photoelectron spectroscopy gives you information about the occupied states, right? It doesn't give you information about the unoccupied state, which is beyond your Fermi level. It gives you information about the states which are below the Fermi level of your material. As simple as that. This is true about the photoelectron spectroscopy, right? Now, when I talk about the same photoelectron spectroscopy, but not the core electrons, but from the valence band electrons. Now remember, if I take a simplest example of say TiO2, if you look at the electronic configuration of titanium, it is 1s2, 2s2, 2p6, 3s2, 3p6, 3d2, 4s2. And then oxygen you have again 1s2, 2s2, 2p4. When you make this TiO2, the outermost orbit of titanium 3d and 4s hybridizes with the outermost orbit of your oxygen 2p, which is 2p4, and in that process they make a hybridized state. So the electron which are ejecting from those hybridized state, their energy states are no more characteristic of the individual titanium or oxygen, because they are in the, they have very small separation in terms of their energy values, right? So if you are probing only the ejected valence band electrons, the spectra that you get is called valence band spectroscopy. And in this valence band spectroscopy, the identity of the element is lost because their energy states are very discrete and their separation is so low that you cannot confirmly say that this ejected electron is because of say titanium 3d or 4s or oxygen 2p electron, right? So to probe that aspect, we generally do this resonant photoemission spectroscopy. I will talk about it in a minute or so, but this is overall understanding of photoemission spectroscopy. Now, when we come to the X-ray absorption spectroscopy, what we do in this process, again we vary the incident photon energy, and when we vary the incident photon energy, there may be some electrons in this say 2p electron, which binding energy will be just close to that of the gap between the valence band and the conduction band. What it will do, it will absorb that incident photon and will be excited into the conduction band, right? So in that perspective, X-ray absorption spectroscopy gives information about the unoccupied states. In a way, it gives information about the conduction band state, okay? Number one.
Number two, another advantage of this X-ray absorption spectroscopy is that if you can perform this type of measurement in two types of polarized states of the incident photon, then the absorption of that incident polarized photon by the up spin is different with respect to the down spin, and therefore the difference of the absorption spectra by say right circularly polarized photon and the left circularly polarized photon will give you information about the net spin polarization present in the individual element in the system, right? So when we do that kind of a study, we call it as X-ray magnetic circular dichroism, and it gives us information about the number of unpaired spins in a way to the total magnetization that you get from any magnetic material, mostly for these 3D based transition metal oxide systems, because this is the kind of energy that we are having at this particular beamline. Again, one can also carry out, okay, so the advantage of XMCD is that it gives you information about the elemental contribution to the overall magnetization, which unfortunately any other magnetometer, be it SQUID or VSM, will not give you, because VSM or SQUID gives you the total magnetization, the bulk magnetization, but it gives you information about the element specific, number one. Number two, there are certain sum rules. Using those sum rules, one can also estimate the spin contribution to the total magnetization as well as orbital contribution to the total magnetization. So that way it is again quite important. One can also carry out X-ray linear dichroism. What is X-ray linear dichroism? We do this against this set of experiment, not in left or right circularly polarized, but what we do, we just vary the incident photon either normal to the sample or parallel to the sample. So what it does, just imagine your 3D orbitals shape. You have dxy, yz, zx, x square minus y square and z square, right? So there are certain orbitals which are pointed along z, and there are certain orbitals which are in plane, right? So the absorption spectra of the incident polarized photon in the two directions happen to be different, and their difference actually gives you information about the electrons occupancy or the in which particular plane of orbital electrons are more populated than the other. Okay, so this information is obtained from this X-ray linear dichroism. Okay, and there are certain some rules which are generally followed. So these are the two types of experiment that we generally do using this synchrotron beam radiation. Okay, and in our group we have pulse laser deposition, and as I said, we carry out photo emission spectroscopy, which gives us information about the occupied state. Occupied state means I am talking about those states which are below the Fermi level, and we carry out this X-ray absorption spectroscopy, which gives information about the states in the conduction band beyond the Fermi level. And of course we do some magnetization measurements, then try to see the correlation between the structural, electronic and magnetic properties of most of those transition metal oxides. Now coming to the topic, of course not the title, I'll be talking about the electronic structure aspect of the correlated transition metal oxides, then the cause and the effect of a strain, and then some examples that how one can use this type of a strain to control or tune various other properties of these transition metal oxides. And then I will show you one example of photomagnetic effect and this colossal voltomagnetic effect. Now when we generally talk of transition metal oxides and we do not consider electronic correlation, then generally the band structure that we are having is that oxygen 2p is somewhere here, and near the Fermi level we have the contribution due to transition metal 3D elements. But this is when we consider that electrons are not talking to each other, they are completely unknown to each other. But actually most of these transition metal 3D, they know each other, they kind of interfere or interact with each other. So there is a on-site Coulombic repulsion energy. And when this on-site Coulombic repulsion energy comes into picture, what happens that this transition metal 3D states, they are actually splitted into two states. One goes below the Fermi level, other goes beyond the Fermi level. So the lowest charge energy fluctuation is between this dn to dn. So you have a configuration like 3dn plus 3dn. So an electron from this 3dn goes to the you know, another states of this 3D, and you have this type of configuration. So this type of interaction is called DD type fluctuation. But if this oxygen 2p is dominating and is hybridizing strongly with this transition metal 3D, then it may so happen this oxygen state will be near to the Fermi level, and in that case, when you have to excite or transfer an electron from to transition metal 3D, then electron from oxygen will go to this transition metal 3D, and that type of fluctuation is called PD type fluctuation. Why PD type? In oxygen, your outermost electronic state is 2p. And why D? Because outermost electronic state in transition metal 3D is 3D. So an electron from P goes to transition metal 3D. So that type of insulators are called as charge transfer insulators. But this charge transfer insulator, as I said, happens when you have a good covalent character in your system. When I say covalent character, that means I am talking about a strong hybridization between oxygen 2p and transition metal 3D. But if this is really very strong, then what happens? Then this oxygen thing state, this actually crosses over the Fermi level, and so much so that this crossover Fermi level again splits up, and you have these two states no more between this P to D, rather you have a lowest, just below Fermi level as the oxygen 2p character, and just beyond Fermi level also as the oxygen 2p character. And in that process, because your D contribution is negligibly smaller or much smaller as compared to oxygen 2p, so actually electron from D first goes to P, and then this electron from P goes to another P state. So you have a PP type of fluctuation, and this PP type of fluctuation is then generally regarded as negative charge transfer insulator. So the beauty of this negative charge transfer material is that it can be metallic also. So that is the advantage of this negative charge transfer material type of system. And so what is important? How much is the gap between, say, between this D to D? How much is the gap between this oxygen 2p to 3D? So if this oxygen gap from oxygen 2p to 3D is lower than transition metal 3D to 3D gap, then that material becomes charge transfer insulator. Otherwise they are called Mott-Hubbard insulator. So there is a competition between this Mott-Hubbard type character and charge transfer type character. That is, Mott-Hubbard type character is dominated by U, charge transfer type character is dominated by delta. So lower the U value, the material will be called as Mott-Hubbard insulator. Lower the delta value, it will be called as charge transfer insulator. So the competition between these two will give rise to a wide range of interesting properties. So one can also tune this delta to negative, and one can also attain a somewhat ferromagnetic state or unconventional magnetic states in the systems. And all this tunability between this delta and U not only depends on the material, but it also depends on the strain states that you can invoke in these systems. And when we talk of a strain can be induced in the system by various ways. What is a strain? A strain is nothing but a change in the variation in the lattice parameter of the original material, be it applied by some chemical doping, be it created by some epitaxial strain that you can attain in the system, or any other way that you can think of, okay? So the strain can be induced in the system by various ways. Either it can be through chemical doping. So when I talk of chemical doping, you are doping some of those elements whose ionic radii are quite different from the host metals ionic radii, and therefore it creates a local strain in the system. Then when you deposit these films on the lattice match substrates, it can create epitaxial strain. And recently we have also come across this photo-induced strain. So there are certain type of material on top of which when you shine light, it shows some strain effect, okay? And again, by using electric fields like piezoelectric type of material also, you can create a strain by applying electric field. Excuse me. So using these different parameters, one can induce a strain. Now what a strain is going to do? So when you are inducing a strain in a system, then your unit structure gets slightly modified. So if I'm just simply talking about, say, TiO2, So you have certain say rutile or NRTS structure that you can think of, and when you are changing its lattice parameter, what it will do, it will affect the hybridization of the outermost orbitals between titanium 3D and oxygen 2p. And when you are modifying that hybridization by inducing this strain, it is going to change most of your properties, because be it optical property or magnetic property or electrical property, they all are governed by the outermost hybridized states present in your system near the Fermi level states, right? So this is what we are going to say, that how they are going to affect. Okay. So as I said, that when you dope chemically different element with different ionic radii, the strain is effective up to 1 to 2 unit cell. And when you are using this epitaxial strain, this strain is retained up to certain critical thickness. Beyond that, the critical thickness, the strain is relaxed by creating some kind of dislocation in the system, and therefore this is effective up to some critical thickness. And then you can, in most of these oxide systems, there are inherent oxygen vacancies, and they can also cause local strain in the system. And yeah, intrinsic strain is throughout the film thickness, and photo strain is of course as long this depends on the penetration of the light, that up to what thickness the light is actually penetrating. Since I'll be talking mostly about the epitaxial strain in the system, just a minute to talk about this epitaxial strain. So when you are growing thin films on a lattice mass substrates, not essentially your substrate lattice parameter has to be exactly as that of your material that you are growing. There can be slightly lesser, there can be slightly larger, and accordingly when these evaporants are reaching on this substrate, the unit cell or the atoms which are arranged on your substrate, they exert a force on the evaporants to match the lattice structure of the underlying substrate. Okay, and in that process, the evaporant or the film material that you are growing, it has to slightly change its lattice parameter with respect to its original lattice parameter, and thereby it induces some kind of a strain in the system. Okay, so the strain can be your in-plane tensile strain or in-plane compressive strain, depending on whether your lattice parameter is smaller than the underlying substrate or larger than the underlying substrate. And because of that, the properties will be changing. Okay, so I will just give you a few examples of how the strain is actually affecting the various properties. One such example of say LASR MnO3 on BaTiO3. If you look at BaTiO3, BaTiO3 is a very well known good ferroelectric material, and we know that it shows various multiple structural transitions. It has cubic structure, or let me start from the lower temperature. At low temperature it is rhombohedral, then beyond 181 Kelvin to 280 Kelvin or so, it turns into orthorhombic, and between 280 Kelvin to 390 Kelvin it is tetragonal, and beyond 400 Kelvin it is cubic. Okay, so you have successive structural transitions. And LASR MnO3 is a very well known colossal magnetoresistance materials, which is known to show, you know, coexistence of ferromagnetism and metallicity, and it has a Curie temperature close to 350 degrees centigrade, and beyond 350 it turns into somewhat semiconducting like property. Okay, so what we decided, we deposited this LASR MnO3 thin film on BaTiO3 substrate. So initially when we deposit its thin film, what you can see, that the substrate that we had taken, BaTiO3, it was having twin boundaries. When I say twin boundaries, that means, of course I am saying it's single crystal, but in that sense it is not a true single crystal. It is having some kind of, you know, C domain. C domain means few regions on BaTiO3 are oriented along C, whereas few domains on BaTiO3 were oriented along A or B axis. That way it was some kind of twinning. Okay, and that was also reflected from this normal theta to theta XRD pattern. And when we deposit the film of LASR MnO3, what do we see? That okay, it grows very well along 00 C axis oriented, fair enough, but at the same time the regions where it is looking at BTO A or B domains, it is also growing along A or B domains. And then we probed its magnetization measurement with respect to temperature, by understanding that if the underlying substrate is a strain is playing a dominant role in controlling the magnetic properties, then this temperature induced a structural transition that BaTiO3 undergoes should be also affecting its magnetic property. With that idea in mind, we did this empty measurement, and what do we see? That all those temperatures where this BTO undergoes those successive structural transition from rhombohedral to orthorhombic to tetrahedral to cubic. Of course not cubic, we have not gone into that because in that region my system is already in paramagnetic state. But what do we see? That when it goes from rhombohedral to orthorhombic phases, the magnetization jumps abruptly. And when it comes again from orthorhombic to tetragonal phase, again it drops abruptly. Okay? Remember, this is not the character of LSMO as such, because LSMO character is a smooth downfall, a normal ferromagnetic second order ferromagnetic transition temperature. But here what do we see? They are showing abruptness. What does that imply? That implies that since the underlying BTO undergoes successive structural change, the change in the lattice parameter causes or inflicts a strain on the film layer which you have grown, and that way it is actually manipulating the magnetic anisotropy in the system. And that is why when we change the direction of the field, what do we see? That this jump has now gone into drop, and this drop has gone into up. Okay, so that means the film is actually magneto-structurally coupled with the underlying BaTiO3 substrate. Fair enough. But BaTiO3 has another interesting property, that it is a very good piezoelectric material. So that means when I apply certain pressure, it should induce certain voltage. Okay, there is an inverse effect, inverse piezoelectric. If I apply some kind of electric field across this BaTiO3, it should undergo a change in its lattice parameter. So with that idea in mind, we applied electric field across this BaTiO3 and tried to see what happens to the magnetic property. What do we see? That the jump which we were seeing earlier, when we apply a field of 8 kilovolt per centimeter, this jump completely vanishes. Okay, not only that, the magnetic hysteresis shape also changes. So that means using electric field also I am controlling the lattice parameter of BaTiO3, which is inflicting the magnetic properties of the LSMO film which is grown on top of it. Now continuing the same BaTiO3 argument, what we observed that when we shine light on BaTiO3, the lattice parameter of BaTiO3, particularly the C domain, undergoes a kind of a strain state, because you can see that after shining light, this 002 peak shifts towards higher to theta value. So that means there is a photo-induced compressive strain in the C dimension, in the C direction of simply BaTiO3 single crystal substrate. But remember, A or B domain is not changing at all. And because of that strain, photo strain in the system, there is a huge photopolarization as high as 40% on that single crystal BaTiO3 substrate. Now the question arises, why only C domain is responsible? Why not A or B domain is showing that change? Number one. Number two question is, remember the incident light was 532 nanometer, okay, which is the visible range light. And if you look at the band gap of BaTiO3, it is as high as 3.6 electron volt or so. So one would not expect that this visible light should be absorbed at all. Okay, but what we see, it not only absorbs but also causes the strain. The answer lies following. When you look at the AFM scan of this BaTiO3, what do we see? You have a beautiful striped structures. These stripe structures, this is A domain. These structures which are where there you can see those globule structures, they are actually C domains. So what we figured out, that the hydroscopic or the water adsorbates present in the atmosphere, they are adsorbed, they are attracted by the C domains, and they are not attracted by the A or B domains. Therefore, these C domain features on BaTiO3, they have some kind of adsorbed defect state in between the band gap states of your system. So it creates a defect state just below the valence band, and that allows this 532 nanometer to be absorbed by this BaTiO3. And because of that, only C domain shows that change in the lattice parameter. Now, when we thought that, okay, if I can control the C axis lattice parameter just by shining light, what will happen to the magnetization if I deposit some magnetic layer on BaTiO3? So with that idea, we deposited a film of nickel on BaTiO3, and then we shine light. And when we shine light, what do we see? As long as we are switching on the light, the magnetization gradually increases. When we switch off, magnetization tends to saturate. Again switch on, it increases. Remember, the catch here is this is not at the saturation magnetization. Had your film been in the saturated state, then you cannot change anything, because your nickel total moment is completely saturated. You cannot create moment. You have to understand this, right? So what we are doing these measurements at lower field, 100 oersted, whereas the coercivity in this system was somewhere close to 450 oersted or so. So since I am doing this measurement at 100 oersted, my domains are not completely aligned. So by shining light, when this C domain is changing its lattice parameter, it is causing a strain on the overgrown nickel layer, and there this magnetic anisotropy gets modified and nickel moments tend to align in the direction of EG axis, and that allows us to control the magnetization of nickel films. So the beauty of this type of experiment is that you do not have to physically make any contact on your device to change or control its property. Since we are using just light, so remotely I can control the properties of any device. So that is the advantage of this type of material. Then again, using a strain, BaBiO3 is a very well known material, and one of my friends suggested, theoretical friend, he suggested that okay, in this BaBiO3 the issue was that if you look at bismuth charge state, it should be bismuth 4+. But bismuth 4+ has electronic configuration of 6s1, which is highly unstable. Chemistry doesn't allow it to be stable. Therefore, these bismuth 4+ state has a tendency to go into 3+ or 5+ state. But in BaBiO3, there was a debate whether it is 3+, 5+, or whether it is 4+ delta, 4- delta. So this kind of incomplete charge separation, we call it a charge disproportionation in the system, or there is a huge oxygen contribution in this bismuth 3+ state. Okay, so there were these debates. So one of my friends who does theory, Dr. Rajamani, he suggested us that when bismuth 6s as well as 6p orbitals, when they hybridize with oxygen 2p, it will favor bismuth 5+, but when only bismuth 6p hybridizes with oxygen 2p, it should favor bismuth 3+. Okay. Now again, the hybridization can be controlled by a strain. With this logic in mind, we deposited its film on different substrates, BaBiO3, on strontium titanate and neodymium gallate substrates. Okay. Of course, there is a very minute difference in their lattice parameters, but sufficiently enough to cause the results that we wanted to see. So when we deposited its film on, say, strontium titanate, what do we see? This is X-ray absorption, X-ray photoemission spectra. You can see that this feature R1 is lower in intensity than feature S1 in intensity. The lower binding energy is indicating bismuth 3+. The higher binding energy is attributed to bismuth 5+. So on the STO substrate, the 3+ is lower in concentration as compared to 5+. But when it is grown on NdGaO3 substrate, what do we see? That R1 now dominates over feature S1. So now bismuth 3+ is dominating over bismuth 5+. So that means I'm just playing with the hybridization in a way that I'm also controlling the charge state or the relative charge state of bismuth ions in the system. And of course, we also did some resonant photoemission, etc., to confirm that what happens to the valence band structure. But I will not go into those details at present about them. Okay. Now coming to the topic, sir, SrCOOX. So SrCOOX, if we look at, it can be SrCO3, which is perovskite, or it can be SrCO2.5, which is brown millerite in structure. The difference between these two is follows. SrCO3 is a normal perovskite AbO3 type of a structure. But when we remove oxygen from one of the planes, what we get is actually brown millerite structure, and we are not, and now we have COO4 tetrahedra as well as COO6 octahedra, which are stacked in layer with cobalt 3+ states. Okay. So this is the structurally difference between this SrCO3 and SrCO2.5. But the problem here is SrCO3 is not stable at room temperature in the normal conditions. So SrCO3 is difficult to stabilize. But this condition is not so for SrCO2.5. It can be stabilized excellently. So we started with this SrCO2.5 thin film. So it is supposed to be antiferromagnetic insulator with nil temperature below 570 Kelvin or so. And when we deposited this thin film, we deposited 3-4 films, 30 nanometer, 70 nanometer and 150 nanometer. 150 nanometer was way beyond the critical thickness beyond which the film is supposed to relax and there is no strain effect. So that was the reason. And the 30 nanometer and 70 nanometer were supposed to have the strained state, but 30 nanometer should have a larger strain than that of the 70 nanometer strain. And the X-ray diffraction pattern confirmed that okay, the 30 nanometer was highly strained than 70 nanometer. So far so good. And yeah, now we do this valence band spectra. So when we do valence band spectra, it is as simple as photo emission spectroscopy. Valence band spectra is nothing but photo emission spectroscopy. Only thing is that here I am not using X-ray source to eject those valence band electrons. I am using only some 30 electron volt or 40 electron volt to eject the electrons. So I am having this kind of features. And there are certain features which we can see, but we do not know their origin. Why we do not know their origin? Because since they are coming from the valence bands, they are the hybridized state of all the elements, outermost orbitals present in your system. So their energy separation is so low that you cannot make a distinction that okay, this feature is arising because of cobalt or oxygen or the hybridized cobalt oxygen or strontium for that reason and all that. Okay. To understand this aspect, what we do is resonant photoemission spectroscopy. What is resonant? Let's try to understand. In the normal photoemission spectroscopy, my electronic configuration is 3p6 3dn. So I am shining a photon. So when I am shining that photon, an electron from 3p6, or sorry, and there are some n electrons in 3d state. So when I am shining photon, an electron from 3dn will be ejected out. So my configuration will be 3p6 3d and minus 1. Very good. But if I change my incident photon energy in such a way that it happens to be just equal to the energy separation between transition metal 3p and 3d gap state, then what might happen? That electron in 3p, it will also start absorbing that incident photon. When it absorbs that photon, it will excite an electron from p6 and will have an intermediate configuration like 3p5 3d and plus 1, but that is unstable. This excited electron again comes back to the ground state, but before coming back to the ground state, it knocks out another electron which was already present in that 3dn state, something like OJ emission spectroscopy. Okay, and in that case your again final state configuration happens to be 3p6 3d and minus 1. So in a nutshell, what is the takeaway message? That if I incident my photon energy with energy values in such a way that it happens to be equal to the energy separation between 3p to 3d, you have now two channels of photo emission. Earlier you were knocking out electron only from the 3d states, but now when you tune your incident photon energy to be equal to separation between 3p to 3d, you are knocking electron not only from 3d but also from 3p also. So that means the probability of photo emission enhances. The cross-sectional area of photo emission to take place enhances considerably. So this energy separation between 3p to 3d is the characteristic of individual transition metal elements. So if I do that incident photon energy, suppose if that incident, this energy separation is close to 56 electron volt, then I can say that okay, this particular feature arises because of say iron. Because for that incident photon energy, the intensity will increase substantially. For instance, here you can see in this example of cerium oxide. See, this is at 118 electron volt, the intensity is very low. 121 electron volt, intensity goes up. 122, it goes very high. So 122 electron volt I know is the energy separation between this cerium 4d to 4f state when it is in 3 plus state. But the same cerium when it is in 4 plus state, this maximum 4d to 4f gap occurs at 125 electron volt. okay, and that is present here. So that means if you take a normal valence band spectra of cerium oxide, the first feature that you get near the Fermi level is because of cerium 3+. Cerium 3+ you should not expect in CO2 if it is a stoichiometric, because cerium should be in 4+ state. But just because you are seeing this resonant maxima close to 122 electron volt confirms that the first feature that you are getting in the valence band spectra arises because of the oxygen vacancy induced defect state of cerium 3+ in the system. Otherwise you will not get this feature, whereas the real cerium 4+ occurs at close to 5 electron or 4 electron volt or so. Okay, so we did this valence band spectra at different incident photon energy and plotted the intensity of these individual features. So the only takeaway message at present is that what do we see, that the first feature, this, it shows an anti-resonance, then a maxima close to 63 electron volt or so. So this 63 happens to be equal to the energy separation between say cobalt 3D with 3p to 3D. So this confirms that this first feature arises because of cobalt 3D state, number one. Number two, this anti-resonance or the dip in the intensity arises because when your cobalt is strongly hybridized with oxygen. So this is an indication of a strong hybridization, because just try to understand, in if you look into this energy range, the cross-sectional area for oxygen 2p photoemission probability gradually decreases. But just because oxygen is strongly hybridized with this cobalt 3D, what do we see, that it shows a kind of dip. Had it been only cobalt 3D state without oxygen contribution, then you will see a flat line, something like this feature C. Okay, so the appearance of dip indicates that cobalt is not only present near the Fermi level, but this is also strongly hybridized with this cobalt 3D state. Okay, so this confirmed that in the strained SrCO 2.5 film, cobalt is strongly hybridized with oxygen vacancy, oxygen states. Now if you look at this X-ray absorption spectroscopy, what do we see, that SrCO 2.5 bulk shows only one peak, but the strained film of say 30 nanometer, the main peak splits into two peaks, and the splitting is symmetric with respect to main peak. The symmetric splitting of these main peaks indicate that now my cobalt is not only present in 3+, but it is rather present in 3+ delta and 3- delta states. So there is a heterovalency induced in the system. The same 150 nanometer SCO film does not show that kind of splitting. That means this splitting arises because of the strained states only in the system. And also there are some extra features which is missing in the bulk or 150 nanometer. This again indicates that this extra feature arises when you have a strong oxygen 2p character in the system. Okay, so from there we confirmed that the strain causes heterovalency of cobalt in the system. Now what this heterovalency can do? This heterovalency will actually give rise to, okay, in your normal state, suppose there is no heterovalency, then in SrCO 2.5 I have only cobalt 3+, oxygen cobalt 3+, and the bond angle being 180 degree, I will expect this cobalt oxygen cobalt to be antiferromagnetic in nature, and therefore my ground state should be antiferromagnetic, which is observed for this bulk SrCO 2.5. But because of this heterovalency creates a hole pockets in the oxygen 2p band, and because of that it induces a double exchange type of interaction in the system and brings the system down to ground to the ferromagnetic state. And when I increase this thickness, that means if I am decreasing the strain state, then this energy separation or the charge disproportionation, this delta value also decreases. So that means I am controlling this heterovalency, the extent up to which this delta can change is decreasing gradually with respect to thickness. Okay, so because of this heterovalency, now you can see that this 150 nanometer, which should have been antiferromagnetic, of course is antiferromagnetic, but the strained film shows a beautiful magnetic hysteresis behavior, and you can see that its Curie temperature is even beyond 150 nanometer. When I increase the thickness, that means when the strain is relaxed, that means when the disproportionation is decreased, then you can see that the magnetization, saturation magnetization also decreases. Okay. Now this is further confirmed by doing this element specific X-ray magnetic circular dichroism. 150 nanometer I knew should be antiferromagnetic, so should not give any magnetic signal, but 30 nanometer shows a prominent signal. So that means a strain has induced heterovalency in the system by means of enhancing the oxygen cobalt hybridization in the system, and hence brought the antiferromagnetic system to the ferromagnetic state. And of course, the saturation magnetization also gradually decreases. I will just take a couple of minutes to show one final example of just tuning this SRCO 2.5 to SRCO 3, how it affects the various other properties. And to do that, we deposited this SRCO 2.5 on conducting NB-doped strontium titanate, and on top of that we had this strontium ruthenate. We do this IV measurement, and what do we see? That when the biasing is close to 2.1 volts, the IV changes abruptly. So that means this SRCO 2.5 abruptly converts to SRCO 3, and the same thing is true when it is brought back. Okay. How do I know that this is really SRCO 3? To do that, we do this electric field dependent X-ray diffraction measurement. You see, please focus on this red spectra, sorry, diffraction pattern. This 0 volt, you can see we have a very good peak of brown millerite peak, very good 006 peak of brown millerite peak. The moment we apply biasing of 2.2 voltage and then do biasing, what do we see? This peak vanishes here and a new peak emerges. This peak vanishes here and a new peak emerges. This clearly shows that when I apply biasing, SRCO 2.5 undergoes a transition to SRCO 3. So what it does, it gets oxygen from the underlying oxide layers. Okay. And when I again remove that biasing, again you can see that this XRD goes back to its original state. Okay. So this electric field dependent X-ray diffraction is a clear-cut demonstration of phase transition, or I should not say phase transition also, because it's materials transition as such. Okay, from SRCO 2.5 to SRCO 3. The same thing is also confirmed from this Raman spectra. SRCO 3 being the perovskite structure, cubic structure, its Raman modes are generally not observed. Okay, so when you see this, this is at 0 volt. Please focus on this peak, okay, this peak. And when I apply biasing, this peak vanishes, again this peak vanishes, because I am changing the brown millerite to perovskite structure. I am controlling the oxygen flow in the system just by applying biasing in the system. And you know what? The beauty is that SRCO 2.5 being antiferromagnetic, SRCO 3 ferromagnetic, just by applying 2.2 voltage, I can change the magnetization like anything. Okay. So here is the magnetization. You can see SRCO 2.5 antiferromagnetic. When I apply biasing, it turns into ferromagnetic. This is also confirmed from this electric field dependent X-ray absorption, which shows that cobalt changes its state from 3+ to 4+ state, and because of that the change in magnetization is as high as 250% at only application of 2.2 voltage. Okay. Not only that, all these individual states are highly stable. You can ramp it as many times as you may like, and you can see that you can get any of these values at the stable states. And importantly, not only these extreme states you can attain any of the intermediate magnetic states just by controlling the voltage, by changing, say, in the steps of 0.1 voltage or 0.05 voltage. So you can stop your magnetization measurement or electric field application at any value and can get the desired magnetic state. So there is a tremendous change in the magnetization with the application of minor voltage of, say, 1.5 volts, 2 volts, and the voltage that you may like to do here. Just try to imagine the multiferroic materials, the magnetodielectric materials that people generally talk about. They talk about the change in dielectric as high as hardly 10 to 15% on the application of 7 Tesla magnetic field. Here those extreme conditions are not required. I am using a minute voltage of 2 voltage And these measurements are, you can see that are being done at the field of 1 Tesla and at room temperature. You do not have to go at very low temperature. So these are huge potential. Just by tuning the X, you can get fantastic set of magnetization data. You can control various of the properties. So the takeaway message is that we all feel maybe strained at present after 1 hour of nonsense talks. But remember, when we apply the same type of strain on these fascinating oxide materials, it creates tremendous in terms of application. It gives us a huge scope in terms of controlling various of the properties, be it electrical property, electronic property, structural property, magnetic property, or the device performance that you can think of. So the strain providers in this work are dedicated to all my old and the current fellows who have been working with us. And yeah, I'm thankful to my director, all the industry workers, my co-workers, and all our extremely talented users from whom we learn quite a lot, all our gurus, and all everyone present here. Thank you all for your kind listening. Thank you.
A few questions.
Just one question. You said like you are applying certain voltage. Definitely it is creating the orange force, right? So the voltage will be same for any sample dimension, or I mean, what was the dimension of your sample?
Okay, the dimension of this sample is 5 by 5 millimeter square.
And let's say if
okay, and the thickness of this sample was 120 nanometer.
If I have larger sample or smaller,
yes,
the same voltage will be there, or we have to accordingly. We have
remember, here I am applying the voltage across the thickness, right, not laterally.
Right.
Okay, so the voltage, even the same voltage will work for that dimension also. Yeah.
Basically, oxygen is migrating from
exactly.
the inner
Yes, from the inner or the top
A
surface.
similar question on that way. Now you are saying that the oxygen is coming from the conducting neon. I mean, this is the niobium.
Strontium titanate.
Strontium titanate.
Yes.
But why, I mean, when you are applying the potential, why oxygen is coming from that? Why the atmospheric oxygen? I mean, you know, if you are doing some
your
measurements.
SrCO 2.5 is sandwiched between strontium ruthenate and NB doped STO. So strontium cobaltate is not looking at the atmosphere. It is looking at the first neighbor, the next neighbor. The first neighbor on top is strontium ruthenate, the next neighbor at the bottom is NB doped STO.
Okay.
And you might have observed that there is asymmetry in IV also, and so for the voltomagnetic effect also. That is because the oxygen releasing energy for strontium ruthenate would be different with respect to NB doped STO.
Okay, I mean, you mean, you know, here this ruthenium transium oxide, is it oxygen 3 and 2.5? Is 2.5 is unstable?
I'm not talking about ruthenate. SrCO 2.5
SrC, yes.
SrCO 2.5 is stable. SrCO 3 is unstable. Yes.
Okay,
yes.
but when it is taking the oxygen, then it becoming the ferromagnetic.
Yes.
Isn't it?
Okay. SrCO 3 by nature is ferromagnetic. By applying biasing, I am forcing it to be in 3 state, SrCO 3. And I am forcing it to be in ferromagnetic state. So that is the state. Yeah.
And what is the application of, by the way, this for this? I mean, can we make a kind of magnetic balls or something like that?
Why not? I mean, possibly one can make, because see, ultimately, what do you want? You want the tunability of the magnetic states,
correct,
right?
Yes.
So this is what is being shown here. Exactly.
I mean, by applying such a small voltage, if you are
Yes.
changing its magnetic state anti
Yes.
to ferro, so
Yes.
it can work as a
Certainly.
very good magnetic.
Yes,
I mean,
yes. This is
ball.
what we have proposed. Yes, exactly.
One question. So this volto-magnetic effect. So in this, whatever the voltage applied, that is
2.2 voltage, 2.3 voltage.
So that is
0.1
generating some
voltage.
lattice strain.
Is that generating some lattice strain? This is what you are saying? No, I am just controlling X in SrCOX.
Okay.
From 2.5 to 3. Okay, now here is a very honest admission that I would like to make here. Does my sample directly go from SrCO 2.5 to SrCO 3? I do not have answer. Okay, it may also go to say SrCO 2.7, SrCO 2.75, but my X-ray diffraction shows that at beyond 2.1 voltage, it completely transforms into SrCO3. That is pakka. But below 2.2 volts, whether it is SrCO3 minus X 2.5 or between 2.5, this part I do not know, because XRD has not allowed us to probe that part.
Okay, and
Yeah,
second,
I didn't see any change. Yeah.
Second thing, as you said,
But of course I didn't see any change, but what I saw here, you can see that since just by 1.8 also I can control the magnetization, that means कुछ तो change हो रहा है. वो क्या change हो रहा है, राम जाने. Yeah.
आपका नाम है वो. आपका नाम भी राम जाने. Anyway, so another question is what, as you said, for those who are working in multiferex, they apply very large magnetic field, and they. So as far as we are also working on multiferex. So this is somehow I feel that this is a converse magnetolytic effect. But
Exactly.
Can I take the benefit instead of using lattice strain? Right now we also don't know. But if I use piezo strain to tune the magnetization in your case.
Certainly, I mean one can do, but here in this particular example, I am not using.
Yes, that's why. I also agree.
Right.
That's why I said
Yes.
it is a lattice strain.
Correct.
But in another system
But
we can design.
certainly, yes, because
piezo
in the
strain.
first example that I showed, that with a strain I can change the magnetic state. Of course,
That is
one
the
can do
beauty of
that.
the.
Exactly. Yes.
Sure.
Yes.
Questions from students. We expect at least 2 or 3 questions from students.
मत पूछना भाई.
Means in SRMNO3, you are converting from second order to first order thermodynamical transition.
LSMO thing.
Yeah.
Which was grown on BATI.
Yeah, yeah.
I'm not converting into second order or to first order.
But your
There
graph
is-
shows that there is.
There is hysteresis, there is abrupt jump, but that is just a strain induced change in the system. It's not the property of LSMO as such. So because the strain is transferred to the LSMO, it has instantaneously played with the anisotropy, and because of that I am seeing that jump.
Yeah.
So as such there is no
There is no thermodynamic change actually.
There is no thermodynamic change in that sense. Yes. So वो जो hysteresis आ रहा है, that hysteresis is arising because my BTO shows a structural transition which is first order in nature, and it has hysteresis character, and because of the hysteresis character of BATiO3, it is reflected upon the properties of LSMO. So as such it is not the property of LSMO but the underlying BATiO3.
Anisotropy.
Yes.
But there might be some delta S and delta T.
Delta, वो होना है. Yes, but this is what I am saying. But this is what I am saying. But that is because of the substrate, not because of the LSMO.
Because of the substrate, yeah. Yeah, any condensed matter students or some? Yeah, why you said some difficult or something? Students are not asking questions.
Thank you.
Yeah. 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 If there are no questions, then let's thanks speaker again.
Thank you
for a nice talk. Yeah.
Thank you so much, sir. Now I request Professor Patil to present Dr. Ram Chaudhary sir with the memento as a token of honor. Now I request Somnath sir to felicitate our session chair, Professor Patil. Now we have a series of oral presentations. Basically, the rules remains the same as before. You will have 8 minutes to present your presentation and followed by 2 minutes of discussion. Now I read the name of presenters to schedule their talk in the BD hall. If you hear your name, please make your way there to present your presentation. Ms. Yogita Padwal, Ms. Sandhya Deshmukh, Ms. Suman Pandit-Shetty, Mr. Akash Kher, Ms. Nikita Kapadia. I kindly request you all to be in the BD hall. Now we are beginning with our oral presentation. Now I would like to announce the next presenter so they can be ready. Ms. Swapnali, Ms. Vrushali, Mr. Suyog Mane, Mr. Rahul Kumar and Ms. Shruti Shaha. Please be prepared for your presentation. Now it is my honor to introduce the session chair for this oral presentation, Professor Said and Professor Kamble from the Department of Physics, Savitribai Phule, Pune University. Sir, I warmly welcome you and invite you to take your seat as a session chair. Now I would like to invite Ms. Swapnali to present her topic. Those who have presentation, can you please be here with your pen drives? Ms. Swapnali, Ms. Rushali, Mr. Suyog Mane, Mr. Rahul Kumar and Ms. Shruti Shah. Yeah. Now I would like to invite Ms. Swapnali to present her topic.
Good afternoon, one and all. Myself Swapnali Vikas Warke. So today I am going to present my research work at 31st Raman Memorial Conference at Department of Physics, Pune. So the topic of my research is voltammetric investigation of bandage parameters and electrochemical performance of hercinite nanoparticles for electrolysis of water into acidic and basic medium. Since I'm working on the area like renewable energy source hydrogen, we can say the deployment of hydrogen is very less as it is used in the transport, as it is 13%, but it can be increased in coming days since we have set our goals as net zero emission by 2050. So as we compare the hydrogen as fuel source as in comparative to the diesel, petrol, electric, we can say that the hydrogen engine is very efficient in energy. Also it emit zero emission. It only emit the water vapor. Also the initial cost is very high, means generation of fuel is very high, running is lower than the petrol and diesel, then maintenance is moderate, then it is having performance wise it is highly efficient. Also the refilling or charging time for hydrogen is fast. So in the India the infrastructure availability is very limited and it can be increased in future coming days. So this is the graphical abstract of my work where we have synthesized hercinite nanoparticle using sol gel method. I added precursors like iron nitrate, aluminum nitrate in water with ratio 1:1 and chelating agent as citric acid and tartaric acid for ratio 1:1:2 and stirred at 120 degrees Celsius to get clear solution, heated at 120 degrees Celsius to evaporate the water and got a sol, and this sol was annealed at different temperature 100 to 1000 degrees Celsius and got a pure phase of material at 400 degrees Celsius. Then the material was characterized using electrochemical technique for its performance for HER and OER. So these are the characterization techniques. We characterize the material using XRD, Raman, magnetic hysteresis, room temperature, and TM studies, where we got a pure phase of material at room temperature. It's as cubic phase. Then Raman spectra was recorded with Raman mapping of mode 5 F2G for 508 centimeter inverse and A1G for 722 centimeter inverse, where we can say that the material is pure phase, where Fe is forming tetrahedral coordination with oxygen and aluminum is forming octahedral coordination with oxygen, and we are having a normal spinel structure of the material. Then from the magnetic hysteresis loop, we can say that material is paramagnetic in nature, as at zero magnetic field, there is no hysteresis or no cohesivity observed. From TM, we got particle size of 20 nanometer. Then XPS study was carried out to confirm the material's oxidation state, oxidation state, where we can confirm Fe is in 2+ state, oxygen is 2- state, and also the aluminum is in 3+ state. Then we carried out the cyclic voltammetry study, like CV and LSV measurements for HER and OER. So for 1 molar KOH, we are getting linear sweep voltammetry graph, and it is shown in the figure A, where we are getting 70 millivolt as over potential at 10 milliampere per centimeter square current density. For the same, we are getting OER over potential as 1.61 volt. For acidic environment of electrolyte, we are getting 613 millivolt for 0.5 molar H2SO4 and HER over potential, and for OER it is 2.12 volt. So based on this result, we concluded that for 1 molar KOH, FeL2O4 is showing better performance, as 70 millivolt is very low in the category of ferrite materials or spinel materials, where we calculated its TFL slope as 51 millivolt per DEC, which shows the rate determining step or RDS step is related to the Walmer step. Then EIS study was also carried out. Also for confirmation of material, if it goes for HER or OER, we carried out the cyclic voltammetry in 3 electrode system, where the material was deposited on 1 by 1 centimeter area on carbon as a substrate. Then we measured the cyclic voltammetry CV curve in nitrogen atmosphere, inert atmosphere, and got 2 peaks, A1 and C1, as shown in the figure A, where we can conclude from this study that we are getting conduction band edge of material as minus 0.65 electron volt and valence band position as 1.35 electron volt, which signifies that material is more feasible for HER reaction than OER reactions. So this is supporting to the our application part, that material is more feasible for hydrogen evolution reaction. As also in the category of other ferrites and other aluminates, the material is better or showing similar conduction bandage. So outcome of these studies, we successfully synthesized novel electrocatalyst and confirmed using state-of-art characterization technique. Electrocatalytic hydrogen evolution over potential is better than OER over potential in basic medium. Also, we validated using band energy diagram, and we will in future possibly develop the alkaline electrolyzer based on the data. So I thank everyone for calm listening, and I request any suggestions and questions for my presentation. Catalyst was FeL2O4 arsenate nanomaterial. Arsenate. Yes.
Can you please explain what is green hydrogen?
Actually, there are different types of hydrogen, like blue hydrogen, green hydrogen. So green hydrogen term is defined as it is not causing any harm to the environment, not causing any harmful gases when it is produced from electrolysis, so it is called as green hydrogen.
Okay, it depends on the method of production.
Method of production. Yes, sir. Yes, sir. Actually, depending on XPS study, we have confirmed using Fe is present in 2+ state. Also, from XRD, we are saying that the material is cubic in structure, and also we have calculated in inversion factor I, which is saying the material is pure form. So. Yes, sir. We have done the Mossberg spectroscopy from UGC DAE, but I have not added the data into it. Yes. These modes are representing the characteristic modes of FeL2O4, where F2G mode is typically for Fe tetrahedra, and A1G mode is typically for aluminum octahedra ALO6. Thank you, sir.
Thank you, ma'am. Now I would like to invite Ms. Vrishali Karoke to present her presentation. OP30.
Good afternoon, everyone. Am I audible? I'm Rushali Karoke. I'm doing PhD under the guidance of Dr. Rupali Nagar. The title of my today's presentation is Phase-Dependent Broad-Range Photo Detection by Iron Oxide Nanorod. Here is my outline of today's presentation. First, I'm going to introduce my work, photosensor. What is a photosensor? Photosensor is a device in which the photon energy get converted into the electrical signals. Why this photo detection or photosensor study is important? Because it has several application in a various field. Before going ahead, I'm going to explain in a basic mechanism of the photosensing. The very first step is a light absorption. When we incident the photon light, then there is absorption of a light come in a picture. Then there is a generation of the electron and hole pair. After the separation of this electron and hole pair, there is a production of the electric signals in the form of the photocurrent. So till date, several material are used as a photosensitive material, such as zinc oxide, TiO2, and many more. But till there is a growing need for developing the more sensitive and easy to fabricate, low cost material. For that, many researchers are using the metal oxide semiconductor material. Why metal oxide semiconducting material? Because it has several and excellent unique properties. So out of this metal oxide semiconducting material, today I'm going to discuss about the iron oxide, because it has a unique property and excellent photoelectrochemical properties, but it has some limitation, such as it has a limited charge carrier mobility as well as a very high rate of a recombination. So to overcome this limitation, we need to find out some alternative way of a synthesis of this iron oxide material. So here is my first objective of today's presentation, that is the synthesis of the iron oxide nanomaterial with the help of co-precipitation method. Here is the schematic. I used FeSO4 and FeCl3 as a precursor, but during the synthesis, I altered the way of addition of the precursor. First sample is a one-shot addition of the one-shot addition was carried out. We named as a COP1 sample, and in a second sample, dropwise addition is carried out. We named as a COP2 sample. Further, we have done their characterization. The very first characterization we have done, that is a XRD. This blue color is indicating the COP1 sample and red color is indicating the COP2 sample. After the analysis, we got in a COP1 there is a formation of the mixed phases of alpha FeOH, gamma FeOH and alpha Fe2O3. Whereas in a COP2 sample there is a formation of epsilon Fe2O3 and gamma Fe2O3. From this, we conclude that there is a formation of a multiphasic iron oxide nanomaterial. And from this data, we have a calculated crystallite size with the help of Scherer formula as well as dislocation density. And from this, all the calculation we have tabulated here. And from the crystallite size as well as the dislocation density, we observe that there is a structural variation in both the sample are observed. Furthermore, we have done their morphological study with the help of HRTM, and from both the sample we got a nanorod kind of morphology. And we have calculated their average length and average diameter with the help of images software. Average length is a 60 plus or minus 8 nanometer in a first sample, which is shifted towards 14 plus or minus 3 nanometer in COP2 sample, whereas in a diameter which is shifted toward 5 nanometer to 3 nanometer in a COP2 sample. Furthermore, we have calculated their aspect ratio and their despacing value. And from this data also, we confirm that there is a formation of the multi-oxide mixed phases of the iron oxide. Furthermore, we have done their optical study with the help of UV visible spectroscopy and determine their talk plot with the help of talk plot. We have find out their energy band gap value, as well as from FTIR spectra. We confirm that there is a formation of the FeOH, formation of the mixed phases of the iron and hydroxide. So from this table, if you see in a first UV visible spectroscopy, in the first sample there is a 3 different energy band gap is observed, and in a second sample there is a 2 different energy band gap is observed. From this also we can say there is a formation of the mixed phases of the iron oxide. Furthermore, we have done their application in a photosensing. The very first application we have done under the UV light illumination at a 365 nanometer at a bias voltage 5. For COP1 sample, these are the measurements. So purposely we have taken UV intensity values 1%, 3%, 5%, 7% and 10%, because we wanted to check at a very low intensity value how this photosensitive material is react. And similarly, we have done a similar kind of a measurement in a COP2 sample, and from this data we have calculated response time and recovery time. So for black bar is indicating the COP1 sample and red bar is indicating the COP2 sample. From COP1, the response time is nearly 6 seconds, whereas recovery time is 9 seconds, except intensity value 5%. And in a COP2, the response time and recovery time is nearly 3 seconds. And from this data, we have calculated the sensitivity as well as detectivity. So this value is tabulated here. If you increase the power intensity from 1% to 10%, then there is an increase of the sensitivity in a first sample. But after the 5% of intensity, their saturation is observed. And whereas detectivity is increases from 1% to 10%. And in the second sample, COP2, if you increase the sensitivity from intensity value from 1% to 10%, there is a decrease of the sensitivity as well as the detectivity. Furthermore, we have done their visible light detection. Purposely, we have chosen red light as well as the green light. So here we are considering 10% of intensity for comparison, and red color, red light and green light. So this is the spectrum we got. And from this, we have calculated the response time as well as the recovery time. So in under UV light, at a 10% intensity, response and recovery time having a value nearly 2.6 seconds. And in the case of the under red light, we got a response time is having a very less value, that is 0.4 seconds, whereas recovery time is 9 seconds. Under the green light, response time is 0.3 seconds and recovery time is 0.8 seconds or nearly 9 seconds. And furthermore, we have calculated their sensitivity as well as the detectivity. From this table, we confirm that, or we observe under the green light, it's showing a very good sensitivity as well as a detectivity. So here is a schematic of a mechanism of today's work. After that, I will conclude my work. It is a one-spot synthesis enabled the formation of the multiphasic iron oxide in a nanorod morphology. A longer nanorod in a COP1 possess the or it mixed showing the mixed phases of the alpha FeOH, gamma FeOH, and alpha Fe2O3. Whereas in a smaller nanorod in a COP2 possess epsilon Fe2O3 and gamma Fe2O3, whereas the crystallite size and dislocation density indicating the variation in a crystallite quality in the material. Under the 365 nanometer of UV light at a 0.5 volt bias, COP1 exhibited a response time nearly 6 seconds, and whereas in a 5% showing a 2.5 seconds, whereas recovery time is a 9 seconds. And in the case of COP2, it consists faster response is nearly 2.5 seconds, whereas recovery is around 3 seconds. And it is okay. In a visible light detection, it showed that COP1 was ineffective. It's showing the noisy kind of signals. That's why COP2 responded well across all tests of the wavelength. Then COP2 exhibited the highest sensitivity and detectivity under the green light. And COP2 dual sensitivity to UV light and visible light makes it a promising candidate as a broad spectrum photodetection. In situ synthesis of the multiphasic oxide in materials is an alternative way of to doping. So I acknowledge to my guide Dr. Rupali Nagar and Dr. Sanjurani from IIT Madras. On this work, my paper got published from 3 to 4 days back. These are few references. Thank you.
Okay, please. Okay, it was synthesis in a just form solution. Okay, so how it is converted in terms of films?
In terms of?
Because it's a film, because your measurement was in on
for
a film.
photosensing measurement,
yeah.
we have a drop casted our sample 20 mg of a sample in ethanol. So we sonicated and drop casted on screen printed electrode.
Okay, so what was adhesion and everything? Because this contains all, let us say, FeO, alpha, and does this oxide material has a band gap?
Yes, sir.
Gamma Fe2O3 has a band gap.
Gamma
Epsilon
Fe2
Fe2O3 has a band gap because you actually calculate band gap. Yeah.
Yes, sir. Yes, sir. I have done XPS spectra also, but abhi time limit. Okay, so after when we drop cast the sample on a screen printed electrode, we kept it for a drying for overnight at a room temperature, and after that we subjected towards the measurement.
Adhesion and everything would be poor, no?
Drop casting sample, your adhesion will be very, very poor.
Yeah, very, very poor. Yeah, even just like even blowing, it can actually powder can come out.
So did you
No,
use
sir.
any other element there to improve the adhesion? Did you change the adhesion of your material with the substrate?
Yes, sir. Actually, initially we have done a slurry in a different solution like acetone.
Binding reagent?
No. No, we used only ethanol. Ethanol for drop casting on a screen printed electrode, because in IIT Sorry? Yes, sir. 4 times we repeated this result.
What was your metal contact, top metal contact, and how did you make it?
Contact, okay.
No, you tell me, don't show me this one. What was your top contact when you measure the device, when you prepare the device?
Okay. Sir? Yes, I'm getting your question. How electrode contact?
You must be bottom contact, you must be conducting either FeO or any conducting substrate. What was the top electrode and how did you make it?
Sir, actually when we are drop casting on a screen printed electrode at the corner, there are the space which is connected to that.
Then what is the thickness you have considered? Because there was no thickness parameter in that case. You know, you have put like a table, the sample is there and another 2 corners. You have applied the bias there, isn't it? So then what is the thickness? Have you studied the thickness dependent property?
No, sir, I haven't.
वृषाली, जस्ट पिछले स्लाइड में जहाँ आपने रोका था, कैन यू जस्ट गो टू दैट? हाँ, you see the intercept that you have made in that UV visible.
Yes.
देख सकते हैं कि उसमें कहाँ मिस्टेक है?
Which one, sir? First one or second?
See, your x-axis is not passing through y equals 0, na? हाँ. So that way your intercept will be different every time. है ना?
0 के नीचे किया ना आपने इंटरसेप्ट.
अच्छा ये बताओ, वो जो तुम्हारा एक्स एक्सिस है 0 से पास करता तो EG would have been different? Okay, I'm sorry then. And from XRD you have calculated dislocation density and crystallite size. When you have so many phases, तो dislocation किसका? Crystallite किसका?
So if you see alpha FE2 FeOH first phase, so there are number of peaks are present. Suppose 4 to 5 peaks are showing the alpha FeOH. Then out of these phases, out of this peak, most highest intensity peak we have considered.
No. Crucially, for example, can you identify whether this is alpha? For example, if there is alpha phase, then what should be the, let us say, features of alpha phase that should represent or that should represent in XRD? Yeah. For example, if I wanted to conclude this is alpha phase, okay, so what phase or what intensity of alpha phase should be present there?
For alpha FE2O3,
Yeah.
highest intensity peak.
Yeah, okay. Which is highest intensity?
In this case, this one is a 111 plain 111 is showing the highest intensity peak.
No, but here in the JCPD's data is 111.
This is the ISPS file. From this literature only I have got. So we have analyzed this sample and 200, 400 and 800 are, no, not this sample. Not this sample, this is as synthesized sample, but after the annealing of 200, 400, we subjected to photosensing result, but we are not getting any results. But for as synthesized sample, we got this kind of result, so we kept as it is and then we have done their application further.
Okay, no problem. So I don't have any question, but I have one comment. So it is a thumb rule. Method of preparation strongly affect the properties of material.
Yes.
So for this nanoparticle, I think it is better you change your method of preparation because you just try with another method. Because in this method you are use the co-precipitation as one COP1 and COP2, little bit variation is there. So iron oxide is well studied material and very good techniques are there. Rather than
Thank you, ma'am. Now, I would like to call OP22, Mr. Suyog Mane.
Good evening, everyone. It is an honor to be here to present my work in 31st Raman Memorial Conference. My name is Suyog Mane. I am working as a research scholar in Department of Chemistry, Savitribai Phule Pune University, under the guidance of Professor Santosh Krishna Haram. The title of my today's talk is composition-dependent band structure parameters and band gap Boeing effect in cesium lead mixed halide system, a cyclic autometry investigation. So let's start. I have just give a little bit idea about why this kind of work is very important to do. So when we talk about the first industrial revolution, the industrial revolution is mostly depend upon the three unstoppable forces: is communication, transportations, and power sources. So when first industrial evolution happens, the communication media is printing press and telegraph, and the transportation is occurred by using a steam engine, and the power source is burning of a coal. In second industrial revolution, the communication is developed more, and people were using telephones, radio, and television as a communication media, and the transportation is also improved, and the combustion vehicle are come into the picture. So, and the power sources was people are using most of the oil sources. So now we are living in the era of third industrial revolution. So our communication is also more advanced nowadays. We are using social media, internet, so many platforms, and our transportation is also become more advanced. So now we are using electrical vehicles, and our power sources is also changes accordingly. Now people are more focused about the using renewable energy sources like solar energy, wind energy. So what is the question? Why are people mostly focused on the using solar energy or wind energy? So mostly we talk about the main reason is pollution or global warming, but actually picture is a little bit different. I thought, because nowadays we observe that the price of non-renewable energy sources are skyrocketing. Accordingly, if you compare the renewable energy source, the development is nowadays the price of renewable sources is become more and more cheaper. So now come to the picture. I directly come to my work. So what are the must knows before crafting a solar cell? So what is a solar cell? Basically, solar cell is a device which convert light in solar energy into electrical energy. So but solar cell is made up of different kind of layers, charge transporting layers. Like we have one light absorbing materials, we have electron transport layer, hole transporting layer materials, and our electrodes. So to construct any kind of solar cell, we must know about what is the conduction band of that material and what is the valence band of material. So why these two things are more important? Because if you see that our light absorbing materials like perovskite, the band alignment of electron transporting layer or hole transporting layer doesn't match with perfectly. The electron will not transfer from the perovskite to any other materials. So even if we fabricate one of the most outstanding material in lab, but our alignment is not properly, we cannot make a efficient solar cell. So now in my work, I have worked on the synthesis of perovskite, cesium lead based metal halide perovskite nanocrystals. I have synthesis using hot injection methods. I have used different halides, cesium lead iodide, cesium lead bromide, cesium lead chloride. We can see the luminescence of different perovskite nanocrystals I have synthesized. The first one is cesium lead chloride, cesium lead, the middle one is cesium lead bromide, and last one is cesium lead iodide. And the blue emission and yellow emission shows the mixture of cesium lead iodide bromide and cesium lead bromide chloride. So so we have characterized this material by using XRD as shown in XRD pattern. We observe that as we move from the cesium lead iodide bromide chloride, the peak are shifted to the higher degree due to the change in ionic radii of the halide materials. So here is the HRTM image of cesium lead bromide perovskite nanocrystals. The average particle size of that is 8.56 nanometers. So here I have characterized all the samples by using UV visible spectra and photoluminescence spectroscopy. Here we are also we can see that as we move from the iodine, bromine to chlorine, as the halide substitution changes, the UV visible spectra as well as photoluminescence spectra is shifted from lower wavelength. It means that the band gap. It means that this blue shift is indicate the change in optical band gap of the materials. So again, the main focus of my work is to investigate the bandage parameter of synthesized material by using cyclic voltammetry. So in cyclic voltammetry, we basically use different non-aqueous solvent like dichloromethane, acetonitrile, DMF, DMSO. So it is very important to know that our material is stable in that particular solvent or not. So for that I have checked which is the most suitable solvent for my voltammetric investigation, and I observed that in dichloromethane, the perovskite quantum dots luminescence properties as well as photoluminescence spectra luminescence properties are preserved, and it shows luminescence under the UV light also. So, in case, as I move further, I have recorded the cyclic voltammogram in presence of dichloromethane, where the platinum is used as a working electrode, silver wire is used as a Cauchy reference electrodes, and platinum is used as a counter electrode also. So, and I have recorded spectra for all the samples for cesium lead iodide, cesium lead iodide bromide, cesium lead bromide, cesium lead chloride, cesium lead chloride bromide. So as we see that our result is very well matched with the previously reported data. So why it has happened? As we see that the valence band is value is increases dominantly as compared to conduction bands. So if you when we talk about molecular orbital theory, the cesium lead halide perovskite in cesium lead halide perovskite nanocrystals, the lead is basically dominant in the formation of conduction band, and halide is dominantly affect on the valence bandage. So as we change the halide from iodine, bromine to chlorine, the electronegativity of the halides is affect on the valence bandage, and we observe the dominant shift in the valence bandage. So also we have checked we have calculated the electrochemical band gap and optical band gap. Electrochemical band gap is calculated from the cyclic voltammetry data, and optical band gap is calculated from the photoluminescence spectroscopy. And we have plotted this data with band gap versus lattice constant, and here we also plot the same with compared to the radius of halide moieties. Also in my current work, we have studied the band gap Boeing effect to observe last slide. So we observe the band gap Boeing effect, which is very important factor to fabricate any kind of solar cell, optoelectronic devices or solar cells. So we observe that the minus 0.2 band Boeing coefficient in both cesium lead iodide bromide system and cesium lead iodide bromide chloride system. And the conclusion of my work is by using cesium lead halide nanocrystal, we can fabricate a solar cell. Also we can design, we get a proper idea which will be the most suitable electron transporting layer, and which is most suitable hole transporting layer. Also by using cyclic voltammetry, we can estimate what is the exact bandage parameter of our materials, and also we in our study we observe that the band Boeing effect, which is more important factor to fabricate a solar cell. These are the references, and this work has currently published in the Physical Chemistry Chemical Physics journal, and thank you.
Now session is open for any question.
Okay, the main difference is that what is a optical band gap. When we shine a light on material, okay, so the electrons and hole pairs is generated in your materials. That is your optical band gap. But what in case of electrochemical band gap, what measurement, we actually measure the electron is come out of the from the materials. Means suppose in voltammetry, what exactly we do, we apply the potential negative bias to the negative bias. So at particular point, we observe that the when we apply negative bias, the electron is transferred from the electrode to the vacant position present in the quantum dots. So as we apply the positive potential, the Fermi level is decreases, and the electron is transferred from quantum dot to electrodes. So by using that, we measure what is the difference between obtained conduction band and the peak we see here. C1 and A1. The difference between two, we can estimate what is the exact electrochemical band gap of that material. So there is a difference because in case of electrochemical band gap, the Coulombic energy come to the picture, so it will be always greater than the optical band gap of that material. Yeah.
So I would like to ask one question. If I remove PB from your system,
Okay.
because lead is toxic,
Yes.
then is there any alternative?
So we can use tin also to replace the lead, but again, lead is a challenge. The lead is toxic, but it has also opened the many other opportunity. How we can coat this material by using different non-toxic material like metal oxide.
Currently there is a ban is happening on the lead.
Yeah.
So that's why I asked.
Okay. Yes, yes, sir. Yes, sir. Actually, sir, there are a lot of paper are published recently also. We can use this, we can directly use, by using spin coating method, we can directly coat this nanoparticle on the surface of substrate and we can fabricate a device. Oh, actually, sir, I don't fabricate any device, but yeah. Okay. No. I have just give idea what is the electron transport and hole transporting layer will be suitable. Yeah. Actually, I have plot the graphs here. So I have by using different literature, I have take values of hole transporting layer and electron transporting layer, and my materials value conduction band and valence band values are here. So I just give
when
idea.
you perform the photoluminescence measurement, what
yes.
was your excitation wavelength?
365 nanometer.
For all?
Yeah.
How you can do all? Because one of the materials is showing the photoluminescence peak somewhere around 700 and one is showing around 350 in your photoluminescence spectra. Can you open your photoluminescence spectra and show? Here you can see one peak is you are getting at 700.
Yes.
And one you are getting somewhere at 400.
Yes.
In all cases your excitation wavelength was same or different?
No, I use same.
Thank you, sir. Now I would like to invite OP17, Mr. Rahul Kumar.
For next slide, previous slide, and for the changing rules, he will explain you once again. Just ask.
ये पॉइंटर का है और ये दोनों स्लाइड चेंज, ये पॉइंटर का बीच में देखो, ये दोनों
फिर से
ये जो है ना, ये आगे पीछे हो गया, देखो
लेफ्ट साइड
और ये वाला ऊपर का और आवाज
गुड आफ्टरनून. Good afternoon. I'm audible. Sir, good afternoon.
So my topic is activation of cross-section measure and estimation of photon induced nuclear reaction for manganese. And my guide is FMD Attar sir and Sanjay Dhole sir. So basically my main topic is to find a shielding material basically. So I have done basically reporting of data on XPOR and database basically. This is for the first time we have measured the for manganese basically. So the photon induced is like this, where this is a incident particle, where you can see this. You can consider it as a photon that is incident on a target material. It can be form a compound nucleus, and there is a prompt gamma that has been detected, and after that it has been decay into radioactive nucleus. So after that it decay and delay gamma has been detected. So we have used HPG detector to decay the to detect the delay gamma, and there is a product nucleus basically. So this is my experiment. So I have choose a manganese because there is no experimental data in XPOR database, and I have gone through this in a literature where there is no author has been produced this data, manganese oxide, and I have chosen monitor as a gold, and we have used a photon of Bremsstrahlung of energy of 15 MeV, and after that we have detected on HPG and theoretical, and you can say experimental has been analysis. So we have used this medical linac in that has been provided in Memorial Hospital, Ahmednagar, India, and by using a tungsten we have produced a basically electron that has been bombarded on tungsten or high Z material. So after that we have produced a photon of a 15 MeV of Bremsstrahlung, and this is a basically a working principle of HPG, where gamma has been incident on the HPG, and it will ionize HPG detector of approximately 2.6 electron volt is needed to ionize the HPG detector. So we have applied basically a reverse bias voltage, and we have detected gammas basically. So this is HPG detector which has been in our institute, and by using a formula we have founded efficiency, where Kc has been represented as a coefficient summing effect. That means where 2 gamma incident at the same time in HPG. So we have found a correction factor on that, and C is the counting basically of a gamma, specific gamma, that is 834 keV, and A is the activity, initial activity, and I gamma is the intensity of that gamma, and decay constant and time lapse. So how much count taken? We have taken 3,600 seconds for counting time of that count basically for that gamma. This is the efficiency of HPG for a various you can say gamma, and 80 and 344 are the from the barium 133 barium, and we have fitted that gamma. So this is a gamma you can say gamma spectra, where I have considered this peak for my calculations, and for uncertainty and you can say covariance analysis we have done this for where we have taken consideration of monitor uncertainty in monitor, basically cross section of the monitor, and uncertainty in the counts of monitor and samples also, and the mass of basically abundance also, and in what is the efficiency on uncertainty efficiency also taken, and activity and intensity basically, and this is the time. What is the decay constant, uncertainty and decay constant has been considered for the, and covariance analysis has been done by using this formula, sandwich formula, where we have taken the sigma IR, that is when attributes basically a parameter that has been considered for this I gamma, or you can say in previous slide you can see counts, or you can say what is the mass and intensity basically. So for uncorrelated we have taken these matrices where this is in a diagonally 1, 1 and all are zeros, and for fully correlated we have taken all ones. And so we have done bash scripting also by using a tallies 1.96, where we have taken a calculation under possible combination is 384, possible combination of 24 input parameters for theoretical calculation. And this is a photon flux we have taken, where we have considered a theoretical value of you can say cross section of gold by summation, taking average cross section basically for flux, and this has been simulated by GN4. So this is formula has been used to calculate cross section, and I have taken this measurement basically, and that is uncertainty is approximately 30% in my case, and we have you can say compare with the tallies 1.96, and this all has been done in HPG basically in GN4. I have developed C++ programming by using this is a HPG datator, and we have taken you can say simulated cross section also. So conclusion is that we have taken a flux basically measure a cross section of 15 MeV Brunstern photons, and by using a LINAC, medical LINAC and GN4 we have taken a Brunstern flux, and monitor we have taken gold, and this results will be the first addition in the export database. Thank you.
Basically, you work on manganese. So, apart from manganese, can I select any another element?
Yes, sir.
Okay. And what kind of data base you have used?
Sir, actually we have not used any kind of database. We have calculated it.
You have calculated it
by using you can say these formulas. This is a cross section formula, and here that is the average cross section is the you can say a tallies from we have taken from tallies.
Yeah.
That is a theoretical basically theoretical value. This one, and that is being done in bash scripting. Linux.
Experimental input here, right?
Yes, sir. Yes, sir.
That's what we expect. What input you have used in this calculation of these processes?
Sir, input, sir, only counts, basically counts, that is gamma. How much gamma is coming from the sources basically in HPG, and that has been used as a to count a cross section basically of the element, basically that element for manganese. That is all. And that has been simulated also in GN4. That is using a C++ programming. No, sir. Manganese for that has been, sir, this one. You can see this. 55 manganese has been activated by using photon.
Why I am interested? Because manganese is quite naughty. It has multivalency. So it may hamper your something else. That's why I'm worried about that. That's why I asked.
But basically, this is a 100% you can say pure manganese has been taken considered.
Thank you, Rahul sir. Now I would like to call Ms. Shruti Shah to present.
फोटो पाठीमागं आणि लेझर पॉइंटर कोणते वरचं हे दोन आणि हे पॉइंटर आहे.
Okay. Thank you. Good evening, everyone. Firstly, thanks for the platform. Myself, Shruti Shah. I'm working under the guidance of Professor Sandesh Zadkar, Department of Physics. Today, I'm sharing my small research work entitled as Stabilizing TiO2 cesium lead iodide, abbreviated as CPIB perovskite buried interface for all inorganic halide perovskite towards highly efficient photodetectors. The outline of my presentation consists of the brief introduction to perovskite system, basically halide perovskite systems, followed by the synthesis protocol used for this study, further followed by the structural, optical, morphological and photoresponse properties, finally concluded with the brief summary and references used for the presentation. So let me take you towards what are the halide perovskites actually. Halide perovskites have a cubic structure material having formula ABX3, where A stands for monovalent cation, B stands for divalent cation and X stands for monovalent anion, basically halogen atoms. Perovskites possesses extraordinary properties like their high absorption coefficient, their tunable band gap, their broad spectral absorption region, and best of all is their low cost fabrication, means they can be fabricated using simple spin coating or solution processing. So though the perovskite have these much properties, why there is a need of interface passivation? We all know for perovskite devices, we need perovskite devices consist of multiple layers sandwiched together to form a architecture. So for that architecture, multiple layers consist of different interfaces between any two layers. So these interfaces are actually the trap sites, means there are the formation of ion vacancies that gives rise to the trap formation. Also at that interfaces there is a high possibility of carrier recombination. So for reducing this carrier recombination, for controlling the hysteresis generally observed in perovskite devices, and for the stability and efficiency improvement of perovskite devices, we need to passivate the interface. This is the simple synthesis protocol used for the synthesis of TiO2 as an electron transport layer and CPIB as a perovskite material. Here for depositing TiO2, we have used a simple hydrothermal technique which gives us the TiO2 nanorod arrays, means a controlled growth of TiO2s. Here we have inserted small amount of 10 mg amount of PVP, that is polyvinyl pyrrolidine polymer, that controls the growth of TiO2 nanorods, which will be observed in the SEM slide. So on that TiO2 nanorods, we have deposited the cesium lead iodobromide precursor by simple spin coating technique, annealed at 100 degrees Celsius for 10 minutes, and these films are useful for device and further characterizations. So let's start with the structural analysis. The XRD graph shows the polycrystalline nature for both TiO2 and cesium lead iodobromide perovskite structure. Plot B is the WH plot, that is Williamson-Hall plots for the analysis of crystallite size and microstrain values. For both of the materials, we can see that crystallite size have some changes. Crystallite size goes on increasing after the PVP insertion in the interface, but for microstrain there is not big change observed, that microstrain exerting on the perovskite lattice. Here TM analysis is carried out to check the interface, to get the more idea about the interface. Here the nanorod is of TiO2, and on the edge of tip of that nanorod the CPIB grain gets situated. A, B and C are the bright field images of those perovskite TiO2 interface. We can see at the image C, we can see that the nanorod, the some part of that TiO2 nanorod gets covered by CPIB grain, and that's where the interface gets formed. Image D is the SID pattern to confirm the diffraction planes present at that interface. For analyzing the compositional condition of this interface, we have carried out the XPS measurement. for each element in the interface has the proper spin orbit splitting. There is no big change between the PVP untreated and PVP treated TiO2 CPIB interface, but only when we observe that lead 4F spectra, for PVP untreated case there is a formation of lead oxide, which is very normal in the case of lead based perovskite, because PbI2 easily degrades into PbO formation. But when we used PVP in the TiO2 synthesis, the PbO formation gets reduced, and here firstly PVP signifies its benefit as a passivator in a TiO2 CPIB interface. Now we are moving towards the optical properties. The UV visible spectroscopy have two plots, A absorption spectra and B is tau plot for determination of band gap. Here for tau plot we can see that the first band gap position is for TiO2 for perovskite, and the second one is for TiO2. The table shows variation in the band gaps for both TiO2 and CPIB after PVP treatment, and this small change, that is for TiO2 the band gap get decreased by 0.1 electron volt, and for CPIB band gap gets decreased by 0.2 electron volt. But this small change can cause the variation in the charge transport mechanism in the total device architecture that will be shown in the band alignment. Here plot A is the Urbach energy plot. Urbach energy is basically the absorption tail in the absorption spectra after the band gap region. It is evident that lower the value of Urbach energy, lower will be the defects or traps present at the interface. Here for PVP treated TiO2 CPIB interface we get lower value of Urbach energy, thus here is reduction in the trap states at the buried interface. Plot B is the photoluminescence plot. The quenching of luminescence intensity after PVP treatment suggests the adequate injection of charge carriers from perovskite to TiO2 material. For morphological analysis, we can see the first image A and B are the images of TiO2 nanorods for untreated and PVP treated case. For untreated case, the nanorods have bulky 1D structures, but when PVP is introduced in the TiO2 precursor, the nanorods have a uniform and proper rod shape morphology. C and D are the micrographs when the perovskite was deposited on both of the TiO2 materials, and E is the bare CPIB film that was deposited on the glass substrate just to check its morphology. Plot C is the histogram that shows the variation in the lengths of nanorods for both the cases. This is the device architecture used for this photodetector application. Plot B is the band diagram. Here the difference we have observed in UV visible spectroscopy in the band gaps of both the materials. Here we can see that for TiO2, PVP treated TiO2 and the CPIB grown on PVP treated TiO2 gets their band H potentials shifted. That's why for PVP treated material we have smooth charge conduction. Now photodetector performance is here. We have plot A shows the transient photo response at 0 volt. That's why perovskites are known as self-driven photodetectors. Plot B is plotted to show the stable photocurrent nature after PVP insertion. Plot C is the single cycle plot used for calculation of rise time and decay time processes, and plot D is the stability curve. Here before PVP treatment the current loss is 25%, but after PVP treatment the current loss gets reduced to 6.2% only. Plot here on this slide, figure A is the JV curve in the light and dark mode, and figure B is the JV curve plotted to show the hysteresis nature in the perovskite materials. Here for both the perovskite materials we observe negligible hysteresis. Plot C is the Nyquist plot used for the calculation of charge carrier resistance. Here the plot is, the data is taken in the dark mode. That's why the higher the charge carrier resistance, lower will be the carrier recombination. And D is the Bode plot that gives the carrier lifetime value. Here we have performed the power dependent performance of the same photodetectors. Here we have taken the repeatability test for perovskite photodetectors, as perovskites are very sensitive to air, moisture and temperatures. These are the photodetector parameters for PVP treated interface. In both the cases we get the fast rise and decay processes and higher recombination resistance, giving smoother charge transport. While concluding, we can successfully passivate the TiO2 CPIB interface by using PVP, and it can be used as an efficient photodetector in UV and visible ranges due to its properties. And further in this case, we can possess the research by using dual interface passivation and its tandem architecture. These are the references used, and thank you. Sorry for delay.
Okay, now session is open for the question.
Changing, right?
Yes, sir. By 0.1 and 0.2
Whatever
volt
it is,
only.
but why would
Yes,
it
sir.
happen? Because the
Sir,
material remains same, right?
yes, sir. Material remains same, but the band gap gets changing.
Why?
Band gap changes.
What is the scientific reason behind it? That is what
Okay.
Because band gap is a material's property.
Okay, sir. Yes, sir.
Which is also utilized under that hydrothermal.
Yes, sir.
After that, you have coated with that
Yes, sir.
or in that hydrothermal, you are added PVP.
So, PVP is added in the hydrothermal setup itself.
So, because
So,
of that, any effect is happening over there?
so because there is a change of size of nanorods after PVP treatment, so that might be a reason, but I will look into it more. Sorry, sir. Yes, sir.
हाँ, अभी आपने ये कहा कि ये जो है लेड के केस में दैट इज द लेड ऑक्साइड पीक.
Yes, sir.
XPS doesn't give any phase information as such. It gives you elemental charge state information, right?
Yes.
So, I mean, there are two features. So you have to understand what is the origin of those individual features. Are they the satellite features or what?
Okay,
or
yes,
the
sir.
heterovalent
For
states features.
lead
So
and bismuth.
so this is what you have to understand. Then
Okay,
again, you
sir.
can see similarly your cerium 3D. You can see that the black curve is slightly having some kind of shoulder feature just below
Yes, sir.
the main feature, right?
Yes, sir. Towards
So,
lower value.
Not towards that shoulder
here.
thing.
Okay.
अरे main peak के थोड़ा से हाँ वो
yes,
shoulder
sir.
feature, right?
Okay,
So
sir.
that means that for that particular sample you have some heterovalency of cerium, right? So this is what you can check. Again,
sure,
you
sir.
showed some schematics on different energy levels, right?
Yes, sir.
And there I could see that you had shown some gap for silver also here, right?
Yes, sir. For
हाँ,
silver.
तो silver में gap क्यों है?
No, sir. It's just for the schematic purpose.
अरे,
it's a metal,
But that's your energy states, na?
Yes, but
So silver is your metal case. So where is your Fermi level? Is it drawn with respect to some Fermi level or what?
yes, sir. For means it is drawn with respect to vacuum.
This is what
level.
with respect to vacuum. Then
Yes.
what is this gap representing in silver? Silver is your
FTO.
metal, na?
Yes, sir.
Right. So it should
Yes,
not
sir.
have gap
The
as
gap.
such. Okay.
Yes, sir.
तो उस वो सब थोड़ा सा देख लीजिए.
Sure, sir. Thank you, sir.
In even your WH plot,
Yes, sir.
you have made one linear line, na?
Yes, sir.
But not a single point is going from that line.
Yes, sir, because it was linear fitted in origin software.
And
So
second, your electron diffraction pattern, can you show me that?
yes, sir.
So here you have observed rings or just dots?
So dot spots only, but in a
That
ring
yellow color ring you have
circle.
drawn, no?
Yes, sir, I have drawn that to show the plane
There is
positions.
something else. If you
Okay.
get only spots and if you get the circle rings,
Okay.
So if the rings are there, then it's a
Polycrystalline
and if
material.
Then this is they will be single crystallite or something like that.
Okay.
So you are changing something else here.
No, I will check it. So thank you so much, sir.
By the way, interface is always buried, right?
Yes, sir.
Then what is buried interface?
Sir, in perovskite case, there are two interfaces like ETL and perovskite interface is buried interface, and the interface between perovskite and HTL is known as top interface. Thank you, sir.
Thank you, ma'am. Also, I would like to thank our session chair, Professor Kamre and Professor Saeed, for being with us. We truly appreciate your efforts and time. Now, I have to make an announcement. We are now continuing our thesis presentation. Following this, we will have our talk by Dr. Makoto Shinde. After that, we will have a trick break. Now, it is my honor to introduce our session chair for this session, Professor More and Professor Sartade from the Department of Physics, Savitribai Phule University. Sir, I warmly welcome you and invite you to take your seat as a session chair. Now, moving forward, we have a thesis presentation by TP1 Pratibha Shinde.
प्ले कोणतं आहे?
हे बघ थांब
हे असं ना?
एक मिनिट दुसरं धक्का दाबतोस इकडे हे बंद झालं ना 10 मिनिटं घेईल. हे बघ हे फॉरवर्ड बॅकवर्ड आणि हे पॉइंटर फक्त
हे फॉरवर्ड आहे. Hello everyone, myself Pratibha. I am going to present my thesis work entitled with Photoelectrochemical Investigations of Zinc Oxide Based Thin Films for Water Splitting Application. So chapter 1, General Introduction and Background. So as we all of us know that the global energy demand is increases day by day due to the rapid industrialization, population growth and the increased standard of living. Here in this pie chart and this graph we can see the majority energy production still relies on these conventional energy sources like coal, crude oil and the natural gas and nuclear fuel. But use of these conventional energy sources will put very bad impact on the environment like air pollution, water pollution and global warming, and this will ultimately affect on human health. Recently the field of conversion of a solar energy into the chemical energy by using the photoelectrochemical water splitting gain attention due to the produced green hydrogen has a potential to replace these conventional energy sources. So in this process the water molecule is splitted into the hydrogen and oxygen by using the semiconductor, and that produced hydrogen can be used as a fuel and it can burn with a zero carbon emission with water as a byproduct only. So let's see the principle and mechanism. So this is a 3 electrode PEC cell used to split water into the oxygen and the hydrogen. It consists of a 3 electrode, semiconductor photoelectrode, platinum electrode and the reference electrode. It basically involves the 4 steps. In the first step there is a generation of a electron hole pairs when the semiconductor is illuminated by the sunlight. That photo generated electron hole pairs get separated due to the electric field present at the interface. The photo generated holes migrates to the surface where it oxidizes the water molecules into the oxygen and the H plus ions, and whereas the electrons are reached to this platinum electrode where it reduces the H plus ions produced during the oxidation of a water. So this is the overall water splitting reaction. Next, material challenges. This photoelectrochemical water splitting is very complex process because the photoanode material used in a PEC cell should satisfy the several criteria simultaneously. The first one, suitable band gap, means the material should able to absorb the maximum portion of a sunlight from the solar spectrum. Then appropriate band alignment. The band edges of the photoelectrode must straddle with the redox potential of a water. Here we can see the straddling of a band edges of a various semiconducting material to the reduction and oxidation potential of a water, and the material should be stable in an aqueous environment. It should possess high surface area and cost effective. So metal oxides are widely studied as a photoelectrode material in a PEC cell due to their abundance, low cost, stability, tunable electrical and optical properties. But among them, zinc oxide can act as a promising electrode because of favorable band edge positions, good electrical conductivity, high electromobility and compatibility with hybrid system. Despite having these advantages, there are certain limitations of a ZNO, limited optical absorption as the wide band gap of a ZNO, photo corrosion in aqueous electrolyte due to the photo generated holes, then recombination losses as the ZNO has high exciton in binding energy, and then low hole mobility. Chapter 2, synthesis, characterization and data analysis method. So, zinc oxide thin films were electro deposited on the surface of a FTO by electro deposition method. This is the actual experimental setup and this is the schematic of a electrochemical process. Then next, chemical part deposition and the RF magnetron is used to deposit the or is used to form the heterostructure of a zinc oxide thin films. So, this is the PEC measurement setup, consists of a potentiostat, solar simulator acts as a illumination source. Then this is a 3 electrode PEC cell consisting as a platinum plate as a counter electrode, reference electrode, and in opposite to that there is a working electrode. Characterization, all synthesized thin films were characterized by XRD, Raman, FSM, EDS and transmission electron microscopy. Then chapter 3, synthesis, characterization and photoelectrochemical performance of analysis of AU sensitized zinc oxide copper oxide heterostructure thin films. So, why zinc oxide copper oxide for PEC water splitting? So, as we know the limitation of a zinc oxide wide band gap, so it absorbs only the 5% of the solar spectrum. So, when we couple the zinc oxide with a copper oxide, then the absorption will increase in the visible region because of the low band gap of a copper oxide. Along with this, the formation of a p-n junction between zinc oxide and copper oxide effectively separate the photo generated charge carriers due to built in electric field, and the band edges of the hybrid system or zinc oxide copper oxide system shows well straddling with the water redox potential of a water. Then roll up surface plasmons. The plasmons are decorated over the surface of this zinc oxide copper oxide heterostructure. So, these plasmons can enhance the optical absorption through surface plasmon resonance effect, and the hot electrons produced during the sphere effect can be transferred to the conduction band of this heterostructure, and which can further participate in the water splitting reaction. Then experimental procedure, zinc oxide nanorods were synthesized by using the electrodeposition method. Then this copper oxide is loaded over the surface of a zinc oxide nanorods by chemical bath deposition. The precursor solution is varied. The copper acetate is used as a precursor solution. That solution is varied from 0 millimolar to the 2 millimolar, and the corresponding heterostructure thin films are designated as ZC.1, 0.5, 1 like that. So, optimal loading of a copper oxide is observed for a ZC.5 sample, and hence the AU nanoparticles are decorated on the surface of this ZC.5 sample by electrodeposition method. So, this is the FSM and EDS analysis. Here we can see the first figure shows the FSM image of a zinc oxide, whereas this B, C, D, E, F shows the FSM images of the heterostructure thin films. So, for ZC.1 we can see the copper oxide nanopetals are get randomly distributed in phase between the zinc oxide nanorods, where as the concentration increases, the copper oxide nanopetals are get agglomerated, and there is formation of a flower like structure which provides the more heterojunction points, and which is beneficial for the PEC activity. As we increase the precursor concentration further, the density of a copper oxide nanopetals increases, and finally they get stacked together, and there is a formation of a thick layer on the surface of a zinc oxide nanorods. This last figure is the FSM image of a AU sensitized ZC.5 thin film. Here we can see the AU nanoparticles are beautifully sensitized over the surface of a ZC.5 thin film without losing its structure. So, this is the elemental composition obtained from EDS analysis. We can see the concentration of a copper goes on increasing as the precursor concentration increases. From the XRD and the Raman spectroanalysis, we confirm the formation of a zinc oxide and the zinc oxide copper oxide heterostructure as the components of both the material present in the spectrum. The peak intensity of a ZNO goes on suppressing as the concentration of a as we increase the copper loading. UV visible spectra analysis. So, in this UV visible absorption spectra, we can see all the heterostructure thin film ZC.1 to ZC2 shows the enhanced optical absorption compared to the pristine ZNO, and this absorption of a ZC.5 sample has significantly increased, this brown plot, when we synthesize ZC.5 sample by AU plasmons through the surface plasmon resonance effect. Then the band gap of the thin films goes on decreasing as we increase the copper oxide loading. These are the XPS spectra for the ZC.5 AU photoanode, ZC.5 AU heterostructure thin film. So this confirms the presence of its constituent elements like zinc, copper, gold and oxygen, and also it confirms the oxidation states of elements present in the sample. So this is the then next PEC measurements. PEC measurements were carried out on a potentiostat. For that we have this kind of setup. 0.1 molar Na2SO4 electrolyte is used for PEC measurements. Solar simulator as a light source, counter electrode is a platinum plate, and the saturated calomel electrode is used as a reference electrode, and working electrode is nothing but our synthesized zinc oxide and heterostructure thin films. Linear sweep voltammetry. So in that first, in linear sweep voltammetry, the samples, all the samples are linearly scanned in over the range of potential, and the corresponding photocurrent density is recorded. The photocurrent density directly reflects the ability reflect the how efficiently the material splits the water. So we can see here this black curve is for its ZNO. So for ZC.1 and ZC.5 the photocurrent density is increases, but as we for further loading of a as higher for higher loading of a copper oxide, the photocurrent density goes on decreasing. This is due to the blocking of active sites of a underlying ZNO, low optical transparency due to the blackish color of a copper oxide, and the recombination losses due to the thick layer of copper oxide. After plasma sensitization, we can see the photocurrent density reached the 1.07 milliampere per centimeter square, which is almost 2 times higher than the pristine ZNO. In this way, we are successful in improving the PEC performance of a ZNO by forming the heterostructure with copper oxide and the AU plasma sensitization. The applied bias photon to current conversion efficiency was calculated by using this formula and the LSV curve, and the ZC.5 anode displays highest applied bias photon to current conversion efficiency. EIS analysis is carried out to investigate the charge transfer mechanism and the recombination losses at the interface. The Nyquist plot shows the impedance of the system. Each point shows the impedance of the system calculated at the particular value of frequency. The small semicircle, small radius semicircle implies low charge transfer resistance. That means the hole suffers from a low resistance to migrate through the electrolyte at the interface. And then the lifetime of a electron was calculated by using the body plot, and the highest lifetime of a electron is observed for a ZC.5 AU photoanode, which is 8.60 microsecond. Mott-Schottky analysis are carried out to study the voltage dependence of a space charge layer. So the capacitance of the space charge layer is related to the applied bias is related to the by this equation, Mott-Schottky equation. From this equation we can calculate the various electronic parameters of a semiconductor like charge carrier density, flat band potential, deflection width, etc., and conductivity of a sample. The presence of both positive and negative slopes in the Mott-Schottky plot implies the presence of or confirms the formation of a p-n junction in all the ZC samples. The ZC.5 AU photoanode shows the highest charge carrier density and implies the higher PEC performance. Then all the photoanodes are implied for the photo response. So all the synthesized thin film shows the good photo response over the under the CHOP illumination, and the base sample, that is AU sensitized ZC.5 sample is subjected to the stability test. It shows the good stability up to the 1200 second, but after that the photocurrent start decreasing. This is maybe due to the photocorrosion of a electrode, and hence the surface modification of that sample is needed in order to enhance the stability. This is the charge transfer mechanism and the schematic of a PEC water splitting process. Here we can see when the heterostructure is when this photoanode irradiated by the light, there is a generation of electron hole pairs in zinc oxide and copper oxide. The hot electrons in space in AU nanoparticles are transferred into the conduction band, and then finally collected at this platinum electrode, where it reduce the H+ ions and produce hydrogen, whereas the photo generated holes migrate to the surface and oxidize the water molecules. Conclusion. The zinc oxide copper oxide AU heterostructure has significantly improved the PEC performance of a pristine ZNO due to increased optical absorption and reduced recombination losses due to the heterostructure formation. AU plasmons enhance the optical absorption and charge transfer through the surface plasma resonance effect, and the stability of this photoanode need to be enhanced through the surface treatments. These are the references which I have reviewed during this work, and this work is published in International Journal of Hydrogen Energy. Chapter 4, Synthesis, Characterization and PEC Analysis of Zinc Oxide, MOS2, nanosheets, nanorods and nanotubes, heterostructure thin films. In this, we vary the morphology, and MOS2 is deposited on the surface of a zinc oxide. So, why to integrate MOS2 with zinc oxide? Again, same, the MOS2 extend the optical absorption, enhance the charge separation due to type 2 band alignment between zinc oxide and MOS2. Then increase stability. As MOS2 is stable, it can protect the ZNO from photo corrosion in aqueous electrolyte. Also, the synergistic morphology means the MOS2 sheets are very flexible in nature, so it can easily wrap around the zinc oxide structure. There is a formation of a core shell structure which is beneficial for the rapid movement of charges, and also it provides the high effective surface area for water splitting reaction. So, this is the experimental procedure. Here we synthesize zinc oxide nanosheets, nanorods and nanotubes through the electrodeposition method. Then MOS2 is deposited on the surface of this zinc oxide, pristine zinc oxide thin films by RF sputtering method, and the corresponding films are designed as ZMS-S, ZMS-R, ZMS-T. So, these are the deposition parameters employed for the deposition of a MOS2 on the surface of a zinc oxide thin films by RF sputtering. FSM and TM analysis. Here A1, B1 and C1 are the FSM image of a pristine ZNO, whereas A2, B2 and C2 are the FSM images of the heterostructure sample, ZMS sample. So, in FSM there is no change in surface morphology observed, except the surface become noticeably rougher, but the presence of or the deposition of a MOS2 is clearly visible in a TM images of a ZMS2 sample. Here we can see the MOS2 layer is beautifully wrapped around this zinc oxide core. This black part is a zinc oxide tube, and this is the MOS2 layer. And this figure shows the MOS2 deposition occurs on the both inner as well as outer wall of the tube. XRD and Raman spectroscopy analysis. So, all the diffraction peaks in this XRD spectra, XRD pattern are associated with the Woodside hexagonal structure of a ZNO. There are no signature peaks of MOS2 observed because because of the thin layer of a MOS2. But the presence of a MOS2 can be detected in the Raman spectroscopy, as it consists the Raman peaks at 407.3 and 377.3 centimeter inverse, corresponding to E2G and A1G vibration of a MOS2. Then in UV visible analysis, we can see the optical absorption has significantly enhanced after the MOS2 loading. ZMST sample shows or exhibits highest optical absorption due to its tubular structure, as the light photons can be trapped inside it. On the band gap, there is a noticeable reduction in the band gap of a zinc oxide heterostructural themes due to the MOS2 deposition. These are the XPS spectra confirming the presence of constituent elements sulfur, zinc, molybdenum, oxygen in the ZMST sample. So, these are the PEC characteristics, JV and EIS analysis. Here we can see all the ZMS sample shows the enhanced photocurrent density compared to the pristine ZNO. The highest photocurrent density is observed for this ZMS-T photoanode. This is because of the increased optical absorption due to the MOS2, effective charge separation due to the heterojunction formation, and there is increase in number of catalytic active site as the MOS2 is deposited on the both side of a nanotubes. So, ABP is calculated from this formula. JPH is the photocurrent density, 1.23 minus V bias is the applied bias potential, and P light is the power of a incident light, which is 100 milliwatt per centimeter square. Then EIS analysis was carried out. These EIS results are consistent with the IV plots, and the most extended or prolonged electron lifetime is observed for a ZMST photoanode, which is equal to 13 microseconds. Then Morse-Schottky analysis was carried out to know the to obtain the values of electronic parameters like charge carrier density, flat band potentials. So, more negative flat band potential of this ZMST photoanode implies it requires lower potential to initiate the hole transfer or water splitting reaction. Then next, stability states. All the synthesized thin film shows the good stability, good photo response under chopped elimination, and it shows the excellent stability over the 4000 second. So this photoanode acts as a so in this way, in conclusion, in this way we enhance the PEC performance of a zinc oxide. The combined system of a zinc oxide and MOS to greatly enhance the PEC performance of a ZNO. The highest photocurrent observed for ZMST photoanode, which is almost 3 times higher than the pristine ZNO. The nanotube morphology provides more catalytic active sites for the reaction and hence enhance the PEC activity. And also the zinc oxide MS2 heterostructure photoanode exhibits excellent stability in aqueous electrolyte, and hence it can act as a it can present the promising pathway for green hydrogen production via this photoelectrochemical water splitting process. This work is published in ACS Applied Energy Material, some references. So in this way we have successfully produced the green hydrogen. We can see here the hydrogen bubbles on the platinum plate using the synthesized photoanodes. These are the list of first author publications, co-author publications, conference attended, acknowledgement. I acknowledge to my PhD guide, Professor Sandesh Zadkar sir, for his constant support and guidance, my lab mates for their valuable discussion and suggestions, my 6-month review committee, Professor Sunit Rane, Professor Maurya sir and Professor Adinath Hunde sir. I thankful to the MNRE for research fellowship and financial support, Professor N.B. Zaure sir for IPC measurement, Professor Sachin Rondia sir for TM measurements and analysis, Head of Department of Physics, all teaching and non-teaching staff, and my family and friends. Thank you.
You made zinc oxide nano rods, nano sheets, right? How do you make by electrodeposition zinc oxide first thing? Because what was your precursor? What was the source of oxygen?
I have mentioned here. Zinc nitrate and KCl is used for the synthesis of a zinc oxide nanosheets, and
exactly. My point is that what was the source of oxygen? Because in this case you are getting Zn2
firstly
plus
this nitrate ions undergoes oxidation, and that is the source of oxygen there. There is a formation of a zinc hydroxide. Here is a chemical reaction. So this NO3 minus ions takes electrons from cathode. There is a formation of NO2 minus ions and the hydroxyl ions. There is a formation of a zinc hydroxide which is unstable under given conditions.
But you make it on cathode, right? You apply the negative potential. So why this NO3 to or NO2 minus, whatever, these negative ions will go towards negative potential? I mean, when you do electrodeposition, what was the potential you applied?
Minus
negative potential,
negative
right?
potential.
So negative potential will not attract negative ions.
It attracts Zn2 plus ions.
Right. But then NO3 2 minus will not be attracted towards that. You understand my question, right?
Sir. What is the source of oxygen? But this is the this one of the reaction I found in literature where they show.
But you have to understand how does it happen, right? All right. Why do you get different morphologies?
Sir, because of KCl, the natural tendency of a zinc oxide to grow in 1D direction, but as we add the KCl, it increases the Cl minus hinders its growth along this Z direction, and hence there is a lateral growth, and hence we get a zinc oxide nanosheets.
But why are you getting? Why are you not getting potassium in your zinc oxide K plus? Because it's also Zn2 plus, and you are having K plus also.
KCl is added. KCl.
So you are having K plus, right? So K plus can come. Did you check that?
Sir, but we applied the potential, that potential which can only reduce the Zn2 plus ions, not K plus.
What was the standard oxidation potential of Zn2 plus and K plus?
Zn2 plus for there is a minus 0.76.
And what is for K plus?
So that I have not seen.
Then how do you say that? No, it is not possible. Yeah, and
I will check, sir.
you again the same question I asked in the morning session. You said it is heterostructure, right? But you don't see two absorption edges. Why? Two absorption edges when you are having optical absorption spectra.
Instead of getting two absorption edges, we got a broad absorption edge. That means that these two absorption edges may blend together due to the combined effect of this absorption of these two material. There is some interaction at the interface. That is why.
No. Can you just show me schematic here? Any schematic?
Which ones?
The previous one. Previous one. Schematic, yeah, maybe here. You can see that this zinc oxide and copper oxide are they are separate, right? So they should show some absorption because of copper oxide and because of some zinc oxide also.
But I got only single absorption edge.
But why? That's the question.
So there may be the presence of
Because
two
their
absorption edge,
band
but
gaps are very different. What is the band gap of copper oxide?
1.8 electron volt.
And what is the band gap of zinc oxide?
3.2 electron volt.
So they are very different, no?
But sir, I will check that one also.
All right. And why you have shown, because you said that when your copper oxide coverage is increases after certain, then keep it that.
Okay.
You said that then you are having more coverage, right? It blocks the sides. But in your schematic, what you have shown, it is not fully covered.
So this is for base sample, ZC.5 sample, optimal
So for
loading.
base sample also, you mean that